Yeah, but yeah, that's.
Yeah, and everything around the border.
Yeah, so it should use this.
Yes. Fine.
Very small level. I saw no one from university. Maybe I have a lot. Like.
This is fine. This is fine.
Yeah. This is just this.
Oh, I just lost. Actually, I was.
Yeah, I could tell. I said,
Yeah.
Sorry?
Yeah. I'm waiting for away, like the area.
Okay. Okay, so, wonderful to see you here. Welcome to Minnesota. Welcome to finding the theoretical physics. And it was, as you know, summer school activity, the part of time and collaboration of superconductivity, and also general activities during school and workshop at fine and so just for this meeting. As you know, there are three of us who will be lecturing. Each of us will give 4 lectures and interrupt. Feel free to interrupt me, seriously. Feel free to interrupt speakers, but speaker will have a right to say no. We'll discuss it later. Just in order not to interrupt the presentations that much. At the end of each lecture, there will be 10 minutes for questions. So if you have questions about general things, leave it towards the end of the lecture. And don't be shy. Seriously, don't be shy, interrupt, ask questions. Do it for you. So it's for you to decide over. Next, there will be 1 minute, essentially 1 minute presentation before posters. This will be oral presentation. And it's up to you to choose whether to say something just like I'm talking to you without any slides or put one slide. If you want to put a slide, then send the slide to FTPI, right? Yep. And then we put it on a computer, because if you come with your computer and we'll start doing this, you spend several seconds of your previous time. Now, the last thing, as we arranged, it's a sort of special school in the sense that you will do work. Not only us will be working, but you will do work as well. So we want to split you into 3 groups, give you homeworks, and such that on Friday, each of the group will make presentation, and you choose how you will make presentation, who will be making presentation. I guess we arrange it as half an hour per group period. And then, yeah. So what we will do, we will give you a piece of paper, which will be split into 3 columns, and you will put your name into one of the columns, but you will see, we want roughly the same number of people in each column. So if you see there are more people in one column, put your name in the other column. If you want to participate in the activities of all groups, you are more than welcome. If you want to solve all problems that we give to you, you are more than welcome to solve all problems. Yeah. Finally, before I inform you to Megan about Wednesday, it will be excursion, and part of the excursion will be Minneapolis Institute of Art, which is Minneapolis Art Gallery. Those who never been to Minneapolis Art Gallery, I would very much recommend it, because it's really capital city style art gallery, so it's pretty high quality. So if there will be no rain, then we'll go to Minnehaha Falls, which is a wonderful thing for hiking and looking at the waterfalls, etc. If there will be rain, probably will stay. Yeah. Okay. With this, if there is no immediate questions, Megan. But if you don't know, Megan and Alicia are 2 people most important for this workshop. You will get nothing if you don't go.
Okay, so make sure you got your ticket for lunch. If you didn't get it, grab it at the break. If you can, if you leave the room and come back, use the back doors instead of coming in this way. While there's a presentation, you can leave your backpacks in that room during lunch if you want to, don't have to, but it'd be easier to do it over there instead of leaving it here. We'll lock the back doors, but just in case. For lunch, we'll have the lunches out there to grab box lunches. And you can go wherever you want on campus, but if the garbages are full, it would be nice to bring them back here because they fill up outside. What else? You can put your posters up at lunch or whenever you want tomorrow. It's fine too. I'll put a Google link on the website to upload the one slides. And that's it. Feel free to email me if you have any questions.
Okay, and if you need, we'll provide lunches. There will be pizza party on Wednesday, but otherwise dinner is on your own. So if you need suggestions for a go nearby, there's a bunch of nice places, not that expensive. So if you want advice, ask us. We'll tell them. Now, the very last thing. So chairmanship at the sessions will be provided by local students. And David, it's your turn now. So go ahead, introduce the speaker and.
Hi, yeah, so I'll be chairing this first session with only one talk, so hopefully my job is easy. But anyway, so this is a talk by Dan Agterberg from the University of Wisconsin-Milwaukee, and he's going to be talking about this intertwined electronic degrees of freedom, applications of superconductivity and magnetism. As Andrey said, it'll be 90 minutes total. After an hour 20, though, we're going to open up.
All right, well, thank you. And thank you all for coming here. All right, so what I thought I'd focus these lectures on is largely the role of symmetry in Bogomolov-Dejean Hamiltonians and normal state Hamiltonians. And so what I hope you get out of these is you become comfortable with understanding the symmetries of both these types of Hamiltonians. And one degree of freedom I'm going to focus on a lot is the sublattice degree of freedom in systems. And so I'm going to go into a lot of detail in deriving normal state Hamiltonians where the sublattice degree of freedom is important. So you can see how to write down general tight binding Hamiltonians for these. And then I'm going to use examples of these kinds of tight binding Hamiltonians in conjunction with the Bogomolov-Dejean Hamiltonian to show you where I think some interesting physics lies and where you can draw some physics out. But the main message of this is how do we use symmetries in both the normal state Hamiltonian and in the Bogomolov-Dejean Hamiltonian. And so to do this, especially when I get to the normal state Hamiltonian, I've actually borrowed some online slides from Jennifer Cano, which talks about space groups, Wyckoff position, which is your sublattice, site symmetries, and band representations. And then also later on, I think I'll have time to talk about altermagnetism, and in particular, a topological altermagnet. And there I borrowed some slides from Jorn Vanderboats. Okay, so what's the motivation? I think, especially in superconductivity, if we go to sort of the original development of sort of much of what we do in superconductivity today, that came in, say, the late 80s, early 90s. The whole emphasis there was a single band picture, and then the role of symmetries in that single band picture to tell us a lot of properties of the superconducting state. But then, of course, we realized that going beyond the single band picture is important. So I'm sure many of you here work on things like quantum geometry and topology. And there we generically have to go beyond the single band picture. And we want to understand what does this mean in the context of superconductivity and also in the context of magnetism. And so I'll start with a sort of standard symmetry classification of the single band theory so we can see what that is. And then I'll go to a topological classification focusing on the low energy excitations of the Bogomolov-Dejean Hamiltonian. And so you can see how symmetry enters in topology and tells us something that wasn't here before. And then I'll talk about nodal classes that come from this and give a series of examples of this. And then in this whole process, I'm going to say, okay, we do need to understand more degrees of freedom than just a single band picture. And so then I thought I would do a systematic development of how we include these more degrees of freedom. And so what happens when we have orbital and sublattice degrees of freedom? And then I'll talk about a symmetry-based construction of tight binding Hamiltonians. We'll construct 3 of these Hamiltonians. One of those will be homework for you. And then of those 3, I'm going to apply them to superconductivity and to magnetism. So that gives you a flavor of where I'm going with this. Okay, so let's begin. Most of the emphasis in this is going to be on low energy quasi-particle states, both in the superconducting case and in the magnetic case. And one of the reasons we do that is because these are readily measurable. And in particular, ARPES has often seen low energy excitations in superconductors. So here, dating back already to year 2000, here's some data from ZX Shen's group in the cuprates. And what he can see is he can see as a function on the Fermi surface here, he can see zero energy quasi-particle states emerge, and he can look at evolution as you go from above TC to below TC. And so here you can see a well-defined low energy quasi-particle in the superconducting state. And then a decade or so later, this was also done for iron-based superconductors. And here ARPES clearly measures all kinds of features of these gaps. And so understanding this is an important prediction of any theory we have. And in addition, it's something that's easily measurable. And so this is often a focus. And then in addition, these low energy quasi-particles are of course important for many other properties of superconductors. For one, low temperature thermodynamics. And so if we have low energy quasi-particles, we get excitations, and those excitations have typical spectra. And so here's one very well-known example in YBCO. So this is the penetration depth. The penetration depth tells us how far a magnetic field enters into a superconductor. And you can measure that as a function of temperature. And there was this very important experiment that showed that this is linear in temperature. All right, and that told us that there are low energy quasi-particles in the superconducting state. And then even decades later, these kind of measurements are still regularly being done. And so here's an example from strontium ruthenate, where the thermal conductivity is measured. And if you have a particular nodal structure, you can see that the generic form of the thermal conductivity is like this, has a constant plus a linear and T dependence. And that's what was seen in the data on strontium ruthenate. And so probing all these responses is a direct measure of these low energy quasi-particles. And then finally, in many cases, low energy quasi-particles are closely linked to topology. And so often if we have zero energy states, then that also means we have edge states in our samples as well. And here's actually not an example from superconductivity. This is from graphene. But in graphene, we have these Dirac points. And we know that in graphene, we have edge states, and those edge states are protected by a chiral symmetry. And they've been observed in a variety of experiments. Right? And so in superconductivity, the same chiral symmetry shows up in many cases. And in fact, in the cuprates, it shows up in, it's been well observed and well studied. Okay, so that was just to give you a motivation for why we understand the low energy quasi-particles. And now let me switch to superconductivity, starting with pictures that are in the single band limit, but I'm going to talk about also sort of Bogomolov-Dejean Hamiltonians in larger spaces in the single band limit. But this is a good place to keep in mind the kind of ideas that we're going to be developing. All right, so I'm going to be focusing on basically the weak coupling limit, so BCS superconductivity. And I think you'll hear more about that in both Andrey's and Nikolay's lectures. But the premise is I'm going to have a Fermi surface And for most of this, I'm going to keep the Fermi surface two-dimensional because that's the easiest to draw, and so we can highlight the points. And so here's our Fermi surface. And what's important for BCS superconductivity is we want to get the BCS log, and you'll hear about that. But that log comes because we have a degeneracy between states at momentum k and states at momentum minus k. And we have to have this degeneracy for all k to get this BCS log. And so we can ask the question, how do we get this degeneracy? And in 3 dimensions, there's 2 symmetries that ensure this. One symmetry is inversion symmetry. That takes an electron at state k at momentum k to electron at momentum minus k and keeps the spin the same. It's also mentioned throughout, we're going to have 2 spin species here and 2 spin species here, and then also go to larger spaces as well. All right, the second symmetry that takes k to minus k is time reversal. Time reversal takes the state from electronic state from k to minus k and flips the spin. And so I'm going to assume in our normal state, except for a couple of your homework questions, that we have these 2 symmetries in the normal state, both time reversal and inversion. And when we have time reversal and inversion, we have their product. And this product's going to be an important symmetry. So this product takes k to k itself and flips spin. And that symmetry squares to -1. It's a symmetry that's valid at local k, so it sits in the so-called little group at k. And that means that we can use it to classify the degeneracies there. And then we have a twofold degeneracy because this is an anti-unitary operator that squares to -1. And so we have a degree of freedom that's like spin when we have this symmetry present. And we can ask, you know, our usual understanding of this degree of freedom is spin, so spin 1/2. But we can ask if it's given by this symmetry, is that actually, are the 2 degenerate states, are they really the same as spin 1/2 or not? And we're going to go to examples where this is not the case, and you'll see some new physics come out of that. Okay, so we have a twofold degeneracy in the normal state, and now we can switch to the superconducting state and what we mean there. And so we all understand that in a superconductor, we get a gap, and that gap is typically momentum dependent. And usually when I talk about a gap delta of k, it means it's essentially it's essentially on the Fermi surface of the system, and maybe within some small energy spread around there. And then this gap, of course, can be anisotropic. It can change signs. And so here's the D wave gap from the cuprates, where I go from plus to minus to plus to minus. We have these zeros here. And this just simply means the gap at this point is large. The gap at this point vanishes. And the gap at this point is also large, but of opposite sign. All right. So the one thing to remember here are these 2 key symmetries, inversion and time reversal, because when we talk about the topological classification, I'll be focusing on these 2 symmetries as well. And then also the fact that we have a pseudo spin coming from this condition, time reversal times inversion squares to -1. Okay, so let me now switch to sort of the object we're going to talk about most generally, and I have some notes I want to put on the board here as well to specify that. Okay, but let me. Okay. All right, so this is the Bogomolov-de Hamiltonian that we're going to be using. And the way we get this is we have a normal state Hamiltonian, and I'm going to talk in detail about how we get this normal state Hamiltonian. In the common case that I just showed you before, there's 2 degrees of freedom, and those are pseudo-spin degrees of freedom for this. But we're going to go to larger spaces. Typically, we're going to consider up to 4 degrees of freedom here. And so we have a normal state Hamiltonian, and then what we do when we add superconductivity, we have some interaction that gives us superconductivity. We treat that within mean field theory, and when we treat that within mean field theory, we get a gap. All right, and I'll talk about the properties of that gap in a second. We'll go into some detail about that. But then we also know that we want to be sure that we're pairing, well, we call electron and hole states, but these are described by, say, fermion operators C at K. Then these are described by Fermi operator C at minus K. And so we want to, when we do the mean field decoupling, we want to break up these two blocks. And so I'm not going to talk too much about the origin of this, but I'm going to tell you some things about why this transpose shows up and why this minus K shows up. And I'm also going to talk about the origin of this delta Q. But let's start now first with this HN. Oh yeah, and for the purpose of homework, I wrote down here a Bogoliubov-de Gennes Hamiltonian for a superconducting condensate that carries a finite momentum. So psi q e to the iqr. So this is actually a vector q dot r. And for most of what I talk about, I'm going to set q to 0. But like I said, there's one homework question where you're going to include this q and you're going to figure out what the spectrum of the system is in the presence of this finite q. But if we have this BDG Hamiltonian, you're going to have to be told what is the delta of q. That's calculated somewhere else. And you're also going to have to figure out what the q is. This comes from your mean field decomposition. You get a self-consistency relationship. This here comes from the condition that the total supercurrent in your system, if you're in equilibrium, is 0. And you can actually derive an expression for q. So it may seem confusing for those of you familiar with supercurrent carrying states. You think this is a supercurrent carrying state, but in the context I'll be talking about, this will be an equilibrium state, and you can show that sometimes, guaranteed by symmetry, q will be non-zero. Okay? So, but you'll see that in the homework, and you may get an understanding of how that can come about in these homework questions. All right, so let's first focus on this normal state Hamiltonian. So I have time reversal and inversion symmetries. That already dictates the form of this. Inversion says that Hn of k is Hn of minus k. K switches to minus k. And then I can write it down in the pseudospin basis. And in the pseudospin basis, I have a diagonal matrix. And why do I have a diagonal matrix? So what's the, yeah?
Because of the twofold degeneracy by the antisymmetry.
Exactly. So this must be diagonal because we have a twofold degeneracy guaranteed by symmetry. Yeah.
It's diagonal, then what's the point of taking the transpose in
Where? Here.
yeah.
Sorry, I should say this is general. This is for more than just a single band picture. In the single band picture, this is the limit. So when we go to bigger Hamiltonians, this will matter. Okay. Yeah, so good question. All right. And then just so that you can see kind of where we're going, this epsilon 0 of k, this is a chemical potential, epsilon of 0 k. This is just tight binding on a square lattice. And most of the examples I do will be on a square lattice, so we don't have to deal with too many different particular examples of groups. Okay, so I told you we're going to focus, we're going to focus on symmetries. And so let's begin with time reversal symmetry and how we write it for this particular normal state Hamiltonian. And so here time reversal, and this is actually going to be general. So this is not just the single band case, but larger. It's going to be written as this complex conjugation operation times some unitary time reversal operator. Okay, so some u of t. And we can ask, what is that? Okay, so we can ask, how does this operate on this normal state Hamiltonian? And here's the definition. Okay, t Hn of k t inverse. We can implement this complex conjugation operator times this u of t. We get ut dagger, and we get the complex conjugate of the Hamiltonian. And then we define that as saying this takes the Hamiltonian at k to the Hamiltonian at minus k. And we'll be deriving relationships like this later on when we talk about the normal state Hamiltonians. Okay, so for the single band case, this time the unitary part of the time reversal operator is just I sigma y, which is just 0, 1, minus 1, 0 as a 2 by 2 matrix. Yeah. And we can also ask about inversion symmetry. Inversion symmetry is a unitary operator. This is an anti-unitary operator. That's why complex conjugation here. Inversion is a unitary operator. So it's just described by the unitary part here. And this U of I in the single band case is trivial. It's just an identity matrix, but when we look at other examples, it won't be trivial. And then we can also ask how it operates on the normal state Hamiltonian. And so here we're doing the same thing as before. I get UI Hn of k UI dagger, and that is by definition of inversion equal to the normal state Hamiltonian at minus. Okay. All right, so now let me just talk a little bit about our choice of Bogusław-de Gennes Hamiltonian, because it turns out there are other choices. And I wasn't careful to take my notes out beforehand. Let's see. All right, okay, this will work. Okay, so here, when we do this Bogusław-de Gennes Hamiltonian, we assume that we have some pairing interaction. Actually, which is some matrix. And we have some internal degrees of freedom, and an M prime could be, for example, spin. So this can be spin up and spin down. And so when we decompose our mean field Hamiltonian this way and write our pairing interaction this way, then we get this form of the Bogusław-de Gennes Hamiltonian. It turns out that this actually has some difficulties. And these difficulties have been pointed out by Kirill Samokin and Blount back already in the 70s. And in particular, when we write down the Bogusław-de Gennes Hamiltonian, this object doesn't transform nicely under rotations. And you can check that yourself, and I'll give a reference to that in a second. But there's another way of writing this, which we can write as follows. So here I've introduced another operator at the same momentum k. And here and what this formally is the time reversed operator of the original state. Okay? And so what this does is the time reversal takes k to minus k. So this is almost the same as that, but it's not the same. And the nice thing about this formulation is if we now do symmetry operations on the full Bogusław-de Gennes Hamiltonian, then the Hamiltonian transforms as we want it to. So this is for some symmetry G. So you may ask, well, why do we use this approach as opposed to this approach? And it turns out in practice, there's only a few people who use this approach to writing down the Bogusław-de Gennes Hamiltonian. And there's actually a very simple reason for that. In this approach, we have two clearly fermion operators, and we know fermion operators anti-commute. And so we can easily apply the Pauli exclusion principle. And we'll talk about that in a second. But if I switch these two operators, I can apply the Pauli exclusion principle. The same is not true when we consider this object interchanged with this object, because there's some additional symmetry showing up because of this here. So this formulation gives you a nice transformation of the BDG Hamiltonian. And the nice thing is we can apply that transformation both to states at k and at k. In this formulation, if we apply symmetries, we're going to have one symmetry at k and the other symmetry at minus k. And so I'm going to be using this approach because 95% of all approaches is done this way. And sometimes you'll see this. Right. Yeah. Yeah.
For a triplet case, when we write this D vector and we factor out this I sigma 2, isn't that kind of equivalent to?
Yeah, it is. It is. Yeah. And you'll see, yeah, you'll see that come on. That's exactly right. So, and I'll talk about that in just a couple minutes. But okay, so
One more question.
Yeah.
There's over here.
When we are applying the transformation using time reversal symmetry, won't the n degree of freedom also change?
yeah, I mean, yes, so this is how I define, yes, but I'm defining this thing as the time reverse state of that. So the n is linked to this n, but indeed this object, if written this way, will have other components. Okay. Okay, so that was some discussion on the normal state Hamiltonian. And I'm still looking for my notes. Okay, well, you were getting close. Okay. So now let me go on. Okay, so now what I want to turn to is the structure of delta of Q or delta of K. All right. So here in the following, I'm going to set Q to 0. And as I mentioned before, Q will just show up in the homework. Okay, so it'll give you a chance to look at normal state Hamiltonians with that Q. All right, so now I'm going to characterize this delta. And so we're going to be working for now in the single band, and we'll talk later about how to generalize this to multiple bands. But we're going to have Kramer's degenerate fermions at the same K, which I already mentioned. So we have these two degenerate states, and we can define this state as the downspin version of this state. Okay, it may not transform like spin, and we'll talk about that later, but we have two degenerate states. One is spin up, one is spin down. Okay, and we're going to pair these states of momentum K and minus K. And then we also, as I mentioned, in the formulation we're using, we have we have two fermion operators. And so if we switch these two fermion operators, we have to change the sign of this pairing state because of Pauli exclusion. So we have the Pauli exclusion principle. And you can see that in this notation, if I switch these, I take K to minus K and I flip S and S prime, where S and S prime can be N and N prime. And now we're going to invoke the fact that our normal state has inversion symmetry. And because it has inversion symmetry, we can classify our pairing states according to inversion. So the pairing state is going to be either even inversion or odd inversion. And so if we have even inversion, which we describe by a scalar wave function, and we say this scalar wave function is psi of k, psi of minus k is equal to sine of k, so it's even parity, then Pauli exclusion guarantees us that this must be a spin singlet object in the pseudospin base. And so we multiply it by this I sigma y psi of k. Now, as was mentioned earlier, this I sigma y should already be familiar. This looks like the unitary part of the time reversal operator. And in fact, that is what it is, and that's what it'll generalize to. Yeah?
I had a question about the square lattice that you mentioned earlier.
Yeah.
Do you model pairing instabilities due to different like a spin channel impacting a
Yeah, go. Yeah, so you're asking about differing pairing channels when we have square lattice symmetry? Is that what you're moving to? Yeah.
Is that possible like without like a diagonal some diagonal aspect to the square?
I think I'm going to answer your question in a little bit. So we're going to look at the square lattice and talk about more details about delta of k and psi of k in those cases. So if you still have the question, ask me again and then go back. Okay, so that's the spin singlet case, but it's spin singlet and it stays singlet because it's even parity. And then conversely, if we require an odd parity gap function, then it turns out because of Pauli exclusion, that must be a spin triplet. It must be symmetric in the spin channel. And so we can describe that by this typical choice of matrix here. We have a vector d of k dot sigma. And again, we have this I sigma y, which is this unitary part of the time reversal operator. So this d of k is a vector wave function, and it is odd under parity. And typically, if we apply a spin rotation to our Hamiltonian, this transforms as a vector under that spin rotation. Okay. Now, as I mentioned, as you'll see later on, that's not always the case.
I have a question. Is it clear that it's always an SU2 symmetry, the pseudospin, or can it also be a U1 in some cases?
Okay, in what we're doing, it's an SU2 symmetry, yeah. But if we, for example, break inversion symmetry, then this can change. And maybe I should be a little bit careful about that. SU2 has associated with it a certain group structure. And then, so there will be, yeah, so sometimes that group structure isn't followed, but all transformations in that space which are SU2-like. So maybe that's not clear, but yes. Okay, I'll just say yes for now and I'll clarify later. Okay, so we get singlet and triplet pairing. And we can then ask, do we know more information about this? And in practice, we do, and I think this relates to your question. For example, if we're now beyond inversion symmetry, we imagine that we have, say, a square lattice. All right, so we have a point group which is D4H, and these are all the rotations of a square. And so I've shown those here. So there's fourfold rotation around the C-axis. There's a mirror reflection through here. There's an inversion center through here, and there's a series of twofold rotation axes. We can then classify our superconducting order parameters according to irreducible representations of the square lattice. And so here, now, so maybe some of you are not comfortable with group theory, and you may think you haven't really seen it before, but actually you all have seen it in undergraduate when you look at, for example, spherical harmonics, the LM states. Those are irreducible representations of the spherical group. And so you know something about that already. And in today's talk, or in all these talks, I'm going to focus, as I said, on this particular, well, D4. So D4H is the group D4 times an inversion symmetry. And I've not put the inversion down here because it makes this table too big. I have 5 other representations to write down. But I'm going to focus by and large on these one-dimensional irreducible representations, which makes our life a lot easier. So this is the character table for group D4. And the character table formally is the trace of the representation matrix. But for one-dimensional representations, the character table is the representation. So now I know, for example, in this particular case here, if I do a fourfold rotation for this order parameter, I have to pick up a minus sign in my gap function. Okay, and we'll see how we implement that in a second. All right, so this is what's going to define our representations. And then once we know that, this is all the information we know about the symmetry properties of our particular order parameters. I mentioned that the actual group has this times inversion, and then we label all these states with a G or a U, meaning even parity or odd parity. And so that's a pseudospin singlet or a pseudospin triplet. And then we typically assume that when we go into a superconducting state, only one of these representations is relevant. And so we're only focusing on one of these states. Okay, so once we know which representation our order parameter or our psi of k and d of k belongs to, yeah?
Below 50, couldn't you have mixed order?
You can have mixed order, and I'm not really going to talk about that too much today. So this happens if your superconducting state breaks some crystalline symmetry of the normal state or time reversal symmetry of the normal state. Actually, time reversal not, but some crystalline symmetry. Then you can, by definition, induce a second order parameter and you can get mixed order. Or you can have 2 TCs and the 2 separate TCs. Each one has a, different representation showing up. Okay. So let's go into more detail in this tetragonal case. And so this is just what we've been writing down before. This is the structure of our delta K. Here I've taken so there's the I sigma Y. And then we have our singlet and triplet parts. And then as I mentioned, these additional symmetries impose this further structure on our Cooper pairs. And in D4H, we can then look at a few representative examples. So we can look at an A1U pairing state. And I can say, well, I know my A1U symmetry must satisfy this plus odd under all odd under inversion. And so I need to write down some gap function which satisfies that. And this is going to be a combination of the spin components of the D vector, X and Y here in particular, and then the momentum components because it must be odd under momentum. And you can see that this object looks like a dot product between spin and momentum. And so it's clearly going to be rotationally invariant under all rotations. And hence it's going to satisfy whoops. Okay. So it's going to satisfy all these ones here, and then under inversion, it's odd. Yeah, okay. I went the wrong way. Okay. So you see where this comes from. And then the D wave state, it needs to change sign under a fourfold rotation. Fourfold rotation takes kx to ky and ky to minus kx. And here essentially switches these two. So it satisfies that property and it's even parity, etc. Okay. And then we can look at the two-dimensional representations. So that was this E representation. And I only wrote down, okay, this E representation. And here we have 2 degrees of freedom, 2 complex degrees of freedom that describes our superconducting state. And so we can, in principle, get multiple different linear combinations of those 2 degrees of freedom inside the ordered state. And in practice, from this, you can show using Ginzburg-Landau theory, there's only 2 possibilities. You get a chiral state, which is like this z hat kx plus I ky. So this carries angular momentum L equals 1. Or you can get a nematic state where you have a separate condensate in kx or a separate condensate in ky. And the same thing can happen in the even parity case, where you can get this kz, kx forms your basis. You can get a broken time reversal state, which is chiral. You pick up this factor of I, and again, you can see this carries angular momentum. Or you can get the nematic states, kz, kx. And later, I'll talk a little bit about this state here. Okay. Okay, so that gives you a feeling for the normal state Hamiltonian and for the pairing Hamiltonian, the delta of K. And so now I want to start moving towards low energy excitations. And one thing you can see, maybe I'll just go back a slide. One thing you can see in this D wave case is that it looks like you have zeros when Kx equals Ky. And these zeros in the single band picture are going to be the zeros of our quasi-particle excitation spectrum. So when Kx equals Ky, this has a 0, and we can ask, well, is this a function of the fact that we chose this sort of simplified form of the D wave order parameter, or is it a general property of the symmetry definition of this gap? And you can actually show it is a general property of the symmetry definition of the gap. And so here again, this is the representation for this D wave gap, which I've written down as an example as kx squared minus ky squared. And now what I'm going to do is I'm going to apply a transformation, this C2 prime transformation. So in the square, that's this diagonal twofold rotation. So it's going to go diagonally across the square, and then I'm going to carry out a twofold rotation around that axis. Okay. And so what that does is if we set kz to 0, then we have kx and ky. Its interchanges kx and ky. And so I apply that transformation. Psi kx ky goes to psi ky kx. But then by definition, I have to pick up this minus sign. So it should be minus psi of kx ky. And so now if I set kx and ky equal, then I have the situation that psi of kk equals minus psi of kk, and therefore psi of kk is 0. So this 0 is a consequence of this definition of the order parameter, and it has to be reflected in this choice, but it's true for any D wave state. And quite generically, so here you see this vanishes when kx equals ky, and I didn't put kz here, but it's true for all kz. And so this vanishes on a line in momentum space, or a plane, sorry, in momentum space. And in general, the symmetry imposed nodes will mean that we have gaps that vanish on planes. Well, not gaps, but these order parameters that vanish on planes or lines in momentum space. Okay, so I'm going to use that a little bit later. Okay, so that told us about where zeros in these gap functions come from. And so now we're ready to talk about the excitation spectrum. But one more detail before that. Okay. Yeah, one more detail before that. So in the single band limit, okay, we have, okay, so you've seen this before. This is a repeat of everything. But in this Hamiltonian, we have a built-in symmetry, which is charge conjugation symmetry. And that charge conjugation symmetry in this particular case says we can transform h of k by this charge conjugation symmetry, and we pick up this minus h of minus k. And so the form of this charge conjugation symmetry is the complex conjugation operator times tau x. And this tau x is just 0, 1, 1, 0 in the particle hole space. And so what I'm going to show you is the mechanics of how this actually is a symmetry. And I'll just do that on the blackboard. Yeah. Okay. Because any theory of superconductivity has to include this symmetry, right? Okay, so this is the definition, and this is true for the whole Baudou-Bottegien Hamiltonian. And I told you C is the complex conjugation operator times tau x. And so now I'm going to write down my Hamiltonian in a simplified form. So this is for the single band case, and I've dropped some Pauli matrices here just to make our life a little bit easier, and I've assumed epsilon k is epsilon of minus k. And so now I can just apply this tau x to this matrix. I can compute tau x hk star tau x. When you do that, and you can just check this. Yeah, again, the complex conjugation operator takes the complex conjugate of k, and in addition, the inverse of tau x is tau x itself. So that's why tau x shows up. And this thing must be equal to h of minus k. And so here's h of minus k. And we can see then that for this to be a symmetry, these two things have to be equal. And so we need to satisfy delta dagger k of star equals minus delta minus k. Okay. All right, so it's not obvious that this is true, right? I just have some function here. And this is not true for any matrix delta of k, right? So first, if I take the Hermitian conjugate and then take the complex conjugate of that, what do I do to this operator, delta k? Transpose, yeah. So I get delta transpose of k must equal minus delta of minus k. And so I'm going to ask you, where do you think this comes from? What is the origin of this constraint? Yeah, I've heard. So it's the Pauli exclusion principle. So this is exactly the Pauli exclusion principle. And so this charge conjugation symmetry in this case is true because we have to satisfy the Pauli exclusion principle. We're going to see this charge conjugation operator come up. In other cases, it's going to be this, but then times some other identity matrix may be in a larger space.
Is this
Okay, so that's charge conjugation symmetry, which we'll talk about later.
modified if if Q is non-zero?
Sorry, what was that?
Would this hold if Q is non-zero?
I have to think about that, and I haven't, it's a good question.
But it showed up with the same sign in the. I don't know what's wrong.
Let me, good, yeah, I'll come back to you on that. Okay, so I've introduced three symmetries that are important: time reversal inversion and charge conjugation, and those will show up later. Okay, and now we're going after the low energy excitation spectrum. And so the easiest way to get that is we can write down our, again, even parity, oops, it's the same slide. We can take our BDG Hamiltonian and we can just square it. If you square it, you find that you get epsilon k minus mu all squared plus psi of k squared. And so the zeros of this will be the zeros of our quasi-particle excitation spectrum. You can also do it for the, this is for the even parity case. You can also do it for the odd parity case. And when you square the BDG Hamiltonian, you get this. And let me just show you quickly where that comes from. Okay, so here's our BDG Hamiltonian for the odd parity case. And the main reason I'm putting this in is so that you guys don't make a common mistake. Okay, so here's our BDG Hamiltonian, and here I've explicitly taken the Hermitian conjugate of this part. And here the I sigma y sits to the left, while here it's sat to the right. So now you can square this. And you guys can just quickly check this. And so that's the square of the BDG Hamiltonian. I forgot a sigma 0 here. And then this is just going to give us +1. And so the only thing that we have to worry about is this d dot sigma, d star dot sigma. And here, using properties of polymatrices, you can show that this is indeed d dot d star plus I d cos d star dot sigma. Okay. Yeah.
So 1 component of the BDG Hamiltonian.
The 1 component.
Yeah, like what do
Oh,
you?
this is epsilon polymatrix sigma 0.
Oh, thank you.
Yep. Thank you. Yeah, and I should. Okay, I may as well make this complete. Put a tau 0 here. Okay. Okay, so throughout this talk, this is called the non-unitary part of the gap. And in practice, there aren't many good examples where this really does show up. And so I'm going to ignore it throughout, I think, all of this. So we're going to ignore this non-unitary part. And then when we have that done, we have essentially the same kind of spectrum for both the even parity and the odd parity case. Yeah?
Does it apply to Umklapp scattering?
The non-unitary part? Well, okay. To get a non-unitary state, you often need to go outside of weak coupling theories. And so you need interactions typically that are strong. Yeah.
Why the terminology? Why is it called unitary versus unitary?
This is dating back, I think, to helium physics. And I don't know why they call it the non-unitary part. And it's a strange, but it is what it's called. And you see it in the literature. So it's a good question.
Second quantization?
To be honest, it could be, but then you have to link it to that explicitly and show what is exactly non-unitary. And that takes a little.
The sound? second sound.
Yeah, maybe, I don't know, but okay. It is called that, and you see it used in the literature quite a bit. But now the even parity and the odd parity spectra look very similar. Here we have psi of k squared, and this is d of k squared, but this is dx squared plus dy squared plus dz squared. So there's three components here, a single component here. Okay. All right, now for reasons that look very obscure, I'm now going to go and rederive this spectrum in a very different way. And it looks like I'm just having fun with mathematics here. But I'm going to do this for the even parity case. And it's going to turn out that this is going to be relevant later in the context of topological invariance for certain states. Okay. So that's why I'm doing it, but it looks like I'm just having fun. All right. So if we have an even parity gap function, then it turns out that we have a symmetry which is charge conjugation times inversion. And actually, before I talk about that, I think I will talk about inversion symmetry first a little bit. Yeah, so that's the wrong inversion. Yeah, okay. All right, so I've already told you what the charge conjugation operator is, and I've treated this somewhat differently than I've treated the inversion operator. I told you what the charge conjugation operator is in particle hole space, but the inversion operator, I've only told you how it operates on the single particle Hamiltonian. I haven't extended this operator to the particle hole space. And so when I want to talk about inversion in that context is in this particular I want to talk about it in that context now. How do we take the inversion operator we had from the single particle Hamiltonian and extend it to the full BDG Hamiltonian? All right, so before I told you that inversion was this. And then in the BDG Hamiltonian, let me see if I have a good example. We want to understand, so we understand how inversion operates here. We also want to understand how it operates on this part. And so that part came from HN transpose of minus K, but we're mainly worried about the transpose in that. So we know how it operates on HN. We want to ask how it operates on HN transpose, and we're worried about the transpose. But to get that, we can just take the transpose of this expression here, right? So we can take UI, HN, UI star, transpose, and that is equal HN minus K transpose. And so here I get UI star, HN transpose, UI transpose. But this suggests that UI is replaced by UI star when operating on that lower block. And so naively, we would say taking our normal state Hamiltonian symmetry operator and extending it to the BDG space, we would say this is our BDG inversion operator. Okay. But we have a nice feature of inversion. Inversion squared is the identity. And because the inversion squared is the identity, its eigenvalues are plus or minus 1. That means we can choose the inversion operator UI to be real. And if we can choose it to be real, then this simply becomes 0, 0 UI. Okay. So this is our guess for what the inversion operator is. But this actually only works for even parity gap functions. Okay. Yeah, so I have to define even parity better. So if our gap function is even parity, then this is a symmetry of our system. For odd parity, we have a small complication, and this will show up. So under odd parity, for the single band case, we pick up this minus sign. And then you can ask, what is the inversion operator in this case? So what operator can we say U tilde H BDG, U tilde complex conjugate is H BDG of minus K. Right, so we apply the inversion operator. Well, it turns out in that case, our BDG Hamiltonian is UI tau z, where tau z is in particle hole space. Okay. And there's a physical reason for that. We have this minus sign, so in the superconducting state, inversion is not a symmetry by itself, right? Because part of the gap changes sign. But what we can do to compensate for this is we can use the fact that we have a gauge degree of freedom in our superconducting state, and we can multiply the superconducting order parameter by a pi gauge shift. And that pi gauge shift is what's showing up in this TZ operator. So you can explicitly check this yourselves and see that this works. But the main message is here is we can extend these operators to the BDG space, but sometimes that extension isn't what you might naively guess. For the even parity case, it's this, but for the odd parity case, it's this. All right. Okay, so let me then go back to, that's the wrong direction. The more complicated derivation of the spectrum. All right, so for even parity cases, I have an inversion operator, which you know how to write down, and we have a charge conjugation operator, which we know how to write down. And you can even do this for larger spaces, but we can write this symmetry as some unitary part times the complex conjugation operator, because charge conjugation is anti-unitary. All right, and so by definition, this is almost like the charge conjugation operator, but we've also applied inversion. So the charge conjugation operator took it to minus h of minus k. Inversion makes this back to k again itself. All right, so we have this constraint, and the important property is you can check explicitly that charge conjugation times inversion squares to 1. And this is true beyond the single band limit. It's true for any superconducting state that is inversion symmetric. And because of that, we can, in effect, diagonalize this operator, and we can show its diagonal elements are phase factors of modulus 1. So e to the I theta along the different thetas along the diagonal. And we can exploit that and unitarily transform our BDG Hamiltonian to a new basis in which we use where we explicitly use this diagonal form for this. And we can show in that basis, we can always find a transformation where the transpose of the BDG Hamiltonian is minus h of the BDG Hamiltonian. So the transpose takes h to minus h. So this is now an anti-symmetric matrix. And if we have an anti-symmetric matrix, you can define a Pfaffian for it. I mean, you may not be familiar with the Pfaffian, but it's true for any anti-symmetric matrix. But the way you can find the Pfaffian in the easiest way is you can realize that, or by definition, the Pfaffian squared is the determinant of the Hamiltonian. And so loosely speaking, you take the square root of the determinant of the Hamiltonian. And in our case, that is this object here. So zeros of the Pfaffian are also zeros of the BDG Hamiltonian, so there's zero energy spectra. So this looks like a very convoluted way to get zeros, but the only reason I do it is because we're going to see this Pfaffian again later on, okay? And you'll see where it comes from, and like I said, it's linked to topology. Okay.
Square root.
Sorry?
The formula in a box, does it need square root?
No. So it's, yeah, I have a tau 0 multiplying the square of my BDG Hamiltonian. And so I have, so I have 4 eigenstates. And so hence 4 eigenvector values. And so hence the square root takes that square away. But, okay. All right. So this is again a rederivation for the spin singlet case. But now let's look at the zeros. Okay. So To get a zero, we need this term and this term both to vanish, right? This term just tells us that our momentum must be on the Fermi surface. So once we have a Fermi surface, we've taken care of this. This term tells us our psi of k must vanish as well for certain on the Fermi surface as well. And I already told you that this psi of k vanishes either on lines in momentum space, or sorry, psi of k vanishes on a line. Then we have a line that intersects the surface, and a line intersects the surface at points. And so we get point zeros in this dispersion, so those are point notes. And if psi of k vanishes on a plane in momentum space, that intersects the surface along a line. So that gives us line notes. So we get point notes and line notes, and you can see from this that generically we expect either fully gapped states, point notes, or line notes. And a very similar argument will apply to the spin triplet case, but we're going to talk about it in more detail later. I mean, the same form shows up. Something squared plus something squared equals 0. And so this is the Fermi surface, and then this term has to vanish as well. Okay. So that's our conclusion from the single band theory. We have 3 possible types of nodal excitations, and that's fully gapped point notes or line notes. And just to drive the point home and to show you a specific example, here I'm considering something that applies to the heavy fermion material uranium, ruthenium-2, silicon-2. All right, so here's our dispersion. So we have epsilon k squared. So we have to sit on the Fermi surface. So let's just assume we have a spherical 3D Fermi surface. So that satisfies that constraint. And now I'm going to consider a gap function, which is this kz, kx plus I, ky. So this is chiral gap function I showed you before. All right, this breaks time reversal symmetry, and that's going to be important a little bit later on. But I can take the magnitude of this, and so the magnitude that gives me kz squared and kx squared plus ky squared. All right, so this magnitude vanishes in the plane where kz is 0. That plane intersects the spherical Fermi surface on a line. And so I expect from this to have a line node on the equator. But I also get a vanishing when kx squared plus ky squared equals 0. So that's the kz axis. So along the whole kz axis, this vanishes. And again, that line intersects the spherical Fermi surface on points. So I expect to get 2 points as well. All right, we know a little bit more about these. It turns out these 2 points are Weil points, meaning we can associate with this a particular topological charge, which is related to a Chern number. And because of that, these Weil points have opposite sign +2 and -2. And that means when we look at the surface, we get 0 energy Fermi arcs on the surface. You can ask, does this line node also create boundary states at the Fermi at the sample edges? And the answer is no. And it turns out that's because inversion plays a role in stabilizing the state, which I'm not going into here. But that inversion is broken at the interface. And so the symmetry is broken at the interface. We can't expect to see the topological protections survive to an interface. Okay, so that's the single band theory. You have some idea of the symmetries in the BDG Hamiltonian for that. You understand when we get 0 energy excitations. And so now I'm in a position to tell you what your first homework problem is. All right, so this homework problem is actually motivated by a physical material. So it's motivated by the appearance of magnetic order in a superconducting state. So this is the so this is the particular material. And there's a group at Brookhaven National Labs who've been probing the low energy quasi-particle states of this. Well, what matters is you have here, well, this is some iron arsenic bilayer. And it turns out you have 4 of these iron arsenic bilayers with these europium magnetic, you have europium moments in these green planes here. And what happens is as you go along the c-axis, it rotates by 90 degrees 4 times. And so it gets this 4-fold periodicity along the c-axis. And here I've only taken half of that here. This magnetic state orders at 15 Kelvin, but the superconductivity happens at 37 Kelvin. So you can look at the superconducting quasi-particle spectra and see what happens. Well, not directly, you look at STM, but you can see what happens as you go into this magnetic state. okay? And the important point is, if we just look at two of these, we can see that this magnetic state breaks a few symmetries on this particular bilayer. And I'll point out this is the inversion center in this material. So without magnetic order, there would be an inversion center here, and these two layers would be related by this inversion. So we can break up, this is a moment along X and a moment along Y. We can break that into one moment along X plus Y, which are both pointing the same way. And another moment where in one case we point along 90 degrees rotated from that, and then in this direction here. Okay, so this turns out to be, this is opposite to this. And you can just add these up and you can see you get this spin, and you can add these up and you can see you get this spin. Okay, maybe you have to look at the pictures carefully. But the point is, it's a combination of a ferromagnetic part and an antiferromagnetic part. Now, ferromagnetism breaks time reversal symmetry. And so we're going to be asking what happens to our BDG Hamiltonian when we break time reversal symmetry. And that's just going to be something like a Zeeman magnetic field. But now when we look at this antiferromagnetic part, it has an interesting property. The inversion center's here. So this thing is odd under inversion. The two moments flip, right? So they go from plus to minus. But it's also odd under time reversal. These two moments flip, and so as well. And that means the symmetry of this is time reversal times inversion symmetry. So if we only consider this particular part of the order, and we consider a normal state Hamiltonian, what can we say about it that we know that it has this time reversal times inversion for a single band? So what do we know when we have time reversal times inversion for a normal state Hamiltonian? I think I heard it. We have a twofold degeneracy, which is pseudospin. So we have this pseudospin, but we've broken individually time reversal and inversion. All right, so one of the questions will be, how does the Hamiltonian change from when we have both time reversal and inversion present to when we only have time reversal times inversion present? How does that spectrum look different? All right, and then what are the consequences of breaking this magnetic order and this symmetry and this symmetry? All right, so here's the detailed question. It looks kind of long. But I wanted to be explicit. Okay, so here I'm going through it. I've told you we have time reversal times inversion, but it doesn't have these two symmetries. And so this is still valid. And so this is what I just asked you. How does this change from what we had before? And then I'm going to say label that change by this epsilon minus of K. All right. And then I want you to find the quasi-particle spectrum for a single band case in the presence of this epsilon minus of K. And then we're going to do this for a purely spin singlet or a purely spin triplet. Formally, you can mix singlet and triplet here, but we're not going to mix them. And then, even though this looks a little bit different, we're going to add that finite momentum. We're going to turn off this term here. We're getting the spectrum in that case as well. And then finally, you're going to examine a D wave gap. You're going to add this finite momentum, and you're going to see what does the quasi-particle excitation spectrum look like, especially around the nodes of the D wave gap. And then finally, for an even parity case, you're going to also add a Zeeman field and see what the quasi-particle excitation spectrum is there. So now you're breaking all the symmetries I've added before. And surprisingly, you can actually get the full quasi-particle spectrum exactly here. Okay. All right. So that's our first homework question. And now I've given you kind of the late 1980s, early 1990s viewpoint of superconductivity from a single band point of view. And then we can start to ask, does this really describe everything we see in low energy quasi-particles? And the first thing I want to point out is that we have YBCO, and that's a cuprate, but it's not tetragonal. It breaks the fourfold symmetry. And so we can say, well, if it breaks the fourfold symmetry, we don't have this symmetry, but also we break this symmetry here. So from a symmetry perspective, every element is one. And so in this case here, we can't have a symmetry argument that guarantees us nodes like we had before. Yet, we see nodes. But these nodes are not dictated by symmetry anymore. They're dictated by something else. And so what we want to understand is, what is that something else? And I already showed you a picture of that as well. Here's this iron-based superconductor. This has nodes in it as well. You can kind of see them right here and here. These nodes are not dictated by symmetry. So our understanding of nodes is in this sense incomplete, and we want to understand where they come from. Okay. So these are often called accidental nodes. Okay, so that's one point that is different than how we understand our classification. And then there's another example, which is, I think, very interesting, especially currently. All right, so there's a high TC iron-based superconductor. You can see, well, here they say TC is extremely high, on the order of 100 Kelvin, but maybe it's more like 60 Kelvin, but still very high. It has the highest TC in all the iron-based superconductors. And we'll get into this in some detail later. But when you look at the monolayer FESE and you look at its Fermi surface, which I'm showing here, you find that it has a pair of pockets located around the corner of the Bruin zone, the endpoint. So one pocket like this and one pocket like this. And if you do ARPES in the superconducting state and you just look at, say, this particular pocket, you see that the gap everywhere is non-zero. Okay. Now, we believe that iron-based superconductors are all driven by correlations. And so because we're driven by correlations, oh, sorry, you gave me some. Okay, thanks. Because we're driven by correlations, we expect that there should be sign changes in our superconducting gap. So electron phonon gives us always the same size gap everywhere, typically. Maybe there's some exceptions to that, but that is the typical case. But here, because we're driven by electron-electron interactions, we expect to see sign changes. And so the natural way to see a sign change is to say, well, on one band, I put a plus gap. On the other band, I put a minus gap. Okay? And it turns out, okay, it's not easy to find the details for this, but there is experimental data that strongly supports this kind of gap structure. All right, now, if you examine this in detail, you can convince yourself this is actually a D wave gap. So if I do a 90-degree rotation around this point, the blue switches to red, I get a sign change. So I go back to this table, I pick up -1s, and formally I have a D wave gap function. And so you can ask, well, there's a problem. If I have a D wave gap function, I've argued before that we should get nodes, and we should get zeros in the quasi-particle excitation spectrum. But in that direction where we should get the nodes, which is here, there's a finite gap. So where did the nodes go? Why are there no nodes here? And so here, we're going to talk about this later on. We're going to answer this question, and it's going to be very closely related to the fact that we have two Fermi surfaces, and so we have not just pseudospin degrees of freedom, but an additional pair of degrees of freedom that can get us around these nodes. Okay. Okay, then a couple other things that are sort of well known in the literature. Now I'm turning to odd parity superconductors. So in odd parity superconductors, we know that we have to pick up a minus sign as k goes to -k. Okay. And so that means that if we put ourselves at half a reciprocal lattice vector, so that k and -k are the same point, then we must have the case that this gap vanishes. And so we often hear, and this was used a lot in the context of strontium ruthenate, that the zone boundary, an odd parity gap must vanish. We're going to see examples where this is violated. And I'll tell you when that happens. And then we also talked about the spectrum of the spin triplet case. Okay. There's the same paper in which this alternate form of the BDG Hamiltonian was introduced. It was also pointed out that in spin triplet case, no line nodes are possible, and we're going to revisit that in some detail. And the conclusion is that you can either only have a fully gapped state or have point nodes. And this is known as Blount's theorem. So for odd parity superconductivity, if you have spin orbit coupling, you can only have point nodes or have something fully gapped. But it turns out that in context of uranium platinum 3, there was a paper by Mike Norman where he showed that you actually have line nodes in this odd parity superconducting state. And this happens on the momentum plane kz pi over c. And so we're also going to understand where that comes from. And many of these things I'm talking about come from the fact that we have more degrees of freedom in our superconducting gap. The only thing that doesn't really come from that is the first thing I pointed out, and that's nodes coming from beyond symmetry. Okay. All right, so you can see where this is going. How am I doing for time?
5 minutes.
5 minutes? Okay, I was hoping to get to the end of this today, so I'm not too far off, but you can at least begin to see where this is going. All right, so the answer to the fact that we have nodes that don't come from symmetry actually is buried in topology. So these nodes are driven by topology, not by symmetry. Symmetry does play some role. And so I'm not going to go into a lot of details into the homotopic classification of nodes, but there's a standard process to doing this. First, we have to identify relevant symmetries. And I've already pointed out the symmetries we're going to use. We're going to use time reversal, inversion, and charge conjugation, because time reversal and inversion guarantee us a superconducting state, at least in the weak coupling limit, and charge conjugation is always there. So we're going to focus on those symmetries. And then once we have certain symmetries for BDG Hamiltonian, we then can use codimension arguments to identify what kind of nodes are allowed within that BDG Hamiltonian. Okay, so we're going to have some symmetries present, but they're only going to be time reversal, inversion, and charge conjugation. And we're going to find out that you can get nodes in those cases. And then you can do a homotopic classification, which we're not going to do, but you can then classify what kind of topological protection those nodes have. And again, I'm just going to tell you the answers and tell you the implications of that. All right, and then once you do that classification, you can go through the harder step of identifying topological invariants associated with these nodes. So just to give you a picture, maybe we have some line node, and then we can define some circle around that node. And if we integrate the appropriate quantity around the circle, we can show that that is topologically quantized, and that topological quantization protects this line node. And the same thing for, okay, a point node isn't here, but that's what happens. And so what we can imagine is we're mapping K to a space of Hamiltonians H of K. So this gives us a series of maps. We can examine the space of Hamiltonians, and we can look at the homotopy groups of those Hamiltonians. And those homotopy groups tells us what kind of nodes are allowed and what are their topological protection. And as I said, I'm skipping this part. I'm just saying it can be done. Okay. All right. Maybe this is probably a good place to stop for today, and before we jump into the details of that classification and see how to use it. I'll stop there and open this to questions.
All right, yeah. Hope you guys have any questions. Yeah, go for it.
You charge operators,
Sorry, what was that?
fractional charge operators, is that?
Yeah, that's here. Everything's an electron.
Give the question for recording.
Oh,
Can you repeat them?
Okay, yes, yeah. So the question is, do we have fractional charge operators, and can you talk about that? I mean, in principle, you can, but I'm not going to talk about that at all.
When you were looking at the time reversal and inversion symmetries applying on the normal state, you said that the inversion symmetry does not affect the spin degree of freedom.
That's right. Yes.
But then we were looking at the homework problem, and you said that in one of the cases where we had an antiferromagnet, you said the inversion symmetry is broken because the local moment points in opposite directions. I can't connect the two.
Okay, so yeah, let me repeat the question. Yeah. Okay, so I pointed out that inversion symmetry operates trivially on spin, but then I gave a homework question where there is a structure that breaks inversion symmetry, but actually it breaks inversion symmetry. So inversion is not a symmetry, so that's one thing to take into account there. But the structure still preserves time reversal times inversion symmetry. And so in the so that's partially the answer to your question. Something can still happen to the spin degree of freedom now between K and minus K, because the inversion symmetry is not actually there. But we still have this condition that we have time reversal times inversion at the K point. And so you're actually starting to answer the question.
Are there some ingredients or some examples where electron phonon, the main instability of electron phonon is not an S wave? Not because you have additional electron-electron interactions, but itself from electron phonon
So the main instability, no, I think you can, I've seen a proof which shows that if you have electron phonon, then you can show that the lowest energy state, at least within a weak coupling approach, is isotropic. However, and I'm sure we have people who can answer this, can say more details, but electron phonon can give you subleading pair instabilities that are attractive, and that may show up in places. But I think the answer to your question is no, and maybe I'm wrong. Maybe I've missed some example, but.
There.
So far, all these Hamiltonians are essentially quadratic. So from a point of view of interacting theory, they have to be understood as a mean field.
Yes.
Is there any argument that would allow to carry all of these arguments to interacting level theories?
You can. So certainly we can derive interacting Hamiltonians using the same approach. And then, so in that sense, yes, but I chose not to do that here because it just adds another layer and we won't get anywhere. But you're wondering, what if we have something beyond mean field theory? So suppose we have phase fluctuations, right? So that's beyond mean field theory, and we have to include that. You can then use these Hamiltonians and start building around that to see. And so the symmetry properties will still be there in the mean field Hamiltonian, but you can now allow fluctuations around that mean field and get interactions involved in that way. Does that answer your question to any degree, or? Somewhat. I mean, so the classifications I'm doing, like the topology and the labeling of states, is all using a single band picture. But you'll hear a little bit later what happens when you add interactions, where do we have to worry about corrections beyond the single band picture, et cetera. So you'll get things like lifetimes. I don't know if this is what you're asking about as well.
It's just not clear how I'm going to use the infinite homotopy theory to classify all of this if I don't have a quadratic Hamiltonian, because infinite homotopy is essentially classification of matrices of different sizes, topological classifications of maps of matrices of different sizes. And if your Hamiltonian is not quadratic, how do you preserve any knowledge about this classification in an interactive theory?
Okay. Yeah, what was the term you started with? Infinite what?
The classification that.
Well, how is it going to last beyond when we go to larger spaces or something like this? Okay, maybe we can talk about it some more. Yeah. Okay.
Yeah, I think I saw in the back over there.
I have a question regarding the setup of the homework problem. Let's say if it was some helical order, you could still looking at two neighboring, like let's say helical order with like different periodicity, let's say 6-layer, 60-degree helix. You can still, if looking at the two nearest neighbor layers, can separate into ferromagnetic plus antiferromagnetic part. But would you correctly get that, like if we neglect anything about spatial symmetry, do we get the correct gap form?
Okay, so let me be sure I understand your question. So you're referring. That's the wrong direction. You're referring to the picture I showed you of the magnetic order, right? Yeah. And now you're asking, what if it was a longer wavelength type of magnetic instability? And then you want to know, and so here I use this to justify the homework question, and that's what it was for, just to justify the homework question, and to show you it applies to something physical. But you want to know now what we can say about the gap structure in these cases. Is that right?
Let's say periodicity of the spatial structure.
Okay, I see. So in principle, yes. So you're saying we have some uniform component of the gap, and now we've broken the periodicity of the lattice, and so we now have some new lattice periodicity. Indeed, in principle, the gap should reflect that. But there's also other properties of the gap, which I hinted at the homework, which is probably, I mean, I imagine this will not be a big effect, to be honest. It will be there, but it may not be such a big effect. But I told you, don't allow for mixing between singlet and triplet Here, the broken symmetries generically imply that even if we don't worry about that inhomogeneity, you will have mixing between singlet and triplet gaps. So that's a consequence of the fact that we don't have inversion symmetry anymore. Once we don't have inversion symmetry, we don't have this classification where we can break it up into two structures. So that's more than answering your question, but it lets you see something about how the gap structures do evolve because of this symmetry breaking.
Yeah, over here.
I have a question about the material called YPCO, and you mentioned it on the PowerPoint.
Yeah.
And so you said that this material breaks some symmetry here.
Yeah.
But it still have the superconductivity properties.
Yeah, and it still has zero energy nodes. Yeah.
So can we just break and not other symmetries and keep the superconductivity?
Yeah, so in weak coupling theory, you need to maintain either time reversal or inversion symmetry to be guaranteed to have instability into the superconducting state. This is true in 3 dimensions. In 2 dimensions, there's additional symmetries that let you do this, but I decided not to talk about that here. And so as long as we have those symmetries, you can have a superconducting instability. But what I mean here really specifically is I said that this is what guarantees us zeros in this definition of the gap under these rotations guarantees us our zeros. But now if I break the orthorhombic symmetry, then these 2 minus signs are gone. And under any symmetry transformation, I just pick up a factor of 1. And so from that perspective, I have nothing to guarantee me any zeros in the superconducting order parameter or the gap. And so these are the symmetries broken by the orthorhombicity. And so I have no reason to expect nodes anymore. Yet nevertheless, we have nodes.
Thank you.
You had your hand up a while ago, so I'll let you.
I have a question regarding your charge conjugation. If charge conjugation leads to the Pauli exclusion principle, why do you need this separately?
It is the Pauli exclusion principle. So it's a symmetry that's guaranteed in our BDG Hamiltonian because of Pauli exclusion. Yeah, but it's reflected in the BDG Hamiltonian as this symmetry, and we know we have to obey Pauli exclusion.
By construction, we have this Pauli exclusion in all the.
Yeah, but I've written down some general form with some matrix delta of K, and we have to implement it. And only if we have Pauli exclusion do we have this charge conjugation symmetry. So if we're doing any analysis of a general form of Hamiltonians, we should assume we have charge conjugation symmetry built into that analysis.
Andrey.
Yeah, maybe you misspoke or maybe I missed it. This is a good slide to ask a question. There are accidental nodes.
Yeah.
Are you saying that there is some topology associated with accidental nodes?
Yes. Yeah.
But then simplest example like this.
Yeah.
I take a minus state.
Yeah.
And S state in a tetragonal system can have cosine for theta term.
Yeah.
As a subleading term.
Yeah.
Suppose the coefficient becomes larger than 1.
Yeah.
Is it really topological transition in this situation?
It's not a topological transition. Well, so the answer to this is yes. We can identify a symmetry that protects the nodes even when you add this cosine for theta term.
The nodes are due to this cosine for theta term. When it becomes larger than 1, if it becomes larger than 1, I start generating accidental nodes.
And so you can actually understand that from a topological point of view. And this is actually even some work you've looked at. If you look in the fully gapped state, you'll find that you have no nodes. But then once you go across that critical value of the cosine for theta term, you'll find that you create a positive negative node pair. And that positive negative node pair, we can classify each of those nodes according to a topological quantum number, which is this chiral number I was coming from time reversal times charge conjugation. So you can give it a topological charge and you can say it's protected. I mean, you're giving a mechanism.
Protection, what protection means here? I change parameter.
Okay,
and
that's
go from nodal to no nodal state.
Yeah. So protection means that you can assign a topological charge to the node. That's it, right? And so you do go from a nodal to a non-nodal state, but you have, but you still have the same total topological sum of charges. So it's 0 in both cases, but now you have plus and minuses spread out.
As long as those two nodes are not being annihilated.
Exactly.
That's what you claim is stability, right?
Yeah. So yeah, exactly.
We just have a different definition of protected. It's not non-zero measure of existence. Because if you say
Okay.
nodes exist only a zero measure combination because of the special symmetry, you deviate just a little bit, it goes away. No,
Yeah.
it has finite range.
Yeah, so when we do the topological classification, we'll use codimension arguments, which says exactly that. We have this many parameters in the theory, and then some have to vanish, and we can say, we can vary those parameters, but the nodes still exist.
Okay, so I think we're a little bit over time, so if you have more questions, feel free to discuss during the break, but for now, we're gonna be on a quick break, and we'll be back here around 11. Okay?
Actually, helping them write the solution manual for that. Yeah. Either chapters, I am writing. I mean, chapters on expressions and also a few chapters
My brother's email, that's the only reason we went.
Yeah, I was struck where you are.
So that's a great
Respond to anything.
No, it's not. Yeah, they're from the succession. Everything we do is need to and perspective first. Well, meaning that the stuff how you go has experimental.
Is he here in the US or?
How do you go this
Yeah, I'm Andrea.
I'm grateful.
Hi again.
So good.
Yes, I remember we're sitting at a bar together. Yeah. Good to see you again.
How you doing?
All right, just carrying on for work.
So there's a place where this is called.
Interesting opportunity to learn about superconductors. So I thought, why not? Let me take this. Yeah, you're part of the US.
Even the last year is still sitting there.
Where are you from originally?
South Africa. Yeah. You're from the US?
So yeah, originally from Chicago.
Ah, okay.
Experience.
That's actually not too far from you.
That's another way.
Energy.
Get back to the Midwest.
And then you can
Sure.
take self-energy and then you can
It gets
study
super cold here.
and show that it has a.
That'd be visiting the sun stuff.
The assumption for the self
Are you gonna present a poster?
Oh yeah, I'm not presenting on Thursday.
Okay,
And
nice.
then
I'm
it's-
presenting tomorrow.
Oh, that's how we presented them.
Maduranos and
Yeah, yeah,
displays all like
Oh, that's.
Yeah, that's the hard part.
modifying their setups.
Yes.
Used to realize my drum with 1D wire approximatized superconductor, if you're familiar with that. Yeah. And replacing the magnetic field that's usually used with an altamagnet. And then letting the implications.
So then. Okay.
So yeah, happy to discuss it with you.
As you say, like you're studying like it's like Rosh Pascal building.
Yeah, the wires are Rasmus.
Okay.
Yeah.
Yeah.
But in terms of the node.
Yeah.
Yeah, you can study any wave, but what we considered in this project was making planar altamagnetism. There's some subtleties that are involved in the project where it's for 3D altamagnets. But yeah, we have proximatized altamagnetism from planar, so D wave, G wave, or
That's my opinion. Actually, it's Russia like this specific form and it's kind of like that. Yeah, sure. Like all the time that y minus like is that like specific like like is that a necessary ingredient or can you have like good types of smoke coupling?
Good question. I think it's necessary, but I actually haven't thought about why, even though I've been staring at it for so long, I just took it as the gospel. But yeah, I think it's because it breaks inversion.
Exactly.
I actually haven't studied why, if I'm completely honest. I'll think about it and get back to you. I think there's probably an easy, there's an easy answer, I just haven't thought about it.
It seems like understand this more. Like I feel like a naive perspective. It seems like it's looking for like out of plane open magnet. Like
You can do in plane or out of plane, so spin orbit coupling has nothing to do. Actually, you're absolutely right, yes. So you can do it with in-plane ultimax, but it still needs to have a component perpendicular to the spin orbit coupling. For this to work.
basically like non-managed mapping. If you look at the string numbers and.
In a sense of.
Yeah,
I haven't even.
So
Don't even just like research.
there is a line up for
Easy winding here actually.
So you can, that's.
Those are.
When I say strong electron
Actually
attraction,
years ago.
I mean non-electron. That's my main message.
Yeah, but yeah, we can definitely.
So we expect, pairing interactions at the field level takes contribution to both.
Right.
And then there's something on electron, which we want.
That's what you.
That's what I refer about it.
How about you? What's your? I mean, I'll ask you obviously more to process it.
Oh, yeah.
But just like the.
Yeah, I will talk.
Oh, yeah. The punchline is, so usually when you study like, for example, like the blend down theory, roughly like terms and bulk term, there's kind of like a specific, like kind of symmetry, like classifications of term as a graded term. Okay. Kind of corresponds to.
Yeah, I mean.
Okay.
And so usually like the BCG not the symmetry, but PD is same way.
Yeah, that makes it probably, but then if we're classifying Hamiltonians.
How easy it
We
is.
should
like,
make sure we have that symmetry.
It's usually like we're talking about like very rigid one, and mentioned like baseball coherent. It's hard because homogeneous pairing order. Or if it's if there's no longer like if it's a super smooth stiffness to get out.
Definition of a chart.
Basically you want things to go out so like rotate more like.
Okay, so.
And I told you that.
So the
conjugation.
perfect rigidity is like perfect.
Clock crater time.
That another way.
It kind of makes if you're like.
So what I did was a TDG.
That's the easy plane act.
I looked at.
How easy it is. Like.
Epsilon sigma 0.
It's like in our project, we basically, so that's usually. in
Yeah,
the context
so
of
then
spin
I said that
like unitary.
This has an equal.
Like, we're looking at a spin triplet.
So then
kind of like have a non-dimensional.
I only looked at.
It would show that there's for example, like kind of like
I
a
remember
Maria
you
type,
got-
prosody star term. So we're.
Yes, like a spin orbit coupling.
They're like, kind of a little bit, but like.
Yeah, so.
And it's like, but basically right now, like, most energy configuration is not like a rigid, like a genius like pairing order parameter, but rather one that actually is a spatial variations, like in EDWs, like vortices, even absence of magnetic field.
Oh, I see. Okay, nice. So I'll ask you more about it.
See, what does it mean to flip these two? So you're flipping N prime, so that's the transpose, you're taking sine of K.
You're getting the advantage
So
because
this,
the up early, funny if you're looking at it.
this.
Oh, and then I'll just walk up, take off the glasses and.
It's kind of like a sword. So it's like three semesters up. I'll go with the one that's not in there.
I made those diagrams. Initially, you see those like. So initially I had those.
On the side, but.
You can still find something.
Just learning blend and
You
making.
can implement it,
Making
but you're not
a
gonna
first class like.
Yeah, that's why, yes, so I didn't see the answer when I.
Yeah.
We basically, it's.
It's
200 is. Yeah, that's exactly that. Also, the reaction exchange, in terms of relabel points. Exactly.
What do you? 6Z, which is like diagrams in the back.
Oh, yeah. Oh, nice.
Yeah.
Right, when.
I think I saw you before.
Man, Jesse, right? Hold on a second.
Oh, yeah, I think so, yeah.
Right.
Yeah. Are you still at UCLA?
Yeah.
Oh, okay.
I still in work.
Yeah, most like LBL.
Oh, so you graduated?
Yeah, I graduated 2024 summer.
25 last year.
Yeah, the last August.
Oh, interesting.
And
Yeah, I remember you told me at
At
the
least
time.
this one does keep it. This one does.
yeah, but that problem, I'm not solving that problem anymore.
Yeah, totally makes sense.
These days, I'm mostly working on the quantum complexity and quantum surface stuff. I know your experiment, that's why.
Right.
That's why it is a little slow in the condensed matter side, but like it's so hard to get a job unless we do some quantum stuff in the theory.
Exactly.
That's why,
Yeah, really a slave state. There was no hot topic.
yeah, I think it will be very hot topic.
Yeah.
Yeah. Oh, I think I remember. Oh, now I see. I see you change your hairstyle or whatever.
Oh, yeah, no, I think glasses.
Oh, glasses.
Explain again how you got in the Agterberg.
Yeah, so-
The Agterberg.
Yeah, so what I argued was that to get, so the problem is our BDG Hamiltonian doesn't have this beta minus case symmetry. So even in the simple case, right? So even when this part is just dead end, and even that, it doesn't have this symmetry. So you can just look at your epsilon k, delta k, delta dagger k, minus epsilon minus k. And then if we apply the symmetries, you get epsilon minus k, you get delta minus k, but this thing is minus delta, so these sort of not equal.
Yes, that's because of the. Okay, I see.
Yeah, and so, but what you can do is you can compensate the minus sign coming right here by saying that our gap function gets multiplied by the pi gauge. So I just say, I'm allowed to, in principle, add a gauge factor e to the alpha pi. And then what that does is, it doesn't affect the normal state, but it switches the gap side. It changes, so the phase transformations don't affect the normal state, but they change the gap, right?
Sure, but it's actually differently in the particle whole space.
Yeah, but so I'm cheating a little bit. So I talked about this approach by Blount and Simokin, where you can classify symmetries that way. And then you can actually talk about sort of particle and time reverse particle spaces. And so you can show. For one, I should think about what you said more carefully, but for one, if, okay, it's not gonna show up on deck, but okay, let's make it, okay, let's ignore that complication. I'm saying this comes from there, but what you can do explicitly is just use this. Apply it to the BDG Hamiltonian, fix this. Okay, yeah, so that's maybe the most direct answer.
Right, it's because you overall do have inversion symmetry.
Yeah, but it's often called gauge inversion in this context.
Okay.
And the way we understand it is it's related to this minus sign to be compensated by a pi gauge.
One more thing, so I'm actually.
No, okay.
So I'm actually studying ultimately.
Okay.
First project, which I think you actually attended my APS one.
I think so, yeah.
Around us with twist.
Yeah.
Presenting a post on that now as well.
Okay.
Sorry about that. One thing we're complaining now is not between ultimates and sports. That's a pretty hot topic now. And one of the projects we're currently exploring, it seems very applicable, which is performing our gene analysis for different types of superconducting pairings in ultimates and see which ones are preferred. I was hoping to discuss that with you because you have a guide to discuss that at some point during the workshop. Because I'm wondering how practical such a project would be, because there's been a lot of mean field analysis being done for like all sorts of purposes, right? Like how much are we gonna ask our hands? Or can I give a spin on it that can really do something novel?
Yeah, I understand. And I mean, this is always, the questions you're asking, the questions we always ask, is there something new there? And I think this is. Well, what I can tell you is that there are people now applying RG approaches to alter magnetism. And right now, the emphasis is in an ultramagnetic state. What can you say about positional interactions in superconducting states? More of us is looking at questions along those lines, for sure. Yeah, so I'm saying, but it's in the literature already, so you can see what they.
I see.
Yeah. Yeah, but it's so they do find something. So they do, it's an RG treatment, and then they do find that they get a density wave state. They show it's stable if you have saddle points in the right places. But maybe, I mean, it's always discouraging if people are doing this kind of thing, but at the same time, look to see what they've done, and they give you ideas of how it's. Okay, so you can see, is there something else there? Because my instinct is there can easily be something else there, and that may be interesting. Okay, so, but you're asking the right question. I mean, if you're gonna generate a D-wave instability, okay. But if you can start to really show circumstances when there was something we have to that, that's interesting.
Okay, thank you so much, I appreciate it. Yeah, thanks for it. So, might be a bit of a value question, but it seems to be like a really strong. It's still very good stuff.
Yeah.
So I was just wondering, is there also like for the non-nodal apps?
Yeah.
There are also a couple of.
There is. I'm focusing on the nodal one because that's what I've worked on in the past. But yeah, so there is, I mean, yeah, so in the usual, like the tenfold way, charge contribution system. The natural place that shows up is. So much of topological superconductivity applies fully gas systems within the tenfold way classification. Then certain classes of that tenfold way are purely stood. On the realizations.
And so in those systems, states, are they like the same as?
Yeah, so the most common topological insulator. The goal is to make wire analysis, but that is the goal. But you can also get superconductivity blocks on top of insulator, where the interesting surroundings is.
今年已经毕业了还是可以
And you can show that the conditions under which that generically.
今年秋天开始涨，然后下个
So it's not the Majorana goal, but it is.
所以你之后打算
So you get exactly the same. Then you have to both charge and change.
So you're saying that within that classification there.
Yeah, exactly. And you have others like, yeah, like the topological insulator. We have.
不认识那个女生是就是刚认识的，她是在苏达这边。
It doesn't come from the tenfold way, it comes through other classification techniques, right? So, you know, the invariant you define there is not one of the invariants from it.
我是第4年，就其实我在那边也会，
And it's fully
比如
gapped.
接了
Here you also should.
所以就要去那边。
So maybe explain that as well, because
在那个德累斯 Just 就是叫复杂类型。
Speak it and ask.
Sure.
So as at the start of high zero. Super high involved.
Yeah.
And you said typically the Q zero.
Yeah.
It's the typical. Like,
Yeah.
are you saying like you don't choose one of these? Particular size and, yeah.
Yeah, so what I mean is. Most of the time you're. It's just. That's what I mean. And then the state, this state. Is not a natural weak coupling state. So usually you prefer this over this. And so this happens, like this can happen. When you break time reversal inversion. And then you can see these states are actually stabilized. But you need special symmetry conditions, which you don't usually have in there. So this shows up when you break the symmetries that you. Yeah, so if you break both time reversal and inversion, then your superconductor is probably generic. Okay, but then you don't have a weak coupling with stability anymore, so you have to work much harder to get a theory that is not nice. But people who, and you will get. Do you have a question, Greg?
I had it and then I forgot it.
Okay.
I was curious if you're going
Okay.
how much is
It seems like there's a lot of flexibility. Okay, actually, it seems like there's a lot of flexibility just by the fact that the Fermi surface doesn't pass through T2 or inversion or transversal invariant. Okay.
Yeah. So we'll talk a little bit about that, especially in the context of what I call blocks.
Okay.
Yeah, I mean, I did talk a little bit about trim points. I mean, it's a useful qualitative guide, but people, it's not really that relevant for most issue rate. Fermi surface has to pass through a trim point. But in the context of things like strong conductivity, Fermi surface comes close to the trim point. If we know that's a zero of the order parameter, we can't understand where you're getting condensation energy from something that passes close to that.
Okay.
And so that's the question that shows up. So it's a qualitative guide to say which states are more stable, or we don't expect a lot of parity to be stable. But here these stress ones,
Yeah. It's the other question I was going to ask you about how do you how much do you nearly intersecting Fermi surfaces interfere? Is that kind of the same picture?
Yeah, so
We'll see, they have like opposite gap signs or something like that.
we'll see. In fact, what you're asking is actually the answer to the question where we live in school. So as I have it, the certain limit show that these Fermi surfaces exactly intersect. So there is a double degeneracy. And then what you'll find is when you turn on all symmetry contraction lattice in this particular case, it's in orbit, you find out it generates an interband pairing. That interband pairing works the gap at one.
Yeah.
And then once you I'll say it.
Okay, now, so for me, this paper completed with 3 parts and sign up for one of the groups during presentation. When you hear all these speakers, and then you decide which group you want to belong. Okay, but again, it should be equal, roughly equal number of people.
So here's the chair of the session, and today I'm introducing Nikolay Prokofiev from University of Agterberg. And today we're gonna talk about funding parts until singular response severity.
Yeah, thanks. I did try to make a small number of slides as possible for very simple reason, just to stay on one slide for a very long time and more or less just talking. There are many things which you can read in books. And so essentially, I would say, whatever I would like to discuss is what is more difficult to find in books. If there are some questions, probably I'll just simply go to the blackboard and try to explain. And maybe I will even try to stay on this slide for a while. Why I call it the quantum part of the phenomenon? Because sometimes superconductivity can be associated with a totally different topic. You create an order parameter, but this is a purely classical phenomenon. So if you ask me what is superfluidity, what is superconductivity, is it quantum, the answer is no. For me, superfluidity, superconductivity is a purely classical phenomenon. You take classical XY model, superfluid. You take classical Psi4 model in continuum or on a lattice. If it's charged, it's a superconducting. You can discuss many microscopic quantum phenomena like Josephson effect, fountain effect, structural vortices, Meissner effect. All of this is classical field. But there is also a quantum part. So quantum part comes literally trying to understand how electrons at the microscopic level, how do they form a superconducting state? Once they form the superconducting state with proper symmetries and everything, we switch to the classical description of the order parameter. So that's why I'm saying this school looks like what I see from topics is not about the classical part of superconductivity. What are the microscopic properties of the superconducting state which you create? It's rather how you create it. And that's probably the most difficult part theoretically. And you will hear different points of view. For example, Daniel started from Bogolyubov-Dijen Hamiltonian. I'll take a totally different route. So which means there will be no UV transformation, no Bogolyubov-Dijen, but I will try to compute TC. So more or less, all my talk will be related to how electrons can actually pair. Probably let me start with the history. because when superconductivity was discovered in 1911, I think, the first kind of puzzle was, maybe I know, some years later, what do we do with Coulomb interaction? Because electrons cannot pair, because it's a repulsive force between similar charges, and there is no way electrons can form pairs. And this was more or less dominating in the community. So even when London was writing down his expressions and how you can understand this and that, who cares? All of this is, of course, nice. It's a scenario. Even when Ginzburg-Landauer has appeared, it was already an order parameter explicitly written. Still, there was no microscopic understanding, okay, how this can happen. Because Coulomb repulsion is the strongest force in any material and electrons cannot pair, period. Then suddenly a very radical step was taken by Bardeen, Pupo, and Schrieffer. They say, okay, yeah, but if we only consider that electrons can interact with phonons, we have effective interaction close to the Fermi surface. And now electrons can pair. But this doesn't answer the question, okay, where did the Coulomb interaction go? So essentially, yes, you have a Nobel Prize for explaining, because universal features around TC were exactly the same as in the experiment. So nobody had a doubt that they hit the right spot. But still doesn't explain what the phenomenon is, because Coulomb repulsion is still there. Electrons cannot pair. And this was like this maybe for a couple of years before Bogolyubov, Shirkov, and Tolmachov. They started wondering, what can you do about Coulomb interactions? They did it semi-phenomenologically, and if you read the paper, it's just horrible. Just almost impossible to read. It's a very complex calculation, order after order in perturbation theory, some expressions I was never able to go through. But the end of the formula, the end of the calculation, which was extremely long and tedious, was that, yeah, okay, effective Coulomb interactions are roughly something like Ba1 plus Fermi density of states and the log. So that's what they did. And then people said, oh, okay, that's probably the solution. So this is Bogolyubov, Shirkov, and Tolmachov. They say, oh, okay, that's how we have to understand now Coulomb interactions. They simply get weaker, weaker, and weaker as you go to lower and lower frequency. Okay, sorry, this is omega d. At omega d, effective Coulomb interactions at omega d are suppressed by the log, and now maybe electron phonon interaction can overcome this effective Coulomb repulsion because it's weaker in the Cooper channel, and now electrons can pair. Everybody was happy, especially Anderson and Morel, because they simply took this formula and gave it a notation. So that's Anderson and Morel now. Okay, so this is Bogolyubov, Shirkov, but you introduce a good notation and this becomes pseudopotential. And they say, okay, if this one is less than the modulus of electron phonon interaction, then you are in a good shape, you can have a superconducting state. Everybody was happy. But then after several years, when people developed numerical techniques, they actually started questioning the formula itself. They say, okay, all of this is nice, but Coulomb repulsions in any material are screened, which means you have dynamic screening of Coulomb interaction. It's not the same constant at high energies, because this is assuming that I have the same constant no matter what is the frequency, because there is no frequency dependence on DUT. What if I add the minimal possible, say, RPA screening to Coulomb repulsion? The answer is that if you repeat this calculation, but now for dynamically screened Coulomb interactions, they turn out to be attractive at the Fermi surface. So which means you don't need phonons in the first place. So the entire puzzle for half a century is a total fake. You don't need electron phonon interactions in the first place. Just do Coulomb repulsion, screen it by RPA, and you have your pairing. You have a TC, and actually pretty high one, because there is no Debye frequency prefactor. The only prefactor is Fermi energy. And for typical material science RS, it's pretty strong attraction. But every material science code is using repulsive pseudopotential. So this is in total contradiction with what you observe in material. You do a better job. Instead of completely screen Coulomb interaction at all frequencies, you do the good job, RPA screen, and you get an answer which is totally at odds with all material science code. And that's how more or less we live up to today. I will probably end the second lecture with one statement. Almost all talks which you hear kind of during the school will be discussing different mechanisms, unusual superconductivity, different pairing states, how Coulomb interactions can actually produce non-trivial coupling. All of this is kind of very exciting. But if you ask any person doing material science and tell them, okay, suppose electron phonon coupling is 0, what is TC? 0. There is nothing unusual in any of the materials if you do material science problem. And that's our kind of current problem. It's a dilemma. We have no software whatsoever. The moment you address a real material and ask a real materials science person to say, okay, what is TC if you switch off electron phonon coupling? The answer is 0. There is nothing. So just what this school is about then? It's all about something which is not electron phonon coupling, which is the easiest kind of ingredient. But if it's not there, then we have to take, I know, correlations, strong correlations between the electrons and produce superconductivity out of this. Do we have a way to apply it to a real material? The answer is no, we don't have it. Okay, that's the introduction. So why we actually bother about the quantum part? How can we get TC? And I will start slowly. I will simply try to present more or less the subroutine, which allows you to compute TC outside of the mean field. Because there was one question, okay, well, if we do mean field, we more or less understand what we are doing. But how to get TC when you try to go beyond mean field? It's not this one. Okay, let me start again from the same more or less heroes. Again, till roughly late 1940s, probably people even didn't believe that spontaneous symmetry breaking does exist. Because suppose you have some symmetry in the Hamiltonian, so you want to compute some quantity Q, but it happens that by symmetry, your Hamiltonian for H of Q, if you just flip the sign of Q, it's exactly the same Hamiltonian. But then if you do statistics, you say, okay, well, it simply tells you immediately that if I compute the average of Q using kind of Gibbs ensemble, no matter what I do, I always have states with value Q and minus Q contributing with exactly the same weight, so they have to cancel to 0. So which means in any physical system, exactly by the symmetry of the Hamiltonian, we should have Q equals 0 at any temperature. And then spontaneous symmetry breaking cannot even happen. I will keep doing it. Well, this is kind of the canonical example when people finally kind of start believing that spontaneous symmetry breaking does happen. Well, it's Ising model. That's the canonical Hamiltonian for the Ising model. Every site variable can be plus or minus 1, but if I flip all of them at once to the opposite, we have the same energy, just because it's a bilinear in sigmas. Well, and then you immediately claim that, okay, for any temperature, the average magnetization, which is simply the sum of all sigma values, has to be 0, because if I flip the sign, M flips the sign. But it's exactly the same statistical contribution in statistics. So it has to be 0. But even before Ansarga solved the problem analytically, Bogolyubov had an argument. And that's how the argument was going. He was saying, okay, well, suppose by symmetry, yes, Q is supposed to be 0. But let's add to the Hamiltonian the source term, which is breaking the symmetry. So I will break the symmetry in the Hamiltonian by adding a term, which is eta times Q. Now, if I compute the Q average, it will be non-zero. Just because, okay, well, I have preference, suppose eta is positive, so I have preference for negative Q. So I will develop a non-zero average. That's okay, fine. So we have a non-zero Q. And then I will simply start taking the thermodynamic limit. I will take system size to infinity, and I will take eta to 0. Well, of course, well, each time I will keep eta finite, but as I scale n to infinity, I'm allowed also to take eta to infinity. Not necessarily eta has to be, say, bigger than square root of n, but otherwise going to 0. It can be actually going to 0 even as exponential function of the system size. It's also allowed. Suppose I just take this limit, and then it may happen that I have the following. So if my temperature is above Tc, I start removing the symmetry breaking field, and at the same time, the Q average will scale to 0 as well. Okay, symmetry is restored, nothing happens. But below Tc, the following may happen. I start taking the symmetry breaking field to 0, and ultimately in the thermodynamic limit, I make it 0. But the response of the system to introducing this one will actually freeze at some finite value, and it will not change. Okay, so which means to stabilize this one, for example, to be positive or negative, it's sufficient to have eta which is microscopically small and ultimately goes to zero in semi-dynamic limit, but nevertheless, it will develop a finite response. So that's how Bogolyubov was discussing the possibility of spontaneous symmetry break before the exact solutions was presented. There is one extra piece to whole of this discussion. You say, okay, how this can happen that I have finite value, but by symmetry, if I flip the sign, it's the same weight, and eta goes to zero. What prevents me from changing q to minus q? And somehow this was.
Can I ask?
Yep.
Yeah. Can I ask a conceptual question? So in this symmetry breaking phase, so do people care about this variance around this value?
To begin to the question was about whether people worry about the variance around Q average.
Yeah.
Formally, yes, but not at the level of argument. Well, because at the transition point, you have to worry about the variance. But once you cross the transition point and you are sitting in the phase, yes, the variance is microscopically small. You develop the average, but the variance scales to zero in relative units.
So, okay, so the argument is because we take the somewhat dynamic one.
Absolutely. If you take Ising model and run it on a system size 4x4, magnetization is zero. Semi-dynamic limit is required. You cannot break symmetry in finite system if we can run the simulation infinitely long. But we are kind of making academic statements. So I'm allowed kind of to explore semi-dynamics for as long as I want. But that's what was missing. That's the number 4, which at the time probably it was not appreciated. That the discussion of finite Q almost necessarily should involve the next piece. Why it's not possible for the system when you switch off the symmetry breaking field? Why the system doesn't go from Q to minus Q? And it turns out that once you develop Q, to get to minus Q, you have to go through configurations which involve defects in the order parameter. So we almost necessarily, to go from Q is equal to Q0 to minus Q equals 0, the system has to create some excitation in the system with the energy which scales to infinity in the thermodynamic limit, which means it becomes exponentially improbable. Okay, in 2 dimensions, it's only power law improbable, but improbable to create such excitation connecting Q0 and minus Q0. Bogolyubov didn't do it. Because if he did, probably almost everybody would immediately introduce vortices to superconductor. But this was done by Feynman, not by Bogolyubov. He kind of didn't discuss this last part. That for the whole argument to be closed and work, you also have to claim that, well, to go from this state to the state which is related by symmetry, you have to, through local dynamics, of course. Of course, globally, if I say, okay, my system size is billions and billions of spins and I compute M average, and you do Monte Carlo, you remember that Monte Carlo, you have typically some updates, flipping spins. Of course, you can suggest an update flipping every single spin at once. It will be accepted because it's the same energy. And magnetization will immediately average to 0. But this is something which is not happening in nature. In nature, all spins at once cannot kind of decide to flip altogether in the opposite direction. They can create a domain of the opposite or the parameter, but then there is a domain wall. Domain wall will cost you energy. So in 2 dimensions, the domain wall energy will scale with the system size, linear system size. And somewhere midway, you have to pay energy which is scale with the system size. It's exponentially improbable in statistics. Good luck with exponential accuracy for exponentially long time. In the thermodynamic limit, infinite time, you will never be able to change the state. Looks like, okay, why I'm doing this? Okay. Now just converting all this blah, blah, you say, okay, this is a nice talk, the discussion, but it's not a practical tool of computing anything. And the answer is no, it's a practical tool. Because what I'm literally telling you is the following. I'm trying to compute how the system develops Q average in response to some infinitesimally small cross term. And I'm saying that, well, okay, if I'm sitting in the normal state before the transition happens, well, Q goes to 0 as long as eta goes to 0, then probably this derivative is finite. But remember that below TC, you develop finite Q average in response to eta goes to 0, which means that this derivative, call it a linear response coefficient of how you develop Q average in response to Q, goes to infinity. So it's literally a singular response of the system to the symmetry breaking field. Okay. So whatever Bogolyubov was saying, I can start converting into something numeric. Just literally developing the strategy of how I can compute TC. I will look for the singular response to the symmetry breaking field. Okay, in our case, yes, Daniel will be discussing symmetries. I will simplify everything in my discussion to just S wave symmetry, just nothing else. Because my talk will just go along a totally different route. So symmetry is fixed, so it's S wave. So suppose I have my Hamiltonian for superconductivity. We know that the particle number is conserved in material science. Well, it literally says that, well, in terms of creation and annihilation of operators for fermions, my Hamiltonian is written with equal powers of psi and psi daggers. So it can be, I know, psi psi dagger, or psi 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 dagger psi dagger, psi 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 dagger psi dagger psi dagger. Just you can go as many as you want, but the number of electrons you delete, the number of electrons you create. So the Hamiltonian can share the particle number. Well, it literally means that in the Hamiltonian, if I multiply every psi by the phase factor, correspondingly, if the psi dagger is multiplied by minus psi phi, well, this is what's called U1 symmetry. The Hamiltonian may not depend on this multiplication because they happen in equal number of powers for psi's and psi dagger. Well, but this immediately tells me that, well, the averages of this type, say, deleting an electron at site I and deleting an electron at site J, somewhere away, this one has to be 0 by symmetry because every psi can be multiplied by e to power I phi, which is arbitrary. It's just like averaging over complex numbers on a circle. If you want, you can make phi equals pi, so same considerations as we had before, or pi divided by 2. So this will simply flip the sign, and this average has to be 0. So that's a typical spontaneous symmetry breaking case. So we'll follow the example and say, okay, well, that's what I have. So let me just simply implement what Bogolyubov was suggesting. I will introduce symmetry breaking field, because if that's the average which I'm interested in, then I will introduce a term in the Hamiltonian which can create a pair, well, say with equal weight anywhere on any side. Well, of course, it's a Hamiltonian, so I have also the term which is psi dagger, deleting and creating. So this is Hermitian Hamiltonian. And now I will start simply computing F, this anomalous average, in the presence of the symmetry breaking field. And my goal is very simple. I will try to find the divergent response. When I can develop infinite derivative df over d eta, when it goes to infinity, I say, okay, that's DC. And this now becomes a practical tool. Because yes, you have a Hamiltonian, you add this term, you do everything in linear powers in eta, you simply compute response and you look for the singular point of this response. And now just, well, okay, everything said before becomes a tool for computing, including high order corrections and all the mechanisms. So that's the beauty of this consideration, how it's done. Again, I will only talk about conventional S-wave symmetry, not to bother about this. So just essentially all considerations apply once you decide in which symmetry channel you decided to break your symmetry. So I will be talking about S-wave for simplicity. Okay. Now just probably something which will require maybe some blackboard. I'm not sure how many of you are familiar with diagrammatic technique, but it's a theoretical school. So I would say, yeah, you cannot live without knowing Feynman diagrams. I know sometimes you can survive without this, but literally, if you want to do mean field, probably it's okay. But the moment you want to account for vertex corrections and to be more predictive with high accuracy, there is no other way, because it's probably, I know, again, I don't know if that is a joke or that's how I learned it. Back in 1940s and 50s, before Feynman introduced Feynman diagrams, there was a technique to do perturbation theory by Schwinger, and this was based on commutators. And people were computing this. And some calculations of second or third order, they took years. And people presented them at the conferences. But then Feynman developed his diagrammatic technique. And he was challenging people, giving talks, that he can solve their problem. Don't show me the answer. Tomorrow, I'll show you my answer. And he was able to do it in one day. And then students of Schwinger, they were cheating him. They were saying, yes, we're doing commutators. But in the background, they did Feynman diagrams, knew that. Maybe went on vacation and then just did a great job. I don't know. So it's essentially, if you want to do perturbation theory, okay, there are many other techniques. But if you want to save time and graduate, do Feynman diagrams. So that's the anomalous average I was interested in. This was type psi with different points in space. Well, formally, you can also do it in different points in tau to be more general. And this is just nothing but the Fourier transform. Well, of course, you can do two operators, so probably I have to mention two momenta and two frequencies. But again, well, those frequencies which you see here, they are Matsubara frequencies. Again, assuming you know what they are, I will just write it down. For fermions, they are pi t double n plus 1. So this is just the Fourier transform. Yeah, integration from 0 to beta, that's because I'm doing everything at finite temperature. So this time is called imaginary time. So this is just nothing but the Fourier transform of this object. When you do the total momentum is 0, the total frequency is 0, but there is relative frequency and relative momentum. So that's relative frequency in tau, and this is relative momentum because I am considering the distance between the 2 points. So this is just nothing but the Fourier transform of the original object which I introduced before. That's the one which I would like to study.
The reason why it depends on R minus R prime is because of Coulomb.
In general, well, it's translation invariance in the system. Of course, if the system is disordered, you have to solve disordered system. Because if the system is translation invariant, everything can depend only, and my source term was uniform. Yeah, I keep doing it. So now just let me switch to what Feynman did. Feynman did said, okay, well, all of this is of course very nice and fancy, but we can replace mathematical object with graphics. And later on, if we want to finish the calculation, we'll go back. We replace graphics with mathematical expression and finish integral. So, okay, well, that's the object which I need, F. I will just denote it this way. Well, remember that this object is deleting 2 electrons. Well, that's why it's kind of written as this way, as if electrons are deleted at this point and this point. So that's kind of the graphics for anomalous average. You say, okay, well, how I can produce this once I have the symmetry breaking term? Well, that's how you create it. Eta creates a pair on some site. Then electron with one spin and momentum and frequency propagates, and the other electron propagates, and then you delete them. So that's the most basic contribution which you have to have. You create 2 electrons, and they propagate, and then you delete them. So those are operators are deleting the electron. Okay. Well, and again, I know when you see the black line, this is nothing but the mathematical expression for what's called the Green's function. The Green's function of the fermions. Formally, it's the Green's function, which is the exact propagate of electrons in the interacting medium. Well, then you say, okay, well, that's not only thing which can happen. What can also happen that you create a pair, electron propagates, but then they interact. And here they can interact in any possible complicated way you can only imagine. But I cannot cut this one and have only kind of 2 fermionic lines which I cross, which means there are more propagators, more interaction lines inside. So if I just try to cut this graph, I will have to cut more than 2 lines G and G. This is called Cooper channel irreducible. So, which means 2 electrons are created, they propagate, then interact, and then emerge from interactions, and ultimately I delete them. So, okay, we have to account for this one. But then I have 3 dots after that, which means I have to account for the full set of ladder diagrams. Well, literally saying, yes, you create 2 electrons, they propagate, interact in all possible ways, but do not emerge as 2 particles. Well, but then they can emerge as 2 particles and start interacting again. They will emerge as 2 particles and then start interacting again. And I can do it as many times as I want. Again, I am trying to illustrate graphically what otherwise you have to do kind of more or less as perturbation theory expansion. Any questions here? Why Feynman diagrams are great? Because they're literally something I can spell out. Yep.
Shouldn't there be GPN on the bottom and like
Not minus.
Yeah, not minus.
Here?
Yeah. No. The right diagram. Below diagram. Up,
Bottom left.
up, middle right.
Yes.
Middle right.
P minus
minus n and
Minus K minus M, K M, minus P minus N. I think it's okay.
Huh?
What's wrong? Total momentum 0, total frequency 0.
The P is an
the p is an n.
one of them.
external.
External.
Minus P goes out.
Yeah.
This one?
No. Here on the second diagram.
On the
Second diagram,
On the-
P M,
lower-
K M.
One on the lower left.
Yeah, on the lower left.
Oh, yeah, sorry. Yes, you're right. Of course. Now I got it. Yeah. PowerPoint. You just copy the object and you forgot to change the sign. So yes, of course, it's PM. Absolutely, you're right.
There's a question.
Yep.
Minus sign from the definition of the vertex.
This is simply just the sign comes from the way how you compute gamma. So if it was, say, brute force interaction U, then the expansion of the Hamiltonian is in minus U beta. So there are no extra loops anywhere. So this is how gamma is divided. It decided it starts from U. So it's sign minus. From perturbation theory. Next order perturbation theory is E minus H. If you have U in H, so this is minus U. Nothing else. Formally, maybe a couple things. Well, if you wonder how the formula goes, literally, I add the source term, but I'm only interested in the linear in eta response. So I drop it from the Hamiltonian. One doesn't bother me because without symmetry breaking term, the average is supposed to be 0, so I drop it. So then I have another term, and then I have, of course, the rest of the Hamiltonian. So that's the next line. You say, okay, well, that's what I have to compute, minus eta integral over dr ds, because I can produce the pair anywhere I want in time and space. Now I have 4 operators here. Eta is already in front. E minus beta h, and that's the correlation function which you have to compute now diagrammatically. Of course, while E minus beta h itself, this one, is written as bare Hamiltonian, which is purely non-interacting kind of Hamiltonian, which allows you to perform Gaussian integrals and weak theorem. That's what you have to learn from the diagrammatic technique. And then the so-called tau exponent, which will address the Green's functions, produce interactions, and everything else. But the lowest order term, and you just forget about interactions at this level. So this is just, well, this is the Green's function, this is the Green's function, and that's the first term which I have written to you. Eta creates an electron hole pair. Electron propagate from capital R to R. This one propagates from capital R to R prime, and then you delete it. Of course, well, once I start caring about interactions, this will produce, I know, more and more terms which will address the Green's functions and will produce gammas to write down kind of the final expression. Okay, that's what we have. Again, so far I'm absolutely exact. I did not approximate anything. Of course, you say, yeah, it's a little cheating because, okay, drawing a box with something inside doesn't make it, I know, easily solvable. But formally, yeah, well, then compute properties of the box and you can do the rest. So formally, just, well, that's how it looks like. So anomalous average has this structure of ladder diagrams in terms of particles propagating in between the blocks. But you immediately see that this structure has certain similarity. So if I just take the first term, okay, it is, and I just cut out 2 Green's functions and the block, put the bracket, and then start writing down what do I see inside. Well, inside I have exactly the same expression as I had above. And again, historically, this is pretty bizarre, but it took several years for Dyson to develop this type of concepts. Because Feynman developed diagrammatic techniques, how to compute perturbation theory. Dyson noticed that, well, okay, a lot of about diagrammatic technique, especially kind of for psi4 theories, free bosons, and free fermions, actually has a very important piece, and probably I have to mention it. There are tons of different perturbation theories, strong coupling expansions, link cluster expansions, tons of different expansions. Some of them are just doing wonders, high temperature expansion. But none of them has the structure of Feynman diagrams, because in those expansions, coefficients in front of different graphs, they depend on the structure of the graph and the order of the graph. In Feynman diagrams, the coefficient in front of the graph is always 1. Yes, my lines carry mathematical structure, but the moment you draw a particular graph, the coefficient is 1. You draw another graph, coefficient is 1. But this immediately creates infinite geometric series which you can sum multiply. And that's what leads to the Dyson equation. So if I do strong coupling expansion, high temperature expansions, they don't have Dyson equation. You really have to sum up all the graphs as they are. Maybe later on you apply the summation techniques. But in Feynman diagrams, you can sum up geometric series on the fly to infinity if you want to, and formulate something which is a self-consistent theory. So that's the difference between the Feynman diagrammatics as expansion relative to other types of expansion. So that's what we enjoy here. So we have Dyson type of equation, and that's what we have. Anomalous average equals this term based on two Green's functions, irreducible gamma, two Green's functions, and closed by the same blue line. So this is our Dyson type equation. Now just to say, okay, well, enough of graphics. So that's how this equation now looks like in terms of our prime objects. The anomalous average is given by the source term, breaking the symmetry, two Green's functions, minus two Green's functions again from here, irreducible gamma, and then the entire bracket, which is our anomalous average itself. So this is now a self-consistent equation. I can redefine it, and it's kind of often done for simplicity. Well, you can simply say, okay, this is f, but if I introduce delta, delta is simply given by Matsubara's sum of gamma times f. Nothing, just simply just take this part and apply it to f on the left. I already have this part here. So this will create delta on the right, delta on the left, and this is the different type of equation. But because the source term goes to 0 anyway, the first term is just simply generating whatever you want for delta. And then, okay, well, the rest is self-consistent equation. So that's what is typically called Gelt function equation. Again, this one or this one, they're no different from each other. This is just redefinition of the quantity which you use for self-consistency. But now this is a tool. Because if I have some idea of how to compute perturbatively Green's functions and the fully reducible gamma, I have something to solve for TC. Now just let's go back to what do we want to say for TC. Any questions here?
Maybe.
Yeah.
Delta naught, which you put here.
Well, I just,
Let me ask a question.
Yeah.
Can you take it as a constant, or at the end of the day, frequency dependence?
It's totally relevant for what I am going to discuss next.
Yeah.
No, because eta goes to 0.
Yes, no, it goes to 0, sure.
Yeah.
But will the structure of delta not important?
Formally, if you want to do everything, including linear response, yes. Because you say, okay, well, delta 0 is this one. So sorry, just, I took this structure, so which means I have GG multiplied by gamma. So delta 0 is gamma GG summed over. So once I compute gamma, once I compute G, yes, I know what is delta 0. But for everything else which I will discuss, this is irrelevant because I will put it to 0 ultimately. So is it clear how we arrived here? Because we started from blah blah idea by Bogolyubov, how you can think about spontaneous symmetry breaking, a singular response to the symmetry breaking field. And we ended up with the equation which actually allows you to start computing this response.
Quick question.
Yep.
Is gamma, is that independent of beta, or is actually like a
Independent. Eta is already taken care to the lowest non-zero order out.
Okay.
Yeah, there is no eta anywhere. That's why it's exact. It's a normal state. Right now, I'm simply saying, okay, well, in the normal state, I take eta to 0, delta goes to 0. And I'm trying to figure out at what particular temperature it may happen that delta starts developing a singular response, that the derivative goes to infinity. I'm not trying to break the symmetry and go below TC. That's a slightly separate discussion now because it will involve, okay, what kind of superconducting state you have, how you modify Green's function with this delta. I will not discuss this. My point is to compute TC. For computation of TC, this is sufficient. Okay. Now just the final piece, kind of to finish the job. So, okay, I'm looking for singular response, but then I look at this equation and say, okay, this reminds me literally, because if I treat P and N as an index, yeah, I have components of delta, and P and N are just, well, simply enumerating the component. Just imagine you have finite system, then even P is quantized, N is already an integer from minus to plus infinity. Yes, it's infinite dimensional vector, but so what? So it's a vector. Well, this is also a vector, initializing. And this is just a matrix. It's just a matrix which is connecting Km to Pn to all together. The entire kind of project, I say, okay, I sum up over Km and Km. So this looks like a vector equals source term times matrix my delta. Okay, but if I look at this, I say, okay, wait a second. If I want to compute singular response, let me go to the eigenvector basis of A. In the eigenvector basis of A, instead of writing it this way, I say, okay, suppose you are given the solution for the eigenvalues. That's how I can write down my matrix in diagonal form. It's alpha, alpha, with some eigenvalue alpha. And those are the eigenstates. So yeah, but if I use the same basis to expand delta, so those are the components of alpha, that's how our equation can be written. Now just everything is breaking into components for the eigenvectors of the matrix A. So that's how it looks like. But now it's not a complicated equation. This is just a simple algebra. So immediately you say that, well, okay, delta A equals, and then you can plug it here, multiply by eigenvectors, done. So if you can diagonalize the matrix, so that's your answer for solving this equation. Of course, you say it's infinite dimensional matrix. How do I diagonalize it? So you just imagine. So if I imagine diagonalizing the matrix, this is my answer. And you see that, well, okay, well, the answer depends on eta, of course, how I initialize with delta 0a, it's just, you know, whatever vector I want, divided by 1 minus alpha. And I have to sum through all the alphas. Well, okay, well, you immediately see that the singular response will happen when the largest possible eigenvalue ultimately reaches 1. So if all eigenvalues are smaller than 1, negative, easily, minus 10 is good. But if you stop at minus 0.5, your response is finite. Which means I take alpha, now I can simply differentiate because I have an exact analytical solution, differentiate over alpha, just plug in this expression to here and you are done. It's a finite answer. You have no singularities in denominator, the rest is just okay. Some finite sum over L in your alpha and you are done. Yep.
Should you worry that this particular eigenvalue with alpha equal 1 may be localized, not representing entire system?
Maybe to some degree academically, but I definitely cannot cross 1 because this would be singularity, infinity. So the moment I kind of get 1, formally the equation is correct in the sense that one eigenvalue, given that you had take the integral, maybe it's an integrable singularity. But it's a one-dimensional integral. So even this one will probably create a divergence.
You may have a singular response, but just in some point or some localized.
I'm not saying that I will break the symmetry. I cannot say what kind of superconducting state I will create. I know nothing, but I know that my response becomes singular. Now my system, when I add infinitely small eta, tries to respond with finite response. At least I definitely satisfy the condition that dq average over d eta goes to infinity. What the singularity means, maybe may depend on circumstances. I cannot immediately kind of answer for all possible matrices. Probably just not well educated for that, but for sure my response has a singularity, so which means I go to infinite response. So that's what I will call TC. So we have our tool. So for superconducting TC, I have to look for the largest possible eigenvalue equals 1. And I simply just formulate it exactly this way. So if my job is to take an interacting fermionic system and determine TC, I have to compute Green's functions. I have to compute fully reducible coupling in the Cooper channel, and then just to perform analysis of eigenvalues of this matrix, or solve this eigenvalue equation, and look for the maximum possible alpha t. And if I can find that the maximum possible eigenvalue equals 1, that's my TC. Okay, so this is the practical tool of computing TC. I'm probably going too fast because I wanted to go much slower, but hopefully this is clear. Any questions about that? Yep.
So this delta object is slightly different than the original F object that we're wanting to
Yeah.
compute, right? So how do we know that this divergence is not coming from, say, the sum in the definition of delta, rather than from the F object itself?
You mean, sorry, I'm moving in the opposite direction.
Right. So from the sum over.
No, I understand. Okay. So unless my interactions are infinite, so formally I would say for almost any kind of realistic system which I am aware of, the two are simply proportional. So yes, you produce some effective coupling, especially close to the Fermi energy and at low frequencies, and delta is proportional to F. The divergence is not coming from this absolutely linear relation. So if delta is finite, F is finite, then you can relate one to another through the product of two Green's functions. And there is nothing divergent as a function of temperature in this particular expression. Sorry, no Green's function. This is just gamma. There is no Green function in the definition between the delta and F. And typically for any system, our interactions just saturate to some number, and this is nothing else. Because this is Cooper channel irreducible. Probably to be more careful with this, I'm assuming that there is no competing instability, because probably I have to reformulate this question slightly differently. What if it happens that divergence is coming from gamma, not from the superconductivity? Yeah, then you're simply going to say antiferromagnetic state, or you go to ferromagnetic state, or you go to the charge density wave. And before anything happens here because of the gap function equation, actually gamma blows for other reasons. So this would be a competing instability, yes. So if you discuss kind of complex material and there are competing order parameters, sometimes probably you'll have to solve it properly, including both channels. Andrey is a specialist in doing this. So sometimes you have competing channels, and the renormalization group analysis says, okay, well, it's kind of delicate balance. Maybe one order parameter wins or the other order parameter wins. So this would be the case, yes. So it's possible that diagrams which are not related to this structure of ladders in the Cooper channel, so divergence is not coming from this structure. Divergence is coming from other diagrams inside gamma, which lead to a competing instability. Which can potentially kind of interfere with superconductivity and change physics. Yes, that's possible. Yeah, thanks for the question. There was another question. Yes.
What if there are multiple alphas where it's discontinuous?
This is typically doesn't happen. I would say just any of them which touch one, I'm happy with. This is TC. Because that's when you create singularity.
And when the temperature is less than TC.
I'm not going below TC. So the moment alpha maximum touches one, stop this, because after that I have to write down already self-consistent equations where delta is already part of the Green's function. So I have to go further.
Because when you in the beginning of the slide, you said pretty derivative of an expectation value of Q with symmetric breaking parameter eta. It goes infinite when temperature is less than TC.
Yes.
But your explanation perfectly explained when T equals TC, where alpha TC equals 1. But when temperature is less than TC, Y needs to be infinite.
Well, by definition. You introduce infinitely weak field and you have finite response. The derivative is infinite. So everywhere below TC, it's already infinite. So I'm just looking when this infinity will happen first. Yep.
If I'm also allowed to ask questions.
Yep.
Suppose I consider attractive U, just simplest case, gamma is U. But Fermi energy is extremely small. It's a standard case of BCS, BEC. Does this calculation give you actual TC or mean field TC? Or in other words, to get the actual superconducting TC, how can I include phase fluctuations in this approach?
Or by being extremely laborious, you will include phase fluctuations. So we have Cooper channel, but somewhere inside the graph, Nobody can stop you from kind of introducing another Cooper channel as part of the graph. So probably I will close this like this, just well to draw something. But this one involves the same ladder. Formally, this is Cooper channel irreducible, but this one starts diverging. So if you start including this type of diagrams, yes, you will take care now of phase fluctuations, and probably you'll see that, well, okay, well, the universality class has to be U1, not the mean fieldish transition. But in most superconductors, TC is so much smaller than Fermi energy that fluctuation region is negligibly small. I think it's TC over Fermi energy, TC to power 4 divided by Fermi energy cubed. So that's the size of the fluctuation region. It's outrageously tiny. But formally, yes, this is hiding inside gamma.
I'm supposed to know this, but I don't. Did anyone really did this?
As far as I know, something like Minnesota. Larkin Aslamazov, of course, did it not in Minnesota, but Larkin is the figure attached to Minnesota. So Larkin Aslamazov, that's precisely fluctuation physics above TC.
It's exactly like this.
Those type of diagrams, yes, because they're the only ones which are dangerous. Because otherwise, if there is no competing instabilities, everything else iterates to a constant.
Okay.
So this is the only one which potentially will bother you. Inside the diagrammatic expansion, you suddenly see that you have to include same channel which is diverging.
There's a question.
Yep.
Why does that diagram correspond to phase fluctuation?
Well, because this is propagation of the pair. Why you call it phase fluctuations? Call it both. Let me say, okay, well, another story. For example, when supersolidity was discussed, at some point Anderson made a statement that it's possible to have superfluidity without compressibility. So which means, and his argument was very simple. Take XY model. In XY model, the modulus of the phase of the field is fixed. You only have phase fluctuation. And looks like, yes, you have superfluid transition when compressibility is exactly 0 because the modulus of psi is fixed. But at the end, 1960s, Anderson was the one who was teaching Josephson that phase is real because the particle number is not conserved. They're just complex conjugate parameters. So if you phase, then particle number is not decided. If you decide about the particle number, then the phase fluctuations are infinite. So literally, when you just start doing this, there is, if you are not breaking the phase yet. So that's both. It's phase fluctuations and particle number fluctuations. You start developing the order parameter because both are fluctuating. And actually, particle number has to fluctuate on a large scale to develop the order parameter, which is superconducting. So if you want to fix the phase, you have to fluctuate the particle number. So it just probably this is just a language which people attach to something which is not done on the mean field level. So they say, yeah, do something like phase fluctuations. But otherwise, I would say just, okay, simply just include other diagrams of higher order, which takes care that the transition is not second order with typical second order critical exponent. The transition is U1. Critical exponents are not 1/2 of the correlation length. Why? Because there are other diagrams. Why we call it sometimes phase fluctuations? Probably that's probably a better answer, even though diagrammatically I have no idea how to do it. You start from superfluid phase. Remember my point number 4 in the Bogolyubov's discussion. How do you destroy the order parameter? If you fix Q0, how do you go to minus Q0? I say, okay, yeah, by defects in the order. Defects in the superfluid or superconductor are vortices. Vortices carry the phase which is rotating by 2 pi around them. So those vortices, you can say they are phase fluctuations. Even though in the core of the vortex, the density also goes to 0. Okay, at least it's suppressed severely. But when you approach the transition point, you have a lot of vortices, and essentially it becomes a soup. But when it's a dense soup of vortices, the phase is fluctuating and density is fluctuating. Once you reach the fluctuation region, yes, you have individual vortices, but they're exponentially expensive in temperature, which means vortex rings very quickly just disappear from the statistics. Only in the fluctuation region they are becoming important, and that's how people say, okay, phase fluctuations. Can I describe a vortex by Feynman diagrams? I have no idea. The only way to describe vortices in Feynman diagrams, I would say, to go to very high order, just do all possible diagrams to high order, and maybe some of the vortex physics will be captured to some degree. At least I have never seen anybody being able to, say, reproduce Koster-Thouless by Feynman diagram. Yep.
That's the resurgence started.
Oh, let's do resurgence now. Feynman diagrams allow you to do a Taylor series in the coupling constant. So this is fine. But then you say, okay, but there's a problem. Suppose I have a function like e minus 1 over g.
Yeah, that's right.
Taylor series are 0, but the function is there, which means purely from Taylor series, you can miss some of the terms in the expression and never know about them. This is not exactly true because there are kind of other techniques. You just go in the complex plane, you can analyze whether such terms are allowed or not. But suppose someone says, okay, I have a technique which allows you to do Taylor series in e to power 1 over g. And I have a technique which allows you to do power series in log of the coupling constant. So for me, resurgence is the following. If you have a technique to compute Taylor series in the coupling constant, exponential of the coupling constant, and the log of the coupling constant, you cannot miss any of the function, which means your answer will be reconstructed uniquely. If you have enough terms, you will reconstruct the answer uniquely. This is research. But we don't have a technique to construct Taylor series in the exponent of g or the log of g. Feynman diagrams give you Taylor series in g, but there is no technique. Regular technique, when order by order, you can switch the computer and compute high order Taylor series in the exponential of the coupling constant or the log. At least I'm not aware. So that's called resurgence. Sorry.
At this point, have we taken any assumption as to the form of the order parameter?
Sorry?
At this point of the calculation, have we take any assumption as to the form of the order parameter?
I already did probably a little bit, but not necessarily, because I didn't say yet in what symmetry channel I will do it. Because formally P is a vector, and you can say, okay, yeah, but gamma is a matrix. And formally here, just say all orbital channels, just to take, say, suppose it's a liquid, helium-3 liquid. Yeah, it's the same equation for helium-3 in all possible channels. Even though I explicitly was already doing spin up, spin down. Okay, in the spins, you have spin triplet, but then I have to write it down separately for spin triplet. This was spin singlet, but still I can have S wave, D wave, and others. So what you do, you say, yeah, I will simply decompose gamma into different symmetry channels. I will decompose delta in the symmetry channels, and my equation will split into independent equations for different symmetry channels. Probably this is precisely what will happen at this level. Because if you have a matrix and different symmetry channels by symmetry are not coupled, simply your eigenstates are already encoding different symmetry channels. And maybe a particular symmetry channel will touch one, and that's the one which will go superconducting. All the others you can forget at this point.
Just a follow-up question. Wherein did we take the assumption that this is a singlet state?
I already wrote psi and psi with opposite spins. I explicitly has written psi I up and psi I down. If I wrote both up, this would be a but that's it. But I was writing already a symmetry breaking term that I create a pair with opposite spins on the same side. So which means if you give me the same spin, I have to split them even in the symmetry breaking term. Okay, we delayed enough. Now just for reproducing BCS mean field, kind of in this language. Well, suppose I just have BCS, which means weakly coupled theory. I'm not going to renormalize the Green's function. So it's the Bayer Green's function for free fermions. So that's the expression for the Green's function, G. Well, dispersion relation is given by whatever you have, tight binding model or any other model minus chemical potential. This is Matsubara frequency. And I will take a model which was done by Barton Cooper Schrieffer. My effective coupling is attractive, so it's minus G. G is a constant. For some energies, frequencies, and momenta, but forget about, for example, momenta, just for some frequencies, less than capital omega, which is much smaller than Fermi energy. And it's zero otherwise. It's kind of step function. So it's attraction and then just nothing in frequency. I will simply plug it into my machinery. So that's my eigenvalue equation. Well, but gamma now is just a number. So which means it cannot produce an index PM outside, which means delta is also a constant. So delta is a constant because of the gamma. Okay, so our matrix vector equation actually becomes the scalar equation. So I have alpha delta equals G. Whatever is left is T sum over momenta and Matsubara frequencies, but the sum over Matsubara frequencies is limited by capital omega, because that's what G in gamma is enforcing that I cannot go further in frequencies. So that's it. So my largest eigenvalue now is simply given by, because there is only one eigenvalue, nothing else. So that's given by alpha equals G and this sum of Matsubara frequencies and momenta for the Green's function. You can introduce, I know, different types of cutoffs, doesn't matter much. And that's more or less the answer. So if I just take this ideal expression for the Green's function, everything is analytic, substitute here, assuming that everything happens at low frequencies and close to the Fermi surface, the integral over energy, measure it from the chemical potential here. Well, it's just the integral of Fermi surface density of states, integral over dxi. This is just standard hyperbolic, conventional tangent function. But so I can approximate it, assuming that integration can be taken to plus or minus infinity, because this is convergent sum. I can integrate much further than omega m, because omega m is limited to a value much smaller than Fermi energy. So with leading order accuracy, you take this integral, and that's the answer. Okay. Of course, taking sum of Matsubara frequencies, that's roughly the same as taking in the integral over d omega over omega from the lowest possible temperature, because remember, omega m is truncated by temperature from below times to capital omega. So this is the log, and this is the answer. So we reproduce BCS. I didn't use Bogoliubov Hamiltonian. I didn't use mean field. So that's the answer which you get. Bayer-Green's functions. The coupling is purely a constant, which is attractive for a particular frequency range. Use BCS answer. Okay. Essentially, once we have our machinery, because machinery was more or less generic, getting BCS, the whole theory of BCS. This is not how it was done, but that's how we can do. Okay, well, just to get TC, of course, you know what to do, because I write down 1. That's what I want. It's my condition for divergent response. I have log, you invert it for TC, and that's the canonical answer for the BCS transition template. Any questions to this part?
Yeah.
Probably nothing.
Question. I'm sorry. Here.
Yeah.
In the previous slide, when you do the summation over the Matsubara frequencies, and when you turn it into an integral, there's a cutoff at the integral, right? The omega. But what
Well,
about
because the lowest possible in modulus is temperature.
Yeah.
Okay, 2 pi t, sorry.
Yeah, and the upper cutoff is some.
The upper cutoff is capital omega.
But if you look at the summation, like where do you truncate this summation? Because the summation is divergent, right?
No, because the upper limit is omega. The upper limit is omega.
That's for the integral.
No, same for the sum. Yeah, probably I don't mention it, but I'm saying just, okay, everything here in the sum, the moment you have a frequency index, it's limited to be less than omega n. So the summation over m is also limited by omega. So probably I have to put it explicitly.
The harmonic series, the summation over n diverges, right?
No, the sum over m goes only as long as omega m less than omega.
So is there a way to like relate this?
So if you sum over m, 2 pi t m has to be less than omega. So which means omega m is limited by the ratio between omega and temperature. So you sum, okay, 2 pi t and 2 pi t cancel. So it's really the sum over m from 1 to omega divided by 2 pi t. Yeah.
Why did you use the fact that it's a weak coupling?
Oh, because my Green's function is ideal. If it's not weak coupling, I'm slightly in trouble. And I'm using a model for gamma. If interactions were strong, how can I be sure that nothing, how can I relate gamma to some original coupling function? So maybe it will be renormalized to something else. So that's why it's weak coupling, because I'm using ideal Green's function and I just do essentially no job for gamma. It's like a model.
Following that question, so why do we need omega to terminate this submotion?
Oh, we need omega to terminate this, so otherwise we have superconductivity at any temperature you like.
Well, that's like an ad hoc thing.
Well, you see, it's a model. So it's for this model you suddenly insist. For example, suppose omega has no limitations. I can give it to you. So I have attractive coupling for any frequency range. Then this integral will slightly be in trouble because I'm integrating close to the Fermi surface as psi divided by psi squared. But ultimately I will discover that, okay, the dispersion relation is probably k squared over double m. And then, okay, while my integral will start converging, and I will change from 1 over omega to omega squared. And if it's 1 over omega squared for large omegas, because it will be much bigger than the bandwidth, then this sum will go as 1 over omega till Fermi energy, and then it will switch to 1 over omega squared and will become convergent. Then instead of the prefactor, which is given by omega, or this one, this will be Fermi energy. So if interactions are more or less not truncated, then probably your prefactor in the exponent will be Fermi energy.
Is this hard cutoff and omega divide just like we just put a hard cutoff like a step function? That's
Next slide.
Oh.
No, this is the model. I say, okay, suppose you want to explore the machinery by a simple model. Yeah, I'll do it.
That's a very small question.
Yeah, this is what Badin Cooper Sharifa did. I'm just reproducing.
Sorry, that's a very small question. So where does this 1.13 come from?
From the sum.
I mean, if you do the integral from t to omega 0.
No, of course, the integral, I'm saying approximately, which means if temperature is very, very, very low, you just do this integral, it's just the scaling. Well, but if you say, okay, okay, approximately means that 1/3 is not a big deal, given the exponent. But otherwise, just, okay, well, simply do the discrete sum with proper restrictions on the computer, and it will give you those numbers.
Or Euler-Maclaurin.
Yeah. Okay, so we're done with small BCS. Now, next question is, okay, well, this is just too much for a model. What if I simply do something more realistic, that electrons are interacting with phonons? There is some coupling constant, which potentially depends on the electron momentum before, electron momentum after. So the electron is scattered from state K to state P, and at the same time will, for example, emit a phonon. And of course, I have a complex conjugated term. Again, by Feynman, you just say, okay, well, this is fancy mathematics. This is the graph. The electrons comes with momentum P, exit as momentum K, and at the same time create a phonon with momentum Q equals P minus K, and that's the matrix element to create it. Of course, if I do my Cooper channel and my gamma, it simply says, yes, electron can create a phonon at one point, or absorb a phonon at this point, and then just do the opposite for the second electron. So this is my effective gamma, which is simply given by this construction for the phonons. Again, this is free phonon propagator, but at the same time, I also multiply it by the coupling constant. So this is my effective gamma and effective attraction between the fermions, because the sign is negative. It's effective attraction between the fermions through exchange of phonons. So this would be more realistic in the sense that I have some Hamiltonian. Now my gamma is not a constant, but you see how it behaves. Yes, there is some dependence on K and P, but if everything happens close to the Fermi surface, I will probably average this square over the Fermi surface. Okay, also my omega may be a function of K minus P because I have dispersion in the phonons. So I'll have to average over the Fermi surface the entire piece. But suppose you have a model where omega is just a constant. Well, that's how the function will behave. Instead of hard cutoff, this will be a smooth cutoff. So it's a function which starts from somewhere, then close to this typical omega, it just starts going to 0 as a function of frequency. And again, this will simply change my integration over frequency from 1 over omega to higher power of omega and make it a convergent summation. Fundamentally, nothing changes. You will simply change the number in the prefactor in front of the exponent. Nothing else. So otherwise, everything works exactly the same because the logarithm is collected here between the temperature and typical scale of order omega. This is simply a different way of how the upper limit of the log is regularized. So it's a different prefactor. So fundamentally, it's the same BCS, not a big deal. But you realize that, okay, well, this is more or less a general statement about any exchange through vertical excitations in the media. They can be phonons, they can be magnetic excitations, and this was very popular in the discussion of helium-3, that probably you exchange magnetic fluctuations in the same Fermi liquid. This can be two-level systems, or any other collective excitation which you can imagine of bosonic nature, which works like phonons. So formally, yes, we do it for phonons here, but otherwise, just any bosonic type of excitation which exists in your system will work exactly the same way. Probably Agterberg was also behind doing it for two-level systems. When high TC was invented, he had a paper when instead of phonons, here you just have two-level systems. Okay, so that's the standard BCS. We did one upgrade that my gamma is no longer constant, but has some frequency dependence, more or less nothing important. Well, there is yet one more step to do beyond BCS. That the moment you introduce interactions, strictly speaking, your Green's function should be renormalized. You have to be consistent. So if electrons interact by phonons, then probably the Green's function is also at least at the same level, at the lowest level perturbation theory, should also be changed. And that's the Feynman diagram for what can change with the Green's function. Yeah, you can read it this way. Again, it's a solution of the Dyson equation, but it works this way. Kind of repeating the same argument. Electron propagate. That's exact propagator, but it can happen that electron propagates, doesn't care about phonons. Electron propagates, but then it interacts with the phonons, creates an emit phonon, and then just absorbs it back and keep propagating. But I can repeat this as many times as I want. You sum to infinity and immediately see you create the same type of Dyson equation. This one, it's G0, and then if I just cut off this part this way, you see that I will start repeating the same expression. So it looks like this one, self-energy. That's this, the object is called self-energy at the lowest order. Otherwise, it can be any diagram which you cannot cut through one fermionic line. Otherwise, it can be horrible and complicated. And this is again becomes Dyson equation. So this is my G, this is G0, G0, sigma G, and that's what's called self-energy. Again, in the lowest order perturbation theory, probably you just do the lowest order diagram. But because of the Dyson equation, it doesn't cost you anything to put it in denominator.
In the self-energy, why is it G rather than G naught?
Where?
Those.
Oh,
yeah.
because of those diagrams. Okay. This is one of the possibilities. Okay. But you can say, okay, what about this one? I say, okay, we'll account it. But I can insert it as many times as I want, and this becomes G. So this is called non-crossing approximation. This is also called Born approximation. So it depends on whom you ask. So it's the same name, non-crossing, because none of the wavy lines can intersect each other in the graph. One is always enveloping the other.
It's nowadays it's called self-consistent one loop.
Self-consistent one loop, Born approximation, or non-crossing approximation. They're all the same. So it's the same name for kind of this construction where self-energy is defined in terms of phonon propagator, which potentially also can be renormalized. I will discuss it lecture 3, and Green's function propagating. So you can just compute this diagram, and turns out that, well, okay, that's more or less the outcome of this type of calculation, that your Green's function will be renormalized. So the Green's function will have a singular part. I will call it singular part because that's precisely the structure which was giving us the log. But remember that in front of the log, I will have now a coefficient z squared. And also kind of the spectrum will be a little bit renormalized. So I have, when I compute the log, I have to change the density of states because the spectrum had been renormalized, and I have to put the quasi-particle residue squared in front of the log. And that's also important. This part is not singular because that's really, if you look at the occupation numbers, this non-singular regular part, which gives you some smooth function. And on top of smooth function, you superimpose a step. But this one works exactly the same way as ideal gas, except you have a z factor and a normalized density. So that's what will happen to our expression. Probably I have to wrap my presentation a little bit. So just instead of ideal expression as we had before, that's the only modification which will happen. Previously, when I was computing the product of GG summed over, this was bare density of states times log. Now I will have z squared, and I will have effective mass renormalization times Fermi energy density of states times log. That's the only difference. It's all coming from here. You change the spectrum, which changes the density of states. Close to the Fermi surface, this is characterized by the effective mass. And I also have z squared because I have the product of two Green's function. That's why z squared. So this tells you, okay, probably if I want to do one step beyond BCS, I also have to account that effective coefficient in front of my log. It's not just bare electron phonon coupling as it was before. I have to multiply it by z squared m star divided by m. And for phonons, it happens that m star divided by m is also given by 1 over z. So that's the famous combination which you will see in all phenomenological formulas discussing electron phonon superconductor. It's exponent, but in the exponent you have not only 1 over lambda, but you have minus 1 over lambda 1 plus lambda. So that's where it's coming from. The combination of z squared and effective mass renormalization. So that's more or less the end what goes into discussion of how superconductivity happens because of the phonons. But this doesn't explain, probably I will just repeat what I already put on the board, why superconductivity happens, because I am talking about some phenomenology, effective interaction between electrons and phonons, but we still have Coulomb repulsion. Coulomb repulsion is the strongest force. So that's how it was done by Bogolyubov, Tolmachov, and Shirkov. I reformulated because that's not how they did it. Again, I cannot read their paper, but that's the modern view of how you will do it. I would like to understand what is the effective gamma which I need for the Cooper channel at low frequencies, which means I will make this gamma Cooper irreducible at low energies, but I will sum up the Cooper logs to infinity for high frequencies. So that's what I want. Electrons come with low energies or low frequencies. They exit with low frequencies, but in the middle, they interact somehow. Okay, this is purely repulsive, very strong repulsion force. Well, but then they interact repulsively, propagate at high energies, and they interact again, but emerge at low energy. So you start from low energy, interactions take you to high energy, you propagate, then interactions take you back. And you can repeat it many, many times as much as you want. So in the middle, you have to propagate at high energies everywhere, because I want something which is irreducible when you propagate at low energies. But at high energies, account for everything. So which means now my gamma is all possible diagrams of any kind you want with only one distinction. If you can cut the graph through two Green's functions, they have to be at high energies. That's it. And you do the summation. It's again, let's do the model. If gamma is a repulsive constant, I just do this summation of the ladder. So that's what we have. Okay, died. Doesn't matter. So we do the summation of this. We say, okay, G minus G squared. This is log, but the log now goes from Fermi energy to some low frequency, which I use for truncation, what I call low frequency. Okay, so the log is only through the high energy state. So this is this log. And my interactions are repulsive. So this is G minus G squared plus G cubed. And you saw, and this is geometric series. You sum them up, and that's done. So that's precisely what was done by those guys in 1958. They say, okay, well, the effective coupling between the electrons, because of the Coulomb forces, if I can replace Coulomb forces by a constant, this is what I get at low frequencies. Yes, it can be very strong repulsion at high frequencies. Nothing changes to the model. The model says, okay, strong repulsion for any frequency you like. But the low frequency effective coupling will be suppressed by this log. And even if G is large, G will cancel. So it's pretty universal. So it's 1 over density of states times log. Well, if I multiply coupling constant by the Fermi density of states, which I will get from the BCS type expressions, well, then G rho F will cancel, and the answer is 1 over log. But the ratio between Fermi energy and dBi frequency is typical of few hundred easily. So the log is 4 to 5. So expect that, well, your effective coupling constant will be, I know, below 0.2. And this can be easily now overcome by the electron phonon coupling. You can start with strong Coulomb repulsion, but close to the Fermi surface in the Cooper channel, those strong Coulomb repulsion is reduced to a small number. So that's the argument. But just keep it in mind and then just forget everything. Well, this is what was done by them, just to argue, okay, that's how it actually happens in metals. Once you talk about effective Coulomb repulsion, maybe it is smaller than the effective repulsion attraction between the electrons and phonons, and ultimately you'll get it. But let me just go back to my equation and keep, yeah.
I'm just curious, suppose that you take a diagram in your Born series, which is not part of the Born series. Let's say at the second order, we would take rainbow diagram or
I'll come to this.
So if a quick answer, so in terms of this parameter lambda, how does that diagram not include its scales with this?
Yeah. That's precisely the puzzle. It's lecture number 2. Unfortunately, if I answer it now, then I'm just jumping ahead. I'm just creating a suspense, small one.
So just to so lambda is G times density of states. This is your lambda, right?
Effective lambda is G times density of state. Renormalized density of state and times the Z factor squared as well. If we care about
At this level, lambda is smaller than 1, that justifies this work of the system.
Okay, so now just let's try to solve the following model. Again, this was done by Rachel and Sham. It's exactly solvable. They were not doing kind of Bogoliubov type of approximation. They just went to the gap function equation, which we use for BCS, the basic one. They say, okay, let's change the model. View BCS was attraction, minus G up to frequency omega. Now I will change the model to the following one. I have pure repulsion everywhere. And my pure repulsion is G if I am in the dark blue. But it's slightly reduced, so my F is less than 1. So my repulsive interaction is strong everywhere at high frequencies, but my repulsive interaction is slightly weaker by some factor of F, maybe 0.5, maybe 0.8. But in this lighter blue region, my repulsive interaction is slightly reduced. So what do we have in this model if we try to solve the largest eigenvalue equation? Now I'm talking about pure repulsion, but simply my repulsion is weaker at lower frequencies. Again, it's the same model, and difficulty is no different from BCS. And for Green's functions, I assume the Green's functions are very lucky. Just don't even bother. Okay. So we don't change anything for the Green's function. Well, this is my gap function equation, but see, gamma is written again in such a way that gamma is a number which cannot produce any dependence in terms of momenta on delta. So I will erase momenta, which means I can take the sum over k from the two Green's functions. Again, nothing depends on the momentum. But in terms of frequencies, gamma is only a piecewise function. So just one coefficient for low frequency, the other coefficient for high frequency. So which means the solution of this matrix is nothing but 2 by 2. So I will simply introduce, because gamma can be pulled out from the sum, each time when I decide whether M is small frequency or high frequency, I'll just put different gamma, either G or FG. So, and then I will face C, the product of two Green's functions. So if I sum up through high frequencies, this is rho F log Fermi energy divided by omega, according to my picture. Well, but if I am going to frequencies smaller than omega, then I'll just do this, and this scales as log of 1 over 3. Okay, so that's the model. If I introduce those two, just because of the properties of my gamma, which cannot project indices on this one, delta is really a simple solution. Delta has only two components. Delta as a function of frequency is one number for low frequency, another number for high frequency. You will figure out that it will actually change sign at frequency omega. So there will be a 0 in the delta. But this is now just 2 by 2 solution. Literally, you start reading it. Alpha high frequency. Okay, if it's high frequency, I can connect it to high frequency, but then it's just this small L because everything goes through G. Well, but the high frequency also can be connected to low frequency because I put here low frequency and then the product of two Green's functions, and this is G. Because I'm connecting high frequency to low frequency, this is involving high frequency on one end, so this is definitely original G. And then you look the same what happens for the low frequency component. It's G again if I connect to high frequency, but if I go from low to low, yeah, it's FG. Everywhere it's repulsion, repulsion, repulsion. But this is 2 by 2, and now you can solve it. Yeah, formally I'm done, so I'm introducing now the homework. Yeah, so the homework goes as follows. We have this model, which I just discussed, and I told you that it's no more difficult than solving 2 by 2. You can easily do it. So consider two superconducting models. Superconducting model number 1. All attractive, you'll figure out it's actually superconducting. No matter that it's repulsive everywhere, it's superconducting. So the first model says, okay, my gamma, effective gamma times the density of state. So this is minus 0.5, and that is simply smaller by a factor of 2 at some frequency, which is 100 times smaller. You'll have some TC, please find it. You have another mechanism, which is attractive, and then goes to 0 at low frequency. So I'm attractive at high frequency, and then nothing at low frequency. Call it anti-BCS. So you attract at high frequencies, and there is no attraction whatsoever. There's no coupling at low frequency. It's also superconducting. Please find TC. You can also check how eigenvalues, eigenvalue disappeared for some, okay, it's here. So eigenvalues, how they depend on temperature. And you will discover this is not like BCS. They are not linear functions of log T. They're highly nonlinear functions of the log. So please plot them. And then ultimately combine the two mechanisms. Take this gamma plus this gamma, take them together, and also compute TC, what TC is. So literally the project is consider two different mechanisms, compute TC for them, see how the lambda of T behaves, then combine two superconducting mechanisms together and find out the TC from the combination. Yeah, I'll help.
I think we spoke at some point. So is model A interaction is attractive, right?
Model A, it's a repulsive interaction.
So you minus sign means repulsion here, or attraction.
Yeah. Oh, sorry. Yeah, probably I just did it wrong, right? Yeah. Sorry. My bad in terms of how I formulated the equation. Yes, so far I was always writing down minus and then gamma. So when I just say, okay, solve this equation with this gamma, I mean literally solve this equation. So this is repulsive, this is attractive because, yeah, sorry.
Okay.
I can put here minus and then flip the sign everywhere. Yeah, sorry. Because my point was just solve this equation with those conditions. Yeah, sorry.
Like 5-10 minutes for questions.
Yeah, first of all.
The electron phonon case, what is the prefactor for TC? Is it prefactor? If you compute TC there, what is the numerical prefactor you get?
Okay, numerical prefactor typically happens to be, okay, the question was if we do real electron phonon coupling, we say typical Debye temperature and finish the calculation for TC, what is the prefactor in front of the exponent? Debye temperature typically divided by 20. Not 1.13, but Debye temperature divided by 20.
So it depends on the Debye temperature.
No, it just depends how you cut off the log and all the details. But if you just do actual numerical calculation, the prefactor happens to be relatively small.
I mean, that capital omega divided by 20.
Yeah. So TC will be capital omega divided by 20 roughly, E minus the rest.
Maybe I can ask again the question which I had before in what you
Oh,
showed.
sorry,
on the
probably
previous
not
slide.
sorry, Andrey. Not E minus, not divided by 20.
No.
It's divided by maybe 5, assuming that the exponent also contribute. Yeah, sorry. When I was saying omega divided by 20, this was the maximum possible value. So I didn't quote correctly. No, the prefactor is much bigger. Say, call it omega divided by 2 pi, and then the exponent.
Maybe just to emphasize one point of what you said. Can you go back to previous transparency when you showed the gap functions that change sign? Yes, this one. So going back to what you started with, when you said that if you look at susceptibility with respect to bare delta, I assume here if you take bare delta at a time some function delta naught and take it frequency with not changing sign as a function of
Yeah,
frequency,
absolutely.
then the susceptibility will never diverge. You need to have particular subset of delta naughts for which you will get this behavior.
Yeah. But formally, the calculation of lambda maximum has nothing to do with this delta naught. I'm simply looking for the largest eigenvalue, which doesn't care about this delta naught equation. But let's say, but probably if you initialize some symmetry channel, that's initializing the symmetry channel. But formally, this calculation just doesn't care.
Sure.
Yeah.
What to connect to part of your talk.
Initially, when you were talking about finding the singularity in the derivative, you talked about saying that you needed to look for the largest eigenvalue that hits 1.
Yeah.
What happens if that eigenvalue just goes past 1 altogether?
Say again, I need 1, but what happens
what
if
happens if that? Maybe I'm asking a silly question. What happens if that eigenvalue goes well past
beyond? It's probably superconductor now.
but you don't see the singularity?
Oh. You see, at this point, once I have a singular response, the entire calculation has to be rewritten, because when I just introduced the entire calculation, I was doing it assuming that delta is going to 0. Because you see how my equation is written. It's delta. If it's normal state, it's reacting only to eta. So it's as small as you want, which means you do everything as a linear function of delta, because delta is proportional to eta, unless it's a singular response. Once the singular response happens, you have to take care that delta now is finite. It will modify the Green's function. And the moment you modify the Green's function, that's what you have for self-consistent calculation of the gap in the superconducting state. You will reproduce the calculation for the gap in the BCS state, all the same expressions from Bogolyubov-Desjardins. But for this, you already have to renormalize the Green's function as well, introduce the gap in the Green's function, and be more careful. Because now the theory is not linear in delta. The moment delta is finite, you have to take care of delta everywhere. So everything is normal state up to TC, but not further. Once you go further, it's not linear response anymore. Yeah, essentially your linear response is over once the linear response is infinite.
Actually, I think he may want to ask in the normal state if the alpha can be larger than 1.
In the normal state, alpha cannot be larger than 1.
So actually, for the at least for the Hubbard model, recent year people find that the irreducible Vertex function can be diverged in the normal state.
Are we talking about alpha or lambda? I'm just not sure.
Alpha.
Alpha? The largest eigenvalue?
Yeah.
No, it cannot.
Actually, there are some papers saying.
Maybe there are some papers, but yeah, then I have to read the fine print, what is defined and how.
I can show you.
Yeah.
Last question. When you discussed about this Coulomb interaction thing, when you integrate the high energy part, now when someone says Coulomb interaction is momentum 1/q square power,
Sure.
Yeah. Where does that appear?
Next lecture.
Or next lecture.
No, that's why I'm keeping everything kind of simple. But once you solve this model, pay attention to what I was talking about, Bogolyubov, Sherkov, and Tolmachov. Next lecture, I'll say, okay, well, now let's go to Coulomb interactions and just do a better job. So the better job will happen next lecture. So this is kind of to introducing to something which is simple models, which you can easily solve, enjoy, and just learn some of the lessons. Because once you solve this one, you will see that a pure repulsive model suddenly gives you TC. Because, okay, well, this is the mechanism H. And you will learn that, okay, combining two mechanisms produces unusual results. And you have to think about this now just deeper when you face the Coulomb interaction. Yeah. Just
Sorry, just one more question. So when we this time we sum over the frequency, we compare it as a Fermi energy. Is the same reason as the previous one?
it's different because well, so one is truncated at omega, the other one is truncated at Fermi.
This setting by the
Just simply just because I'm using constants, something has to control the convergence of the sums. Because the sum goes as 1 over, okay, it's not here. This sum, it goes as like 1 over omega, only under the assumption that frequencies are less or comparable to Fermi energy.
Yeah, I mean, I just.
But I'm using a constant. So otherwise you would say if it's untruncated, it goes to infinity.
Yeah, but why
So
not?
I have to truncate.
Why not like 2 of the Fermi energy? 2 times. Yeah.
It's a model. If you say 2, I will ask the question, okay, why 2? Why not 1.5? So this just 1 is the good number. Yes, you can easily make it 1.5. Totally agree. You can do that.
Okay.
Yeah. No, this is just pure simplicity of the formulation, nothing else. There is no deep anything.
It's not a question, it's just a request. Since we record everything, when you ask a question, try to ask as loudly as you.
Oh, yeah, sorry. Yeah, I keep forgetting. Yeah, the question was why I'm truncating here at Fermi energy, but not say 2 Fermi energy or some other number. The answer is introduce any number you like. It's as good. This is a repulsive. Yeah.
So yeah,
Create 1 minus g rho goes, yeah, it's minus. This will start creating a singularity, which is precisely the proof singularity.
I don't know, I think
Yeah. But this is superconduction instability. Because I'm now doing the entire level in the group channel, that's what gives you the. As for repulsive case, it simply makes effective interaction for energy weaker.
but it was
Effective interaction gets stronger. But effective repulsion gets weaker. If you have attractive interaction, if you lose the frequency in the Cooper channel, they effectively are getting strong. And ultimately they will. Yeah, formally you can start writing RG because we have one.
The R solution. Just you need to go to strong power.
Are you presenting an impulse?
Coupling because of a case what is partially lower without any chemical.
Yeah.
No.
Simply Rachel and Shem were precise in mathematical calculations that you can solve it exactly. So to finish the job. And Anderson was simply repeating Bogolyubov. We didn't do anything new. Anderson model, nothing new. They just repeated Bogolyubov, but in a made transparent way. So they did it transparently, and that's why it kind of became popular.
Localized state solution, like some imaginary.
Because I know this
Changes time. Essentially, this model is exactly solvable, but it's introducing this one. It just says, yeah, you protect the function, and then you say, okay, yeah, but at low frequency, you make it slightly smaller. So it's exactly the same model as Rachel Shams. but this is kind of in words. Introduce effective links and then add the electron phonon attraction, and suddenly you see movable attraction. Rachel Sham says, okay, here's the model, just solve it exactly. What's the advantage is that you can see how the eigenvalues behave. And they behave ugly. Because when you do BCS, you definitely might be STC 10 minus 10 Kelvin. But I can only do calculations say up to 10 minus 5 Kelvin. Okay, yeah, but I will extrapolate because with G, extrapolate. You'll follow this model and you'll see it's unextrapolated. Because that's what you have. This is BCS. BCS has alpha T, this is most 1 over T, this is grows, and ultimately choose 1. And suppose those are your, yeah, this is 50. Yeah, I'm only interested in approach. You do this, you take Rachel Sham model, you solve for alpha T, and your function behaves like this. Question, is it superconducting?
So I have a couple of.
That's the problem. So maybe it behaves like this. And there is no. But your data are only available here. This is 10 minus 5. There is no branch, I'm changing.
Yeah.
So this is BCS.
Yeah.
Pure attraction, nothing else. This is Rachel Sham model, and the effective filtering is repulsive everywhere, but weaker. This is FG, and this is my gain, repulsive, no attraction. That's how the eigenvalue, the largest eigenvalue will be. I don't know. Those are that's my latest thought. I don't know what to do. You say, okay, yeah, extrapolate, and maybe it will cost 1 because it's different physics. If it crosses 1, it's superconductor, but if it doesn't, it's not a superconductor.
But if you can interesting,
You can look at the entire spectrum as well. In Rachel Sham model, there are only 2 eigenvalues because it's 2 by 2. If you do a model with continuous frequency dependence, there is a continuous spectrum. So there will be this eigenvalue that's the largest, there is another eigenvalue, and maybe the whole continuum. If you have pure repulsion, or pure repulsion, alpha T, 1, it will keep increasing, but it will never reach 1.
Yeah, no, it's, I actually.
Probably I would say it will keep increasing if I have F less than 1. But probably if you have pure repulsion, yeah, if it's pure repulsion and nothing else, your effective, it's not a straight line because the effective G simply goes to 0.
Side the way that they would cite it, not in the way I would say.
I didn't check. I say, step simply allows you to do an analytic solution easily. The moment it reduces, switch to numeric. You can use it. No, it doesn't. No, it doesn't. This one is the same as weak at low frequencies, and this is typical frequency. No, it doesn't. It's simply for exact solution. Because the moment you have exact solutions, you understand that there is no way you can escape it. If you have numerical solution, you can argue whether I did a bug or how general it is. But the exact solution is okay, you have to live with this. And kind of it has to be somewhere in your brain that this is part of the
Like zero. Yeah. Then they made them like in I see. Okay.
It's epsilon here, yeah, because everything is close to the same extent.
They're equivalent here.
Well, you see when you integrate this one, it's inverse tangent function. So it behaves like 1 over omega and then saturates frequency. It's not nice. But if you, but in reality, this was D3K, omega plus epsilon K minus S.
This will.
Okay. So this one will be K to K to power. Yeah, because this is ultimately, if I do continue, of course, it's binding model. So suppose this is side binding model, and I just integrate. Now you go to very high frequency. I say, okay, this is 1 over omega squared. Let's do side binding model. This is some through the Brillouin zone, whatever. 1 over 30K minus mu squared. Some number. It starts decaying as 1 over omega squared. So instead of 1 omega,
So what they did is that.
its frequency is bigger than the bandwidth. This will start decaying as 1 over omega squared. Oh, everybody else is listening.
What will have a current carrying state?
So what they do is that.
Sure, yeah.
It's convenient for them to back in their background.
Yeah.
As soon as you do that, it actually cancels the diagram to any. So I should, it makes your
This was something
actually found so if you don't really have to say
along the direction.
This interval, it's also non-zero, but it contains an additional subversion information. So there, so if you recall that the same answer was linear regression, which is incorrect. And there is this interceptor cancellation. So it appears either to the cubic order. So
What we have for so you just we consider
So this I can figure out that this
so okay so people when they usually talk about this
I feel like this model was
but when they apply an experimental mechanism so time reversal and inversion is in so we were thinking about this problem as like a little bit more general like let's just consider systems.
So let's say we get right let's say Rush and Ice you immediately cancel this.
Okay. I mean, I can like sort of review later, but essentially it's that it makes sense if you see the go back to or different facts, right? You have the electric dipole that breaks up inverse. You have the magnetic dipole.
It's not really, of course, right now it feels like a very overpopulated small pocket, so I still really the question is about interesting, but now I can't. It's that's sometimes the threshold and it's place. Good job. That's fine. But anyhow, I just wanted to tell you that I really appreciate that paper very much.
You assume that this order exists along with this. We actually found states where running in one direction and the gradient, the derivative of the phase gradient is not parallel. We have a transverse component. So the consequence.
No, I actually some peaks. I mean,
So the basically along the high symmetry direction like opposite to the high symmetry direction
because of to your point, I think there are interesting, I believe, questions about manifestation of this higher point of view.
performance invariance. In the dynamic responses, let's say things like galvanic effects. And you look at finite frequency non-reciprocal responses, but you need a nonlinear probe to probe this vector structure of all of this.
Yeah.
But then it gets more involved. So superconductivity is.
It does feel more involved. I always said so.
You throw a term out like full galvanic effect, and I have to sit down, write down what exactly is that was, and then.
It's also a lot of semantic considerations, but I'm trying to pick up this.
Actually, what we are in our
Navigation tool.
Yeah.
All of this.
And the question we ask is what's the largest current for which I want to have a supervisor? Yeah, yeah.
Contact me and I can help.
Yeah, I was more or less open to bluntly ask people who have an interest to
So the
sort of
current
help with the symmetry required to plus this thing. So I because I think that the 99 yeah, I was just graduated.
I don't know anything about
Wonderful. So maybe you know the I know something. He was a student here in Dania.
They do know
things. And he also loved so so I feel like this probably is for his question. Like it's something that he would enjoy to make.
the function of the things is how
Yeah, there is a separate line we are pushing with Maxim for all of this.
I
Small mechanism. And I would like to maybe to.
Yeah. Yeah, sure. We had some follow-up work on this fall. Really the function is a story, so it looks like generically info. So I now actually read the story. So you understand really important. So. Yeah. So now I understand that. We made an argument early on that the model is always linear in spin. But that argument is different than what you had because we did not worry about any. So it is sort of in that sense it's slightly different from your contribution. But nevertheless, it's linear. Then we ask the
no, there's no
question.
non, yeah,
So if you.
the behavior is not,
You can
it's
also.
analytical in the sense that there is no weird term. But there are these additional, so because of this additional order that I have.
So we, there are DFT and we saw that.
So if these terms are not there, then basically A of your superconductivity. Yeah.
And so we try to, we
do it
try to
for
address.
one that has the minimization.
That's what I'm sorry. So we don't work in a limit where we have.
Yeah.
In an orbit.
Space.
Then you also don't work in the limit where you make.
Social and
Yeah.
And then you have some sort of beauty actions around that. Those symmetry
Current makes a one gradient finder.
Yeah, yeah.
Versus large.
So that's.
So it's not really an on the small, but it's.
So, very.
So we need to be able to control the weight.
So what you get between this is gradient that you're developing and access.
Yeah, sure. That's the, let's go. Yeah, because the problem itself, the problem itself should be.
It's your current was flowing this for lenses. Sorry, this was your sample. It's changing this. What is changing is happening is that where this direction is dependent on. First, you can always this direction. So
I will not solve it completely, but I will, yes, I'll give some answers.
Good, somehow.
So
You
this
can have
is the
correct
story like
point
that,
of view.
like if you do this with the solve the gap equation with Coulomb interaction, it comes out something attractive.
Yeah.
I think I have, was this part of, I don't know, Tao's friend's defense, what's his name? He graduated.
Yeah.
Because this looks very familiar to, I think, what both of them presented in their defense.
Yes.
Yeah, so this is.
No, that's their PhD.
That's their piece.
That's why you cannot read it anyway.
So technically I'm monitoring the.
Very recent development.
As a function.
No, you see,
of the
this part is not recent.
Oh, just what's the
This
current?
was
Yeah.
done by people.
No,
in the
definitely,
past, like
definitely, you can do that because.
But they did it only for say.
Yes, we have like analytical forms for.
Our
for
students,
this,
they did it for
because-
all possible channels.
Yes, sure.
2D, 3D. And then start doing
What
vertex
we use
corrections and see how they make pictures.
whether there's an analytical form or what is that?
This is just, again, of course,
Just.
just
if you
forms
can
the potential,
plot it,
looks like.
Don't need to be.
And completely.
Sure.
And that is for science. Science.
Right.
I just want the.
So then how do you explain the real science it is?
I see.
With
So,
calculation, well done
like, so
calculations.
say you have your
Science says no, we're
mass
using physiologically
which,
possible.
so
So you have to
and
explain
it's
how
not
to
like
why
m
it's technically possible,
that's
while
where
calculations that it's.
theta over by 2 and superconducting water parameter something like theta q dot I. So this is the sort of concepts that we are working with this.
Gradient.
Question, when you say
Yeah,
channel.
gradients, yeah.
So when Green's function.
Essentially,
No,
m
this
is,
channel.
m can be
Because
represented
the
as
S way,
unit
P way,
parameter
P
plus
way.
q squared
The L
plus this beta
L
cube
different
cube.
elements, yeah.
So essentially,
Oh, yeah,
this
the
cube
general
term is it's the weird term
General
that's giving rise to your, so essentially,
Different.
yeah, so this J, which is, okay, so in the ordered state, f is basically minus n
So
squared over
somebody can do what Daniels.
and J, which is del f over
It's
del
dependent on those.
Q.
Based on that, you.
This basically depends on, this becomes proportional to both Q plus, 3 beta Q cube times the mass, so, sorry, Q squared. So this is the sort of, weird term that.
Usually when it is program is diversion.
For an entire week. Yeah. It's fine.
Yeah, but yeah.
Because they just said, okay, homework, so which means they're on 3, 4. I don't know. I don't know how many homework schools.
If there's it. Before the signals that
Yeah, but this is the only example. First grade. And they're they are too technical. Otherwise, we can finish those things, we can all publish something.
Yeah. So basically, I had on top of you, captain James. And this is
George.
I was there.
Yes.
Which year? I did really go damaging the.
January the 5th or.
Oh, I was on stand. So, no, I remember this was in technology, right?
Yes, everything about FCI and that. The first time I've over there, he's my vice.
Oh, question how to propose it. No, but.
Should work.
You have to come there and if there's a gamma, then if something fun happens. Then you can have an effective. I think it's a topical that's not
Anything about this space?
Why not? Yeah, absolutely. Hello, everyone. Welcome to our afternoon session. We have our speaker, Professor Andrey Chubukov, who's going to talk about
Superconductivity. What else? Yes. Okay, look, first of all, again, great to see all of you. I was a little bit down. Yeah. I was a little bit afraid that Nikolay and I would be talking about the same stuff and was ready to completely change my lecture during the lunch break, but fortunately it's not exactly the same. So you will hear similar story, very similar story, but I'll try to put it differently because it will be important for me when we start moving into somewhat different direction. So let me start with this. The way how superconductivity is presented in the previous lecture was essentially calculation of TC. And pretty much I will be doing similar thing. But let me try to formulate it slightly differently, and then you will see why I go this way. So let me look at the system of interacting fermions. So we're talking about the very beginning of theory of superconductivity. So we pretend that we don't know anything about superconducting instability and just want to look at the system of interacting fermions at zero temperature. And let me remind you something again related to diagrammatics, but a little bit more than just also to diagrammatics. That properties of single fermionic excitation, spin 1/2 excitations, are described by fermionic green function, which is generally functional frequency and momentum keep. I occasionally will switch between real frequency and Matsubara frequency, but I'll try to keep you updated on which frequency I will be using. In what sense they're determined by green functions? Poles of the green function determine your elementary excitation. If you have free fermions, your green function of a free fermions is 1 over omega minus epsilon k minus mu, which very often I will just write as epsilon k, meaning that chemical potential is absorbed into dispersion. And obviously then when omega equal to epsilon, this is where the pole of the green function is. So something that you will know. But of course it works also for interacting systems. So poles of fermionic excitations are pole of a single particle green function. Collective excitation, zonic excitation for a system of interacting fermions, are pole of what is called vortex function. Vortex function is related to two particle green function, but in a simple relation, but still they're not identical. So when we talk about two particle green function, we normally call it gamma. And here is how we define it. We take fully dressed interaction between particles K, P prime, with obviously momentum conservation is assumed. And even here, I will put K as combined notation for momentum and frequency. So this interaction generally depends on both momentum and frequency. Not necessarily always on momentum transfer. It can also depend in principle on total momentum if consider lattice systems with orbital degrees of freedom, etc. So this is fully dressed interaction, including all channels. Spin indices, alpha, beta, gamma, delta. Interaction preserves spin. This is how original Coulomb interaction, which is charge into density interaction, is arranged. And so spin structure of this quantity is delta alpha beta, delta gamma delta, meaning that spin index along the interaction line is preserved. Vortex function is what's called anti-symmetrized interaction, and the anti-symmetrization is nothing but reflection of Pauli principle. I can take these two fermions, interchange them. When I interchange their momenta, frequencies, and spin. So with minus, of course, I change sign when I interchange two fermions. And so minus same fully dressed interaction with momentum k, p prime, right? K prime and p, but most important is that this is alpha delta, this is gamma, gamma and beta, and this is delta alpha delta, delta beta gamma. So there are two terms with different spin structure, and for superconductivity it will be important. Spin structure will play a role, as you heard in both previous lectures today. Again, this is fully dressed interaction, this is fully dressed interaction, so we need to calculate each of them. But when we look at this object, how should I write it down? Let me write this object as something like this, meaning anti-symmetrized. Poles of this object determine all collective excitations in the system. In particular, information about all electronic instabilities are embedded into this function. Now, why I'm saying this? Because let's remind you something that we all know, that collective excitation in a fermionic systems have two possibilities. Either when I hit the system and force electron to vibrate collectively, then there are two possibilities. One, collective excitation decay exponentially. This is where the system is stable, right? I put in some perturbation, perturbation decays with time. This stability of a system. Or I put in perturbation and they start exponentially grow with time. This is instability of a system. And mathematically, it reflects in this way, that generally gamma, in the simplest case, gamma is a function of external frequency that is coming in here. Sorry, I have to be more careful. It can be a function of both transverse frequency. Okay, let me just throw it in concrete example. This gamma is generally a function of two variables, both frequency and momentum. Let me put it in terms of k, and you will see immediately. It's a function of k plus k prime, and also k minus p. I defined it like this. I put the same notation here, kp, k prime, p prime, despite that this is anti-symmetrized interaction. So here's what I want to say, that all poles are somewhere in frequency, and system is stable if the poles are in the lower half plane of complex frequency. Because what it means that if I take Fourier transform and then look at time dependence of perturbations, they will decay exponentially. Danger of a system and instability of a system is when a pole moved from lower half plane to upper half plane of frequency. Any pole in the upper half plane of frequency means causality is broken. Actually, the pole in the lower half plane means causality, that the function is completely analytic in the upper half plane, which basically means that reaction will be after action. A good example of singular behavior of the vortex function, which doesn't.
There's a question here.
Oh, yeah, sorry, go ahead.
Singularities in the upper half.
Sorry, try to speak loudly, both for a recording and for me.
This is specifically for the ordered Green's function, right? Not the time ordered one?
This is so far time ordered Green function. So far, this time ordered.
But doesn't.
Oh, sorry. When I said, sorry, my fault. When I talk about poles in the lower and the upper half plane, of course, it's retarded.
Okay.
Retarded, of course. Sorry. Of course. Very good. Good. So, simplest example, when the system has singular behavior of the vortex function, but it's completely stable, is what is called zero sound mode in a system of interacting fermions. vertex function as a function of transverse frequency, or let's call it omega k minus omega p, and transverse momenta k minus p goes as, let's call this quantity omega, let's call this quantity q. It goes as omega plus I delta square minus v square q squared, where v is close to the Fermi velocity, but slightly large. You probably saw this many times in courses on solid state physics. These are normal sound-like excitations in a system of interacting fermions at zero temperature. At finite temperatures, there is a sound. At zero temperature, this is what calls it zero sound. And this is the dispersion of zero sound. This is how gamma behaves. You notice immediately that, yes, there are poles here, but poles as at omega equal to plus minus VQ minus I delta. Minus is important. Pole is in the lower half plane. Causality is not broken, right? I'm talking about this because you will see that in a particle channel situation is different. So again, we're at zero temperature, and we want to do what Nikolay did in his lectures. But I want to do it slightly differently. I will not introduce at this moment some infinitesimally small order parameter and then check reaction, although we could do it. I will just look at the function itself and see what this function is. So here's what we're going to do. We are going to do simplest case, weak coupling and constant interactions. This is what we start with. So which means that what I label as fully dressed interaction will be to first order, will be just, let's put it like this, just interaction which I label as U. And at this stage, I don't care what the sign is. We'll just look at this interaction and talk about the sign later. Then gamma, let's call it gamma naught or gamma 1 to first order, will be equal to U delta alpha beta delta gamma delta minus delta alpha delta delta beta gamma. Very good. And then I'm going to go to higher order. And just as Nikolay did in his lecture, I'm going to focus on a particular channel of interaction between fermions, which is called in particle-particle channel. Namely, I want to add series of direction to interaction, which contain two fermions moving in the same direction. Later in the next lecture, we'll consider what constitutes this line when I go beyond weak coupling. And this will be the story about Kohn-Latinger, superconductivity, etc. But at this stage, what we do is just simple ladder, right? Simple ladder summation. Contrary to what was done in a previous lecture, I want to keep frequency and at some point momentum, total frequency and total momentum non-zero. Let me at least keep total frequencies non-zero. Namely, in terms of notations that I used here, it will be k plus q over 2 minus k plus q over 2, which means that q is the total momentum. And as I said, with this notation, it's also total frequency on these two fermions. To make my presentation easier for you, let me first assume that only frequency matters. So there will be some frequency incoming in each of these graphs. And so what I have to do is to calculate the product of two green functions. Let's put there, again, momentum and frequency, L plus Q over 2 minus L plus Q over 2. And it's simple exercise to calculate the product of these two green functions and see what you get as a result. So when you do this, you find interesting result. That, of course, as we all know now, there is a logarithmical singularity in this channel. If you take two fermions with almost opposite momenta, here it's exactly opposite momenta. Remember, this only frequency component. Let's put this. Okay, omega, that's enough. If I put fermions with momenta L minus L, but allow their frequencies to vary a little bit to the extent of external omega. Then I will get interesting result for this quantity, which I call particle-particle polarization, which is nothing but the product of these two green functions integrated over intermediate frequency and momentum. And this quantity will be equal to minus MEF in 3 dimensions over 2 pi square 1/2 log of what? Just like we discussed in the previous lecture, I need to put some upper cutoff in the theory. Otherwise, I will have infrared divergence, ultraviolet divergence, sorry. So let me put cutoff such that U as a function of frequency will go up to some omega naught and then disappear. You will see later that it's completely unnecessary, but let's do it here. So you get log omega naught square over omega square plus I pi over 2 sine omega. Good exercise. I will not put it as an exercise, but it's a good thing to calculate this data. Very good. Then what I need to do? Every time when I see interaction U, this is U, this is U, and you do it all the times using standard rule of diagrammatic technique. Each green function is equal, each line is equal to IG. In the conventional case, its interaction is minus IU, and etc., etc., or beauty of diagrammatic technique. And you get gamma when you sum up ladder series of graphs. In the form, let's call it U bar, still delta alpha beta delta gamma delta minus delta alpha delta delta beta gamma, which is nothing but singlet configuration of two fermions. It's antisymmetric over spins. And the quantity U bar, let me move to that part of them. U bar will be equal to U 1 plus MUPF. I use P or K. Let's say PF, right? Over 2 pi square. And this is the same quantity, 1/2 log omega naught square over omega square plus I pi over 2 sine omega. You will see in a second why I keep this I factors. Very good. The rest is obvious. You want to say, well, what happens if U is positive? Means repulsive interaction. Yeah, go ahead.
What is omega naught and what is big omega again?
No, omega naught is this one.
Ah, I see. Okay.
Big omega is what I put in.
Okay, thank you.
So if you want, in terms of frequency, this will be omega L plus omega over 2, and this will be minus omega L plus omega over 2. I integrate over L. Now Q is equal to 0, so I put it like this, right? L and minus L and almost opposite frequencies. This is why I never have infinity. Everything is cut here, even at 0 temperature. But I want to do a very simple exercise. I want to see where is the pole. Obviously, when I solve for this, at some point, denominator goes to 0. And if U is positive, means repulsive interaction, then we don't need to worry when denominator goes to 0, because this is the leading term. It's obviously positive. This is positive, so I have a denominator 1 plus something positive. There is actually a pole at very large frequencies where we actually all approach is failing, so we don't need to worry about it. But if we formulate this stage, assume that U is negative, that you have attractive interaction, then of course you immediately see that forget about this, that when this stuff times log is equal to 1, you get 0. Just like you get 0 at 0 sound, right? And the only question is where is the pole? Because of this guy, which is present, we cannot have pole on real axis. And simple exercise shows that the pole is actually on imaginary axis. The question is where. And I leave it as another exercise. What will happen if I solve this equation in complex frequency, which has both real and imaginary part, and you find out that the pole, omega pole, is equal to I times some quantity B, and the quantity B is equal to I omega naught e to minus 1 over lambda when lambda is equal to m u mod u pf over 4 over before or 2 pi squared. Let's see very quickly. Over 2 pi squared. Everything is fine. Very good. Where is the pole? In the upper half plane. This instability. So we can immediately look at zero temperature, do a standard analysis for interacting fermi, and find out that something is going wrong. That we have pole in the upper half plane, which means that any perturbation when we introduce two fermions and create essentially trial order parameter in the form of, say, psi-Dyer, this perturbation will exponentially grow with time. This is what superconductivity is. Well, this is what pairing instability is. Let's put it this way. Okay, then again, from this quantity, you can go to time dependence and find out that for pole like this, perturbation exponential grow with time. Very good. Interestingly, we can ask a question, what happens if Q is non-zero? If the total momentum of a pair is non-zero? And then you find that in fact situation changes. By the way, near the pole, let's put it first of all, near the pole. Near the pole, U bar, which is the same as gamma, they differ only by spin structure. Scales as 1 over omega minus IB. B is here. So obviously, the pole is obvious. But if Q is not equal to 0, it turns out the pole starts moving. And if you look at the position of the pole, so it will be B of Q as a function of Q. Position of the pole when Q becomes non-zero. We start with this, when this is B, if Q is equal to 0, and then it goes like this. Crosses 0 at VFQ in 3 dimension equal to square root of 6 times B. What is this? This means that everything is fine now, right? The pole now is a lower half plane, which means that instability involves only fermions which are moving in almost opposite direction. That when I allow two fermions to move together, which means that when I create a current and form all fermions to move into the same direction, I get a critical current when I lose this effect. The system becomes stable again. And this is nice because this all can be obtained without even thinking, what should I put in? You clearly see that something going wrong. And yeah.
Just one more time, like the physical meaning of negative.
Physical meaning of negative B.
I mean the pole. The pole is lower
the pole. When the pole goes into negative B,
yeah,
means that everything is now fine. The pole is in the lower half plane. Causality is now satisfied, which means that the normal state is fine, just like a zero sound.
Great. So if I will rewrite this B in terms of delta, so this critical value of Q corresponding to a critical current destroying superconducting state, is it what it is?
Yeah.
Physically, yeah?
Yeah.
So it's like,
yeah.
Okay.
But I probably said, didn't I say this?
I'm not sure. Maybe.
Okay, then I said it for myself. Okay, good. Good. Now, since somebody has to say a few words about BCS, let me just put two formulas about what happens when there is instability. So now I want to look again at t equal to 0, I know q is equal to 0. I take omega very small, so there is instability of the normal state of interacting fermions, and we need to find out how to cure this instability. And for this, of course, I need to rely to Nikolay's lecture that you know which susceptibility diverges. What I showed you can be easily figured out in the same way by looking at susceptibility as the reaction to some external perturbation. And obviously what happens is that the quantity which is minus u over n is the number of particles, sum over k, bk dagger up, b minus k dagger down is called delta, and it's not equal to 0. And it's equal to u over n, right? Sum over k, b dagger k down, b minus k up dagger, which means that, of course, if I change spin to minus spin, order parameter changes sign. It's spin singlet. Good thing to remember is that this delta is determined up to a phase. So when we look at what comes out of calculations, only mod delta appears in calculations, phase doesn't appear, and this gives the reason for phase fluctuations and all beautiful physics associated with phase fluctuation. But at this stage, let's do simple mean field analysis. Namely, let's assume for simplicity that delta is real. We know that this order, we don't know. We assume that this order is non-zero. We look at the Hamiltonian of interacting fermions, which is sum over k, epsilon k, bk dagger bk alpha, sum alpha. When alpha is up, down, obviously, then we write down plus u over n, sum over b dagger k1 up, b dagger k2 down, bk3 down, bk4 up, which is nothing but density interaction written like this. I could take this fermion and move it here without any problem. It's again density of fermions with spin up and density of fermions with spin down. This is how we write down standard Hubbard interaction. And use this stuff. Yeah.
Should momentum be conserved?
Absolutely, absolutely, absolutely. Sorry. Yes, of course. There is a conservation of momentum. What this means that K1 plus K2 equal to K3 plus K4. Obviously. Yeah, and the way how we normally do it in a mean field, we say let's decouple. Let's assume that most of fermions form bound pairs. Almost all of them. Then the leading term is when we create pair of this fermions and put it condensate. We take pair of this fermions, we put it in the condensate. And subleading terms is when we take only two fermions and put in condensate, and the others we keep outside of the condensate. The next term will be when all fermions are outside of the condensate, but this will be effect of the interaction. So what I'm doing this is really BCS theory in its purest form. When we take term u over n, b dagger, bb, so schematically, and write it down minus delta square n over u, minus delta, sum over k, bk dagger up, b minus k down, dagger plus bk down, b minus k up. And then what we do? Then we diagonalize quadratic form. We now have this term as a quadratic form. We have this term as a quadratic form. So something that I'm sure you did 20 times in your life at least, diagonalization of quadratic form. When you diagonalize of quadratic form, you go to new fermions. From fermions B, you go to fermion C. And then in terms of fermion C, your Hamiltonian will be equal to sum H naught plus sum over K, EK, CK dagger alpha, CK alpha. There's still degeneracy with respect to spin. And energy EK will be equal to square root of epsilon K squared plus mod delta squared. And again, when I write epsilon K, let's just write it as K square over 2m minus chemical potential, although of course I don't need to write K square over 2m. Any dispersion will work here. Very good. You all know this stuff. What you, yeah.
Where does the delta squared term go in when we find the energy?
You take this guy, put in the condensate. You take this guy, put it in the condensate.
No, I mean the delta squared n over u term. When you
Because remember, delta contains u.
Uh-huh.
So when I write this term, it will be some b dagger. It will be delta over u.
Yes.
Right? So I take delta over u square and then multiply 1 power by u.
Oh no, I mean, where does it go when we go from there to that final quasi-particle energy?
Here?
Yeah. Is it just?
I will come to this point in a second.
Okay.
It goes, there is a constant.
Yes.
Yeah, and it's important.
And you said delta is just real, right? Right now.
Yeah, I put more delta just to say that even if delta, if I put phase, the phase doesn't show up anywhere. Yes. I said at one point, let's assume that delta real. If I take the words back and say, let's not assume that delta real, you still get the same. And it's actually interesting to prove, to show that it's only mod delta that shows up in the expression. Very good. So what else we know from here? We don't know this guy, right? But we have self-consistent equation. So what we did? We assume that delta is there and try to write down equation on delta. How we do it? Well, we know relation between old fermions and new fermions, and therefore we can write down this quantity in terms of new fermions. And in terms of new fermions, what can be more simple than this Hamiltonian? This Hamiltonian shows that there are no new fermions at 0 temperature, right? Why? Energy is positive. Look at this. Square root of two quantities. It's positive quantity, right? So if I ask you how many fermions of C type are there at 0 temperature, no, their energy is positive, right? They don't. Density of fermions C doesn't conserve. It's only density of it's only number of fermions, original fermions is conserved. So what you do, you write down this quantity in terms of new fermions and not going into all computations. Well, it should be this stuff, yes. You get self-consistent equations in the form delta is equal to delta times lambda, which I already defined, log omega naught divided by delta. Let's put mod delta here. This is what you get. It's the first thing you get. Again, do it. I'm sure you did it before, but do it one more time. I mean that diagonalize this Hamiltonian, this term plus this term, right? You diagonalize by introducing linear transformation from old fermions to new fermions. Then rewrite this quantity in terms of new fermions. Use the fact that Ck alpha dagger, Ck alpha average is equal to 0 at 0 temperature because of positive energy. They're just no fermions, right? Their distribution is Fermi function with positive energy at t equal to 0, obviously 0. And then you will write this equation. You will get this equation, which is not surprising. You put something in, you want to get something out. Something out should be proportional to what you put in, right? So delta should be proportional to delta. And it looks like idiotic equation. What is the solution of this equation? One is obvious, delta equal to 0. Because if you put delta equal to 0, you go back to original problem. So delta equal to 0 is one solution. But another one is 1 equal to lambda log omega naught mod delta with logarithmical accuracy. I don't put the number under the log. There is some number under the log. Which means that it gives you delta. I will proportional because again, I didn't put number under the log. Omega naught e to minus 1 over lambda. And I remind you that the quantity B was also omega naught e to minus 1 over lambda. So these two quantities are comparable to each other. They differ by a number. Very good. No question so far, right? Very good. So We get second solution. We have two solutions. This is first one, this is the second one. The question is which one wins? And for this, of course, we need to look at this quantity. And it looks like everything is trivial, right? So question is what is H naught? H naught should show you energy of the ground state, right? And since I'm only dealing with equilibrium value of delta, which I already wrote from here, then I only have to compare two quantities. I have to compare H naught at delta equal to 0 and H naught at delta equal to, let's call it delta naught, and delta naught will be this one. Solution of this equation. And not surprisingly, of course, this one wins. You get lower energy. Simple, right? Very simple. With only one exception, that this is a wonderful example of anomaly. Because if you just use it as again as informal homework, calculate this quantity. And remember, we're at 0 temperature, right? Very good. So this quantity, H naught at delta equal to delta naught will be equal to integral over d omega equal to d psi, and psi will be equal to epsilon k minus mu, which I expand to linear order near kf. And here it will be quantity omega square minus psi square divided by something. And something will be function, in fact, it will be omega square plus psi square plus delta square, and overall factor here will be delta square. And let's put proportionality here. It's just to give you some entertainment. What is this integral? I have integral over one quantity and other quantity, right? As Nikolay explained, we can take integration over psi from minus infinity to infinity. We integrate over omega from minus infinity to infinity. So in fact, I'm asking you, what is the integral dA dB? A square minus b square times function of a square plus b square. What do you think? What is this integral?
0.
0, right? This is the first thing to say, 0, right? Yes, this is 0 times divergence. If you look at this integral, see how, right, I think it's should be square here, I'm sorry. 2 powers here give you 4, right? And there are 4 powers in denominator, which means the integral is logarithmically singular as the upper limit, right? And as always happens with the integrals which are formally 0 but singular, you need to shift this integral a little bit. How you shift it? You shift in a physical way. Omega is a variable which by definition at 0 temperature goes from minus infinity to infinity. Psi is dispersion. And if you put a system of A on any lattice, psi will be constrained, right? So the way to shift the integral and makes two variables not equal to each other is to put this as integral from minus lambda to lambda. And at the end of calculations, you will set lambda to infinity. If you do it like this, you find correct result. And I always make a joke, which I really like, that not long ago, but quite recently, in the last 10 years, there were 2 papers that calculated condensation energy. And one paper has right expression and integrated it like this. They obtained correct condensation energy. The other paper made a mistake. People made a mistake. And they put overall sign minus here. You know what they did? They knew what the correct result should be. So they said, let's do it differently. Let's assume that frequency is integrated in the finite limits and psi is integrated at infinite limits. So you can change 2 variables, right? You change the result, the sign again. Then they obtain correct results. Which means doing mistake 2 times, any integer number of times, any even number of times, right? Give you correct result. Okay, what's the result? After you do integration correctly, meaning integrate over frequency at infinite limits, integrate over dispersion and a finite limit. What nice thing is that you find the result will not depend on lambda. As long as you put any finite lambda, You can, after you put any finite lambda, you can integrate in any order you want. It's just easier to integrate over frequency first because integral is infinite limit.
You just have a different lambda already.
Which one? Oh, I put the integral from, I should be minus lambda to lambda. So did I put small lambda here? Yeah, I hope that I did put it like this. So anyway, condensation energy. Condensation energy, basically, this is what we need to answer. Who wins? And it turns out that H naught of delta naught is equal to minus number of particles, delta naught square over 2, times some quantity q. And this quantity q is equal to 1 over n sum over momentum, which you can translate into integral EP minus mod epsilon p divided by EP mod EP plus energy EP divided by EP. I must remind you that EP, should put it here, that EP is square root of epsilon t square plus delta square. Calculate this integral. You'll find this integral is 1. Again, funny thing. It looks that when delta equal to 0, right? This quantity and this quantity are the same, right? But there's divergence in denominator. And as a result, again, it's another example of anomaly. You keep non-zero number in numerator, and integration of in denominator will give you singularities that will eat up the number that you put in numerator. So this number, this 1, integral, but the most important part is a minus here, which means that you gain energy by introducing delta. And this closes the whole loop. Namely, you introduce, first of all, you know that the system is unstable at 0 temperature. You're asking us ourselves, against what? And in some sense, this is the assumption. We assume, with good reasoning to do this, that it's unstable towards introduction of spontaneous symmetry breaking and introduction of the condensate, when you put pairs of fermions in the condensate. You don't know whether you are lucky and you will lower the energy or not. In fact, many theories nowadays are done this way. We see that something happens with the system. We assume, we make reasonable assumptions that the result will be like this, and then we check whether the energy of the states that we get will be lower than the one we started with. Here, everything goes straightforward. The energy is lower than the energy of the normal state. Okay. Very good.
That n del square by 2 or n del square by u?
Say it again.
There are u there, n delta naught square by.
Nope.
Actually,
Nope. U is in delta naught square. U is in lambda.
Delta naught is energy, right? Delta naught is energy, right?
Delta naught is energy.
Energy square.
It should be density of states somewhere, right? It should be density. If I put it for particle, it should. Sorry?
It's in cubes.
It's in. Just a second. Let's see. Density of states is in cubes. Right. So I integrate. I do get density of states. Yeah, I think it's correct. It's correct. So it's not 1, it's a density. Very good. Most important is doesn't depend on delta. Condensation energy is proportional to delta naught square. Very good. Before I go further, and I will go further, I want to do 2 things. First, make strange connection to modern physics. Now, there's also physics of at least my generation. Well, one generation before. You can phrase, and this is what Nikolay already told you, that any effect of interaction can be generally measured as effect of fermions. We change dispersion of fermions, right? We don't need this, but we need Hamiltonian. H is equal to H naught plus sum over K, EK, K Geiger alpha, TKI. Energy is different from the one that we had before. And in fact, it's fundamentally different. Because if I plot as a function of momentum k, and this is what we call kf, pf, I use pf here. Pf is epsilon pf is equal to 0, which means pf squared over 2m is equal to chemical potential, which is obviously at 0 temperature, the same as Fermi energy. Then this quantity, if I plot epsilon k as a function of k, it will go something like this, right? This is my epsilon k. It goes through 0 at point k, and if k is smaller than pf, then energy is negative. This energy is always positive. So I had one energy like this, and that's it. Although, in fact, if you look carefully, what happens with this part? With the negative. So there is a connection between this part and this part when delta goes to 0. But there is no connection between this part and this part when delta goes to 0. One becomes opposite of the other, right? So in fact, what comes out is that if you look carefully, you find out that you plot excitations, you measure excitations as either electrons or hole. So energy is positive. When k is larger than kf, positive energy means I add them. When k is smaller than kf, states are occupied. So positive energy will be when I take electrons, there is empty state. Energy of the empty state compared to what was there is also positive. So I can write down the same energy with the negative sign. So if this is Ek, this is minus Ek. And then, of course, when delta goes to 0, this part becomes the same as negative part of the dashed line. And again, this part becomes the same as positive part of each hit. And meaning of all this is that if I now plot spectral function, imaginary part of the green functions of original fermions, imaginary part of the green function of original fermions, without superconductivity, this was my green function, E naught, which is 1 over omega, let's put it as retarded, omega plus I delta minus epsilon k. So if epsilon k is positive, the pole is at negative omega, right? If epsilon k is negative, the pole is at positive omega, right? So the pole is either here, and the pole is delta function, right? What's imaginary part of this part, by the way? Question to you. What's imaginary part of this green function? Imaginary part of G naught is equal to?
Negative I pi delta omega.
Say again?
Negative I pi.
Imaginary I already there. Minus pi delta function omega minus epsilon k, right? Yeah. So I think that, let me say again, because I think I misspoke. When epsilon k is positive, the pole is here as a function of omega. This when epsilon k larger than 0, and this will be the pole when epsilon k is negative, right? Either or, there is only one pole, right? If I now look what happens with the green function in a superconductor, then what I find is that there are two poles for any k. It turns out that for a superconductor, imaginary part of the green function, this is also imaginary part of the green function, this G naught, and this is G superconductor. How can I find this G? I diagonalize quadratic form, right? So I know the relation between new fermions and old fermions. What is the green function of C fermions? Green function of C fermions is equal to 1 over omega plus I delta minus Ek, right? Free fermions. But of course, when I write down green function of original fermions, it contains linear coefficients of linear transformation from old fermions to new fermions, which sometimes are called Bogoliubov coefficients, sometimes are called coherence factors, sometimes are called the origin of quantum geometry. So it's all stuff that comes in with the notation for this coefficient. So anyway, What happens is that at any k value, there are two peaks, delta functional peaks, but with different coefficients. This is called uk squared. This is called vk squared. And uk vk is equal to 1 over square root of 2, 1 plus minus epsilon k divided by ek. Right. Should it be? Just a second. UK squared plus VK squared. I think one half. Right. Very good. Which means you take any k, either when epsilon is positive or when epsilon is negative. You know the experimental probe called photoemission. In photoemission, you put a light in, the light inject electrons out of the system, and with analyzer, you measure the energy of injected electrons. Because electron has to be there, you measure essentially only occupied states. You need to eject electron from occupied states. So which means you measure only here epsilon k, which is negative, which means momenta is smaller than PF. So in normal state, what you measure only is this, right? Yeah, epsilon k is negative, you measure at negative frequency. When k is larger than kf, you get nothing, 0. In a superconducting state, even if k larger than kf, you still get this peak. So there are still states there are still fermions that you eject from the system. And it looks like this is really 2 generations previous studies. This has been measured in high TC superconductors about 10 years ago. Very nice measurements, very direct measurements in overdoped cuprates of essentially BCS coherent factor and superconductivity. You change K, this coefficient changes, so you measure overall area of the peak. Of course, nobody measures delta functions, right? There is always a width. But if you integrate the width, you give information similar to delta function. And so this coefficient has been measured as a function of K, and it works perfectly well. And it's always good then. Even simple theory is confirmed by experiment. Very good. Why I want to make connection to something that people are talking about nowadays. Very much. Yes, please. It's called under-resolved photoemission. Yeah. When you put light in, eject electron from the system and measure this electron by analyzer. Then there are several measures, laser ARPAS, non-laser ARPAS. We can talk about this. I already mentioned that any effective interactions can be viewed as self-energy. So we can introduce delta as a condensate. Or I can put it differently. I can say that my green function will be equal to 1 over omega minus epsilon k. Forget about I delta, it will always come in. Minus self-energy of k and omega. This I can always do, right? I can always say that effective interaction is something that creates me self-energy. It turns out that if you want to reproduce all this result, all you need is a very simple expression for self-energy, which of course you can get diagrammatic, absolutely. Self-energy will be equal to delta square divided by omega plus epsilon k. You can check that with this green function, what will be G will be equal to omega plus epsilon k divided by omega square minus ek squared. If I didn't make any assumption, any mistakes, this is what you were supposed to get. Sorry?
Minus the opposite.
No, it's in ek. This is why in denominator you get dispersion, which is new one. You can take this expression and express it in terms of these two peaks. One will be at ek, one will be at minus VC. So just write down a square minus b square, write it as a minus b times a plus b, split it into two parts, and you'll see coefficient in front of each of them. Now, this is the simplest example where the system becomes unstable because self-energy develops a pole. Look at this. This simple expression for sigma tells you that self-energy by itself has a pole structure. At omega equal to minus epsilon k, not plus, but minus epsilon k, your self-energy becomes infinite, right? So this is instability, if you like, generated by self-energy with a pole. Of course, if you start with the normal state and don't reach any instability, interaction, say, is repulsive, then you can calculate self-energy doing like this. This is Fock diagram. You can go to higher orders. You will never get self-energy with a pole. So you will need to sum infinite series of graphs, like we summed up from the beginning, infinite series of diagrams, and this is how we get instability. But there is more. When people talk about modern violation of Latinger theorem, etc., it's often related to the fact that green function has zeros. Look at this green function. I'll write it again. This is green function. G is equal to omega plus epsilon k divided by omega square minus ek squared. When omega equal to minus epsilon k, your green function has zeros. So your green function has two poles and 1 0, right? As a result, if you put this green function into standard expression for Latinger theorem, you will find that Latinger theorem is violated. Yes?
Sorry, I missed that. Where does this expression for self-energy come from?
This one?
Yeah.
I didn't explain, but let me quickly explain because I want to move further. It goes like that. The fact that it's condensate, which I already erased, meaning that the system develops new element. Element is when two fermions form bound state. How you define this new element for diagrammatic theory. Previously you had line, you had interaction, right? Let's put it like this, but this is actually interaction. Now we have another quantity, and quantity, let's put interaction like this. Now we have quantity like this, delta. Either two fermions go out or two fermions go in. And this is a new element, right? This is your B dagger delta or BB delta, right? Now let me take this one and write down self-energy. How should I do it? Look at this. I want to write self-energy. So I want to write full green function as usual is equal to bare one plus minus I sigma times full one. So I want to write down what self-energy is. No external legs, right? What self-energy? It's like this. I put in fermion, another goes away, and then this one keeps going, right? So let me write down maybe even easier if I put it like in the form of correction to the green function. Full green function is equal to this plus this delta delta, right? Agree? Okay, very good. Do I need to write down higher order terms? What do you think? For the green function, yes, but do I need to write down them for self-energy? The answer is no, I don't. Why? Because remember what Nikolay showed you in the previous lecture. Full green function is equal to bare one plus minus I sigma and times this. And this corresponds to irreducible diagrams for the green function. What means reducible? The ones that I cannot cut by vertical lines through only one green function. You see, we go back to the same green function that we started with. So then whatever I add, it will be reducible, right? So it's a nice thing. For irreducible, I only need one diagram, right? And now you see what's going on. This is your self-energy. Delta square times green function with minus omega and minus epsilon, minus k. But energy is symmetric. Energy of minus k is equal to energy of k. So this green function will be 1 over omega plus epsilon. And this is how you get the expression for the self-energy. This is how you get self-energy with the pole. This is how you get 0 of the green function. And those of you who are interested in Latinger theorem immediately will find out that Latinger theorem is violated. Of course it's violated. You lose the Fermi circle. Yes?
Why isn't it minus omega? So you said since the Green's function is like.
Because this, if this is omega, this is obviously minus omega, right? Total frequency, there's a conservation of frequency.
Right.
Total frequency is minus. Yes. Okay, very good. Let's move on. I want to do one more thing about interesting question of what somehow interested people at the beginning of superconductivity era, and then resurfaced back in the studies of cold atoms. And the question is this. It's actually similar to what was in the previous lecture in one aspect. We said that, first of all, we did something terrible, and nobody is raising hands and saying that I'm telling complete nonsense. While I am telling you at this moment complete nonsense, because I'm assuming that interaction is attractive. Nobody asked me why the interaction is attractive. Of course, it's a big question. And the rest of the lectures will be to partly answer where it all comes from. Very good. But at this stage, I want to do something different. We said that every time we deal with BCS theory of superconductivity, with this logarithmical theory, we have log, as Nikolay put it, from temperature, and I put here from frequency to some omega naught dx over x. We need to put this quantity in. Otherwise, we'll have ultraviolet divergence in the problem. And what if this quantity is not there? What if omega naught goes to infinity? Do we have TC which is infinite? Technically, yes, right? Let's see more accurately. So now I want to do this. My interaction u is, let's put it like this. Let's be careful. It's negative, so it's attractive, and it's constant. And somewhere here we put Fermi energy. So it constants up to whatever scale. 100 times Fermi energy. And then I ask a question. Can I write down expression for TC? Superconducting TC. And the answer, which was given back in 1961, I guess, is that yes, you can. Interestingly enough. And this answer is this way, that let's separate two phenomena. Both come formally from particle-particle chain. One is superconductivity. This one comes from energy epsilon k. I put it close to 0 at weak coupling. These are small energy. And the second one, also in a particle-particle, is something that you know from the course in statistical physics. It's, let me start with a question quickly. Is interaction measurable? What quantum mechanics tells you? Is interaction measurable or not? Well, I asked this question to those who were in Boulder lecture, so you know the answer. No, it's not measurable. Because if you allow particles to interact once, they will interact 2 times, 3 times, etc., etc. What is measurable? Measurable is quantum mechanical quantity, which is scattering amplitude, right? Which is the limit of weak coupling when we need actually small energies, reduces to a constant which is called scattering length. So what is scattering length? Scattering length is proportional to interaction at weak coupling, but then there are corrections, meaning that particles can interact 2 times, 3 times, etc. And when I want to rewrite the right relation between scattering length, physical quantity, and interaction, which is technically non-physical quantity, then diagrammatically what we do, we take two particles in a vacuum. There's nothing else. It's not a many body system. It's just two particles, and they interact with each other. What is two particles interacting with each other? Diagrammatically, which means that I still write down the same stuff. Particles interact with each other and keep interacting with each other. Similar to same particle-particle channel. What's the difference with superconductivity? There is no chemical potential. So these are particles without chemical potential. Density of particles is 0. And superconductivity is a phenomenon near KF. So what I do? Every time when I write for superconductivity, and we go back to calculating gamma, which is equal to U plus all these wonderful corrections that we, every time we write down, we write down integral of green function of, say, K omega green function minus K minus omega. If I want to do or omega plus capital omega minus omega plus capital omega, but I put KF here. KF means that these are real green functions in a many-body system. I subtract from this the same result, GG, at KF equal to 0, KF equal to 0, and at GG, I'll put it like this, and at integral GG, this is KF equal to 0, and KF equal to 0. I added and subtracted the same quantity, so I didn't do anything, right? But now it turns out that if I include all this, this is what gives me relation between interaction and scattering amplitude. And summing up all series of these terms, I express interaction in terms of scattering amplitude. And look at this guy minus this guy. What happens now with ultraviolet singularity? It is gone, right? Because if I go to energies larger, much larger than Fermi energy, and I said, let's assume that interaction is constant everywhere, then you find out that this integral is now completely convergent. Where? At momenta comparable to Fermi energy, right? So as a result, you get completely universal expression for superconducting TC. And this universal expression for superconducting TC is TC is equal to 0.277 Fermi energy, let's put epsilon F, e to minus pi over 2 mod A KF. So this is what originally was our coupling constant, but now coupling constant is expressed not in terms of U, but in terms of scattering amplitude. And the idea is that scattering amplitude is a measurable quantity. So somebody can tell you what the scattering length is, you put it here, notice that everything else is universal. Question, is it different from BCS?
Yes.
Hmm?
Yes. No.
I hear the answer yes, I hear the answer no. Let's not take popular vote, yes.
With Fermi energy, not omega divide.
Fine, but did I do something different from BCS? The answer is no. I didn't do anything. This is BCS formula. This is really BCS formula. And somebody said correctly, it's EF, not the bifrequency. Take relation between A, re-express back A in terms of U, and you go back, get back BCS formula for TC. Where is the trick? The trick is that the relation between U and A contains formally ultraviolet divergent integral. And it's cut only at energies at which actual interaction dies off. So I just put under the rug the problem with ultraviolet divergences in the theory. But again, the argument is that we don't care about what to put under the rug. This is measurable quantity, this is not. In cold gases, this is the key formula that they're using. Very good. And with this, I still have 10 minutes for this presentation before discussion. Let's now move on and do one thing. I hope that 10-15 minutes will be enough for us to do this. So right now we start asking difficult questions. and difficult question is stop playing games. I set U negative. Big question how. So the first step in this direction is to ask a question, what we need for superconductivity. Naively, the answer will be what? We need negative U for superconductivity. But this was under assumption that we assume that interaction is a constant. Let's not take this assumption. Let's assume that interaction is generally some function of momentum transfer. So I now go back to what I started with, that this quantity, I call it gamma, is equal to, remember, it's fully dressed interaction alpha, beta, gamma, delta, minus fully dressed interaction in terms of alpha, delta, beta, gamma. Very good. Let me not go beyond first order at this stage. We can all discuss how to go. We will go beyond first order for sure. But let's at this stage, let's not go beyond first order. So this will be, I put approximately Kp and whatever moment is here, minus K P prime, if this is P prime and this K prime. And of course, we all assume that there is a momentum conservation. Let me right away consider pairing channel, because this is where I'm interested in the interaction. So I will take K prime equal to minus K, P prime equal to minus P. Let me write it down right away. Minus K minus P, then this will be minus P, this will be minus K, and this will be P. And of course, alpha, beta, gamma, delta, alpha, delta, gamma, beta. We go back. But now, what we do new thing, we take this as some interaction as a function of momentum transfer. Which one? Generic. So we take this guy, and this will be U of K minus P. What will be this guy? It's the same interaction, but only I change momentum. Interaction don't care about spins, right? Interaction cares about momentum. So this will be U of K plus P. And then all this combination gets multiplied by delta alpha beta, delta gamma delta. This gets multiplied by delta alpha delta, delta beta gamma. Two different interaction, two different spin dependencies. Of course, it's completely straightforward then to write down symmetric and antisymmetric combination. So our gamma 1 will be equal to U of K minus P plus U of K plus P over 2, and then delta alpha beta, delta gamma delta minus delta alpha delta, delta beta gamma. This is our singlet combination. And the second term will be U of K minus P minus U of K plus P over 2 delta alpha beta delta gamma delta plus delta alpha delta delta beta gamma. Right? Just symmetric. I just took some of the difference between these two terms. Very good. What I did, I split interaction into singlet and triplet channel. Later on, I will come back to this formula, split interaction into charge and spin components. But so far, it's singlet and triplet. By the way, why is this a singlet? I think you know why. Because what is singlet? If I have two fermions, for example, if I have fermions, what was this? Alpha, gamma. What's the singlet combination of these two fermions? I, sigma, y, alpha, gamma. Right? Delta, alpha, beta, delta, gamma, delta minus delta, alpha, delta, delta, beta, gamma is equal to I, sigma, y, alpha, gamma times I, sigma, y, beta, delta. Product of two singlet combinations. And if I have plus alpha, beta, delta, gamma, delta, plus delta, alpha, delta, delta, beta, gamma, it's actually sigma x, alpha, gamma, sigma x, beta, delta. And sigma x is a triplet combination. It's symmetric. Up, down, plus, down, up. If you want to rotate, of course, you can always write up, up, or down, down, but the easiest is to write down, up, down, plus down, up. Very good. Nice. Does it help us? Well, in very quantitative aspect. I mean that we have interaction in two channels. Now this one is singlet. This one is triplet. So previously we said that interaction was a constant, only this, that was zero, and we said interaction has to be negative in order to get superconductivity. Now we have at least two options. We consider interaction, we consider interaction in a single channel, we consider interaction in triplet channel. But there's not much. It's just, of course, something that we need to look at, but it's not like something extraordinary. It turns out that for isotropic systems, we can make much more powerful statement. And in order to make much more powerful statement, I really need no more than 5 minutes. We consider, and it's important, at this stage, and for the next half of the next lecture also, we will consider isotropic system. In fact, not necessarily k square over 2m dispersion. Any isotropic dispersion will work, but it should be rotationally invariant. And for rotational invariant system, I can take interaction u of k minus p. I want to put this interaction between fermions on the Fermi surface because this is where I know the superconductivity is. So I take k mod k equal to pf. I take mod p equal to pf, but still, this is vectors. So the interaction can be the function of the difference between momenta on the Fermi surface. And I think you understand why I put kf and pf, because this is where logarithm is important to us. All the stories about dependence on the upper limit, it's all for our amusement, etc. The real story is, of course, logarithmical dependence on the lower limit. Then this is a function of angle theta between two fermions on the Fermi surface, right? 2 dimensions is easier to plot. So this is k, this is p, this angle theta, and they are both on the Fermi surface. I will write formulas in 3 dimensions. Formulas in 2 dimensions are very similar. So this function for isotropic system can be always expanded in infinite set of eigenfunctions. That's again similar to what Nikolay was saying in his lecture. Only in this case, eigenfunctions are well known. These are eigenfunctions of angular momenta. And eigenfunctions of angular momenta in 3 dimensions are Legendre polynomials. So I can write down explicitly sum over L, 2L plus 1, UL, PL of cosine theta. PL are Legendre polynomials. Remember, 1 cosine theta, 3 cosine square theta minus 1, etc., etc. I don't remember what the force is. Good. So, using this, we can go into one more step and write down u of k minus p plus u of k plus p over 2 will be equal to sum over L equal to m over all even harmonics, 2L plus 1, UL, PL of cosine theta. And of course, do the same with minus u of k minus p minus u of k plus p over 2 will be just sum L equal to m plus 1 up to infinity in both cases. Again, 2L plus 1, UL, PL of cosine theta. You know this. The difference between k minus p and k plus p is the angle theta shift by theta plus p, right? All odd harmonics, all odd Legendre polynomials are odd with respect to this change, or even harmonics are symmetric with respect to this change. Very good. But then, interesting thing happened. So what I did, I wrote these interactions as a function of component UL. And now I need to write, remember this quantity U bar that is obtained, or gamma bar if you like, but let's call it U bar, which is obtained by summing up ladder diagrams, right? So U bar which is also a function of theta. Particles are still on the Fermi surface. It's something that we don't know, but we can expand it in Legendre polynomials. And we can write down sum over L, 2L plus 1, UL bar, PL of cosine theta. And on the first glance, you'll need to work hard to find out the relation between UL, U bar L, and principal sum over L prime of UL prime, because every time, look, I just do one cross section in a particle-particle channel. This was K, this was P, this was L, right? So this was a function U, K minus L. This was a function U of L minus P. And I have to integrate over intermediate L, right? So without knowing what the interaction is, it's difficult to say what the result will be. But there is a wonderful relation. And the relation is this. That, where should I put it? Let me put it here. That if I want to expand everything in Legendre polynomials, I expand this, then I can use the fact that integral over solid angle Q of L, over 4 pi. So I integrate over all L on the Fermi surface of Pm of cosine theta KL, Pn of cosine theta LP will be equal to 1 over 2m plus 1 delta Kronecker between m and n, and then Pn of cosine theta Kp. This factorization. So all these integrals eventually factorize because of this formula, this factorization. That only Legendre polynomials with the same n give you non-zero result. As a consequence, you have this wonderful formula, which apparently was obtained independently by Landau-Pitaevsky on one side of the ocean and by Anderson-Morel on the other. And the formula is that there is a local relation between UL bar and UL. No other L's are involved. It's not like UL is equal to sum over L prime of UL prime, etc. It's completely local, and the relation is UL divided by 1 plus MUL PF over 2 pi square. And let's write down log omega naught. We still play the same. Omega naught divided by mod omega. And of course, you know that I have to put here I pi over 2, but we know. I don't need to do it again. What it tells you? It tells you really very fundamental things. That interaction can be totally repulsive, except for one component. If there is a one component of interaction, one value of L, for which UL is negative, you immediately see that there is instability. That the system will generate condensate with this angular momentum L. And this is much less severe restriction than restriction that interaction has to be attractive. Let me finish today's lecture by saying where are we going to move. We are going to move to the case of, that if you start with content, let's make a connection. Nikolay was and will be talking about dynamical aspects of the pairing. I will touch dynamical aspects of the pairing, but this will be lecture 3.
Sorry, which year was it?
Sorry?
Which year was it?
1961, 2, 3.
Okay, so past.
Something early 60s. Probably 62 as far as I remember. So here's where the story is. Let's look at Coulomb interaction. U as a function of coordinate r goes like this, 1 over r, right? You know what happens next? Let's start screening. Let's include standard screening. We go from 1 over r to Yukawa potential. We're still talking about static screening. Dynamical screening will be the subject of Nikolay's lecture. You go from this to much faster decaying interaction, 1 over R, E2 minus R over Xi. This is your Yukawa potential, right? But you know this is not the full story for the static interaction. It turns out that at large distances, screen Coulomb interaction start oscillating. Cosine in 3 dimensions 2k of R divided by R cubed. It's called Friedel oscillations. There's something that is very heavily used in the theory of impurities, etc. So there are, what it means for our case, it's just Friedel oscillations of screen Coulomb interaction. What it means for our case, that occasionally, let's put notations again. So this is interaction U of R, the same interaction U of R, and I just wrote as there, Yukawa, and this is Friedel. There are regions where interaction occasionally becomes overscreened. And then the question is it enough to have one component of this interaction attractive or not? And this is what we'll do next time. Okay, good. Okay.
We have time for a few questions.
Yeah. Yes, Andrew, you have a
Yeah,
relation.
sure.
You have a relation between the autogramming and the sketching length. Does have some constraints on the size of the A, say KFA has to be smaller than 1, or the equation has to KFA all differential.
Can I say it once again? I'll just
I'm
need to
curious
repeat the
about
question.
the relation between auto parameter and the scattering amplitude.
Right.
Scattering length.
Yeah.
What if the KFA is much larger than 1?
We assume that we are still in the weak up. So the question, what's the value of AKF? We assume that we are still in the weak coupling regime. AKF is small parameter.
If the KF times A is much larger than 1, is it
Different story, have to do it differently. Although, to be honest with you, when people apply all this, they applied it to helium-3, in which AKF is equal to 2. Then you will decide pi factor, it's AKF divided by pi, but then we go into gray area. Yeah, technically it's all for small AKF.
When you had the Green's function with 1, 0, and 2 poles, what is the physical meaning of the 0?
The physical meaning, to me, the physical meaning of the Green function, exactly what I said, that for any k, there are 2 poles. Basically, 0 is basically, if you have 2 poles, take any function, write down 1 over omega minus e plus 1 over omega plus e, and then combine them together. You will get 0 in the numerator at some point.
So does the 0 only appear for an ordered state, or can it occur? So is the 0 of the Green's function also an indication that you are in an ordered state?
Is it the indication that the system is in the ordered state? That was the question, right?
Yeah.
It's a very good question. In fact, something that I don't know how to answer well. In the simple mean field theory, which I showed you, the story is, of course, you have delta, right? I don't want to put modulus, I put delta. And this is your order parameter. You assume that all pairs have the same delta, which means a condensate, right? Condensate means macroscopic number of particles in the same ground state, which means all pairs have the same condensate with the same phase, this phase order. If you do this, or really in the mean field theory, just calculating lowest order diagram, you get self-energy, which will be delta square divided by omega plus epsilon. Very good. Is it delta square? No, it's mod delta square. At this stage, you may say, well, who cares? It's the same phase for all pairs. But now modern studies is attempt to understand, can it be that the system has, I put it as superconductivity, strong phase fluctuations, such that average value of delta, which is average value of mod delta e to I psi, will be equal to 0. So which means that average value of E to I psi is equal to 0. Means that phase fluctuates, but mod delta is there. As a result, you still get self-energy with the pole. This, I think nobody can really tell you how to get it. But this is what people are searching. How can one possibly get self-energy with a pole, which immediately translates that it will be 0 in the green function, without producing true long-range order? Subir Sachdev and his group are studying this in detail as an indication of possible topological order. So order parameter which does not lead to conventional order, but still it's enough to produce you 0 and poles in the green function, poles in the self-energy, which means 0 in the green function. Yeah, I know one crazy example, and if interested, I can show you how it happens, but I cannot say more. But this is what people are searching right now. How to obtain poles in the green function, zeros in the green function, and violation of Luttinger's theorem without introducing conventional order. This is why I put it this way.
You said that one UL in a certain angular momentum channel has to be negative. Is that the same angular momentum the Cooper pair?
Yes, yes, it will be the same angular momentum. So this means that if there is some UL which is negative, which means there will be condensate into Cooper pair with the same delta. Delta is a function of theta, can be by itself expanded in angular momentum, but will be exactly the same. It doesn't mean that there is only one, right? It can be that all of them or half of them are attractive. Then you have to choose which one has the largest negative energy. This is what we will do next time, tomorrow.
So today we get the expression for the gap function from the gap equation, which is an exponential form, and we also get the same exponential form for the poles of the interaction, just interaction in the pairing channel. So does it mean that we can in general get the shape of gap function from the pole in the normal state?
Very good question. My answer would be that yes, although not everyone will agree with me. I mean that this, you see instability. Where is the instability, right? If you go slightly below the instability, it's pretty much guaranteed that the gap function will have the same form as the instability. But if you go to lower temperature, who knows what will happen? There will be other channels, the gap will evolve, etc. So there's no such theorem that you solve in the normal state, you find the structure which give you instability, and yes, my gap will have this form. Only very close to instability. And then you have to solve nonlinear equation and see what's going on. And it often happens that you get more complex behavior.
All right, let's thank.
Wait
a second.
I hate to be this guy, but like, what's the homework problem?
Why bring it up?
Yeah, I was thinking about homework problem. I have one homework problem about Kohn-Luttinger, which will be basically, I thought about giving you guys one homework problem such that you will work on this. But in terms of, since others are giving homework problems every time, and then you still have presentation on Friday, right? So one thing to do really is to look into this and really derive this, because this is not that straightforward.
This relation.
Yeah. So basically, okay, what you have to derive. I didn't tell you anything, right? This is, you will have to derive it. So try to do this. But on that part of the classes, there will be probably given to you tomorrow one big question about how to do calculations for Kohn-Luttinger. And I will give you a problem for which I don't know the answer. You know what I will do. Okay, good. Now it's what? 25 minutes break and then your presentation.
Right? Both particle and particle culture. But still.
Saying something super fast. Yeah, it's like how you could get like repairs those like that, you know, it's just like pretty bad.
This is a kind of bad background including No, I actually почти оно, да, то есть положительные его, все положительные его отели,
Я знаю, я слышал это.
So.
Has all kinds of applications, places. Yeah, I gave my lecture to Megan, so I think she's gonna upload it, but she said she would. But okay, good to see you.
Yeah,
So
I was basically writing back to this whole night.
Oh, I see, okay.
I sent it to Andrey like 5 yesterday, and I thought I would be able to come here, lecture, but I just.
To write out the formula.
My lectures are,
Raise to the negative beta H. So.
I think,
And
as what's missing.
Oh, I see.
So it is.
H, so basically the negative.
Yeah, the more stuff is what's. And the
Saying that it could take like 9 pounds yeah, because I applied it like
And then you see duration of staff reject the negative.
Oh, I
it's
see.
saying like take like 9 months or something. I don't know. They said they will change it once they move to it. Like the this or you want me to?
Oh.
Well, let me know if you take that.
Yeah, I mean, in principle, I'm willing to, but I have to find a mechanism to do that.
Pretty way,
So-
also something.
Yeah, so it's,
What we usually do is.
I don't know if I can solve that because I need to use some source of money to pay for it and I have to justify using it for this purpose. And so that part, I would.
SD channel or chart.
1600 I'll ask and see what I can do. But
Just do some initial configuration for the optimal.
Average type, like for example, if you consider the say you what if you clean or you
Yes, so basically, we can assume if looking at the finite temperatures.
these are always.
On the, for example, square.
I feel like it's like.
Basically, for each side, you will have a corresponding.
Now, I mean,
And also corresponding to the imaginary time.
I mean, not you, but some people.
You will, the auxiliary two will be at I, L, so I ranges from all the light size and L ranges from all the size. So, and then all the variables, and then you can randomly choose.
But I'm looking at all these things have to be agreed to, so that's always. Yeah. I'm trying to see, so what do you combination?
So the auxiliary.
I didn't think you had to apply for that process. Thank you. Yeah, okay. No problem.
Now. For basically for just use the discrete.
I'll provide this.
But there are also some continuous.
So then, okay, then, so for every step you update, your.
So the, I mean. Yeah, so basically access the same you actually.
Okay, so. Sure, you actually, by the way,
Basically later you just so. Force function, which depend on.
So it is a way of implementing Pauli exclusion principle through this.
But that is it's acts like a different.
It is. Well, not exclusion, but.
Be mindful. Like the water parameter.
Part of that.
There are also discussions, I think it's still based on. So one is in the surrounding to say we expect the water parameter.
If you're studying Hamiltonians of that type.
Is in the water.
So it's always.
In the many body configuration. Use the symmetry, if you directly calculate the average of the water parameter, it will be symmetry. If you calculate.
因为在那个
Because it contains Hamiltonian
correlation. With
yeah, I'm gonna spend a lot of time on that.
Okay.
Realize I'm more slowly than I thought. So I'm trying to right now reorganize it so I if that are address super technical questions. Get into short.
对，因为这两个相加的。Yeah, question about any history of like feel free to move it down. Full days, but Like, it's more like, I guess it's also like, there's some, it's more or less like, kind of the idea of like,
Yeah.
yes, even like, like frustrated. I'm done here. I'm like, oh, it's close.
Get one or that.
As I say, as J say.
Yeah, and the sum overhand.
Yes.
Oh, so you, yeah, so you're asking how magnetic order affects. And so, at state you're talking about, if I recall, you'll generate in a spin orbit interaction that is right? So it's not generated by the spin orbit, but it's the same structure as spin orbit, but it's generated So in that case, that's the on the translationally invariant part of the Hamiltonian.
It depends on the function of such a correlation as a function of. So basically, if it's
Those situations, you will.
Otherwise, it becomes extremely
By this. There this book is standard term.
They get quite fast, and then
And then you'll get the fact that the issue as far as you know, even this all generates some higher order structures of delta. Those effects are going to be, I think, something you can
information.
something like an Altermagnet. So Altermagnet.
What properties or
Everyone goes to find it. The simple reason for that is because basically I see it's not the great like the house. What you have left over is possibility of Andre drew that picture of this one and the Q value.
and you will have different.
So that can survive if people study that very extensively because that's a natural state of the but it can make the altermagnetism stronger.
Plus minus. And then if it is at half billion, it could in the whole cycle, it will just appear.
People do study.
Yeah. If you have some in the system, and don't affect.
So it's only been explored in the last 2 years, really, but engineering usually statements but symmetry does take great does what now survives the presence of that broken symmetry. And then you
Since I'm having the picture, kind of like that. Measure the way, in this case, you have like spin up, spin out, for example, like.
Principle, yeah, I mean, I threw out non-unitary today, but because you've broken time reversal symmetry, you will have non-unitary. So that does merge. And then. No, important that unitary parameter is. I don't know if you're expert.
That's the first one that like before.
Oh, the alternate. Yeah. Yeah, so you have up on one surface, down on another. Preparing in that situation, applies to non-unitary pairings. I don't know that paper. Okay. But in the context of superconductivity, this is It only
For the,
odd pairs.
long things.
So, I have asked a question, like, to
But for some other cases, there is a long.
a lot about the development of odd parity states. Taking ultramagnetism is like.
太多计算你对我太低了。
Odd parity superconductivity is still is a good question. So if you can answer that, that would be interesting.
And like, sorry.
Yeah, that's fine, that's fine.
And so is that like, does that come from, for example, when you sell the self-consistent gap, it doesn't come from like a parity structure, like the determinants, but like, there's also other papers like, even like Gorkov, like back in the 90s, like. Get rise, like spin triplet for like, is that what you're like?
Yeah, in some, yeah, so it's in some sense, yeah, so. So maybe you're referring to
Otherwise,
spin orbit coupling that Prokofiev was talking about, and then, and there you get anomalous green function currents coming from this. But then you get an anomalous Green's function, so if you look at your Green's function, singlet parts and triplets part, but if you actually look at the order parameter, let's say sum over frequencies omega n of anomalous Green's function part, you find that often is very small. So, but what you're saying is
that if you want to
in the presence of broken inversion, you usually might expect spin singlet, but now because of the band particle generate some spin triplets. And so there is that. But yeah, actually in Gorkov's paper, he doesn't really talk about that per se, but he talks about the form of the anomalous Green's function and how it develops a triplet component, and that triplet component can be large. Even if the uniform spin triplet order parameter itself is not large. So maybe that's a little nuanced, but.
比较有争议的地方，就比如说在pure Hubbard model 里面，到底有没有
Yeah, so this matters a lot. Like in any weak coupling theory, the band structure matters tremendously, right? Because in the end, you're an instability of the Fermi surface. So whatever is happening in your eigenstates of the Fermi surface.
So we're interested right now, like in our group, like kind of like, well, again, we're just saying those like maybe sublattice.
Okay.
But like, we developed I'm interested in kind of like maybe expanding more, but really like it's like there's a recent I was kind of connecting this like sublattice like these alter magnet.
Oh, I see.
Is there both like compensated in a sense?
Yeah.
As like
So are you working with Oleg or?
Actually, I work with UE, but I kind of closely tied to Oleg.
Okay. Because now I remember he has written a paper on how to write down an effective, symmetry-based description field theory for a three sublattice. Right? So I just, and then he found some surprising, he found that numerically you generically get in the spin excitation spectrum, you get a double degeneracy Magnum spectrum, which you don't naively expect in this three sublattice space. But this is a little different. So now you're moving to, you're trying to understand. So you're going after superconductivity? Who do you work with? Sorry,
I work with UE.
Okay, I know her. Yeah, okay, that's right. Yeah, so okay. So now you're trying to think about if that was superconductivity, is that's the I see. Okay.
So we had developed it's kind of doing independently while she was on maternal leave. Like we developed a theory. Where we have this proximatized aspect ferromagnet. So it kind of like as you're mentioning, like Prokofiev, really normal screens function characterized as full-flipped.
Yeah.
Generally, that can give rise to like additional terms and things like again, the window, or usually have like a single term, d dot d term, or d dot gradient d. So now you can have like d cross gradient d.
I see, okay.
So in which case you have the lowest energy configuration.
Okay, this sounds reasonable. And this is, you said, a coplanar state.
Right. So like you can add a spin chiral, or like a non-vanishing scalar spin chiral, then it'll create a just some diode effect. But even for a coplanar, like zero magnetization, it can still rise to frustration.
Okay, interesting. Yeah, so maybe related, I don't know, this is.
No, there are two sources. Just one is the frequency dependent piece, another is direct related direct piece.
So since, yeah, this is, I also trying to redevelop my notes.
Yeah.
Yeah, it's always takes.
And system.
So I was actually like,
I don't see.
seriously short.
It's a nice problem.
So it's a lot, but okay, let me, so you're talking about coplanar magnets, and I thought I would just maybe share. We recently published this paper, which is about coplanar magnets, and it's a little different than what you're doing. But there are many coplanar magnets that fall into this sense, but they share a feature with what you have. So you said that there is this odd parity spin orbit term, and then you can go to that. So all these magnets have this odd parity spin orbit term. And so what we call odd parity magnetism is basically the magnetics that generates a Gorkov-like odd parity spin orbit. Does that make sense?
Right.
Yeah. So maybe in what you're studying, this may be interesting. I mean, this is all about the mechanism for doing it and the microscopic theory behind that.
This is a function,
But it is, it's not something I can explain quickly, but okay, I mean, you can find examples in DFT where you can, so this red and blue are up and down spins. Sure. And then if you look at this band structure, for example, so here you see red and blue are separated by an energy scale that's even 0.1 eV. That's massive. For any spin orbit energy scale, that's a gigantic spin orbit. So DFT shows that these things can be big. And so it sounds like maybe you're working down here, so I thought maybe this might be interesting.
So yes, yeah, like when we were solving it, just like that's how I got like a specific for this ended up being like it's not really like surprised like us way than like I didn't think it was gonna survive, to be honest.
Okay, so it's right, okay. Yeah, I mean, this just came out with his red letters like 2 weeks ago. I mean, this is even parity spin splitting. And so, the question asks is generally odd parity spin splitting. And so it's lost in
They call those like I forget the name.
Yeah,
It's like the structure, is that?
Yeah, it is. Yeah, so that's exactly. So here we give a specific mechanism for commensurate anti-magnets to generate the state. Here, this is two atoms in a sublattice of a unit cell. And then magnetic ion, these magnetic moments are 90 degrees rotated. And so that's repeating itself across the system. And so it is really a coplanar magnetic state, like you're kind of doing in a sublattice integral. So it sounds like it has some similarity to what you're interested in. Yes. Yeah, so these are coplanar states that they generate this like P wave magnetism. It's not always P wave, it's different. I'm not sure I thoroughly understood what you're saying, but if you remind me.
Even like those these things are
It's very like. How I do so I don't know, but it's right.
I first started off, I said I think it was like.
Okay.
I think it's about 50-50. Okay. It's like going
Yeah, but that is exactly what's here. And I guess in your case, everything is coplanar, so you must also have the same length orbit term.
Okay, yeah, essentially, okay.
There's additional terms or?
So the way we would figure like we do it on a Kagome lattice and not the triangular lattice. We do it on the Kagome lattice and it's relatively the band structure is coplanar, whereas you do on the triangular lattice, because it's not commensurate with the three-step lattice, and it ends up actually being around the same.
Yeah, okay, and so then you get something that's not complicated. Yeah, I'll be here.
This you try to give a third like in 5 days.
Yeah, but the message is, here are other sublattice problems where you get coplanar states and you generate spin temperatures that will affect the surface. And so that's the kind of thing about maybe this.
Yeah, no problem.
Did you assign anyone for this?
For this, no, I didn't really assign anyone for this. I can always do it, but that might be easiest.
I'm almost.
But I think today.
I don't
Oh, yeah. 1, 2, 3. You put your name on one of this. No, you don't need to go to second page. One page will be. Yeah. No. Okay. Group 1, group 1, then group 2 will be.
No, we can sign our one ranges.
Or the group 3. Yeah, who is one? 1 plus 2 plus 3. In the one. So Agterberg group 1, Prokofiev group 2, and Chubukov group 3. Yes.
Hi everyone, so welcome to the presentation. So I will call your name one by one and it's down here and you will have 2 minutes to present. That's the
Total time 1 hour.
Yeah, total time 1 hour. So we'll start with Azam Alzarani. Probably need this. Doesn't need this slide. No.
Oh, you have a slide?
Just one, yeah.
Sorry?
Yeah, one slide.
Then,
Separate files first. That's the only thing.
Yeah. So. I love their t-shirts. But
And slides are, yeah.
Yeah, last day.
So like,
You get that.
Yeah. Okay, yeah. So all we need to do with each Okay, it's fine. You can put it in there. Do I need to download it first? No, you think I think it's detail. One.
Yeah, if you don't use the PDF, you can just go back to Google Chrome. It's long enough anyways, yeah, it's over time, yeah. Okay, so, hi everyone. My name is Azam. I'm from University of Maryland. My advisor is Professor Yakovenko. I'll just introduce the motivation for my poster really shortly. This is the title. Yes. So our work is motivated mostly by a recent theoretical paper on the AC Hall effect in a hypothetical time reversal symmetry breaking superconductor on a graphene lattice, I believe, co-authored by Professor Agterberg actually, and my advisor, Professor Yakovenko. The main thing we see in their result is that there's a huge sharp peak at a certain frequency in the Hall conductivity. So my work was to investigate the origin of this peak, try to generalize it beyond the specialties that they are covering here, going beyond graphene basically. And hopefully we can propose that as an experimental, very clear signature for time reversal symmetry breaking superconductivity. The kind of experiments we are thinking of are the ones at the bottom there, which measure the polar Kerr effect, which is proportional to the Hall effect anyways. And yeah, I mean, this is an example from 2 years ago, I think. And as you can see, there is a serious problem there with the statistical significance. Okay, yeah, I mean, this is the end. Yeah, there's a serious problem with the statistical significance of these results. So we think that, we mix these two together, basically, we can help improve the results a little bit. But yeah, that's all. If you're interested, you can check my poster outside. Thank you.
Okay, so I don't have a slide, so I'll just start talking. So hello, I'm Shagnik Banerjee, a PhD student at Cornell University, and I'll just talk a little bit about the poster I'm presenting. So our work is on the interplay of disorder and quantum geometry in unconventional superconductors. So quantum geometry, which comprises Berry curvature and the quantum metric. So these are all single particle aspects of your Hamiltonian, but it turns out they play a key role in realizing different strongly correlated phases of matter. For example, a notable example is superconductivity in flat bands, which has a lot of experimental relevance to modern systems. Now, it's interesting to see what happens because for clean superconductors, this is a very well-studied phenomenon. But it's interesting to see what happens when we add disorder in the system where we have flat bands with quench dispersion and see the interplay of quantum geometry as well. So when we add disorder to a superconductor, the first thing that happens is there is the presence of these bound states in it, known as Andrey bound states, which occur below the superconducting gap. Now, what we showed that quantum geometric effects in the regime when the dispersion is quenched, it can strongly enhance the localization lengths of these Andrey bound states. And this has interesting implications in the spectral and thermodynamic properties of these superconductors. Another interesting finding was that although we started out with a clean gap superconductor initially, but when we added disorder to it, it turned out that the Andrey bound states that resulted from it was had asymptotically low energies. So we had sort of a gapless spectrum, and the findings showed that these low energy states mimic the properties of dirty nodal superconductors, like dirty D wave, for example. But the superconductor that we started with was unconventional, yes, but it was still fully gapped. So this has interesting implications for experiments with modern materials as well.
Liam bonds.
You have another person who do it?
Yeah, he's grabbing our poster right now. My name's Liam, and I'm going to be co-presenting a poster with Changbin Chu. Our title of our poster is The IV Characteristics of Multi-Valley SNS Junctions. And so for a background of our problem, this is a non-equilibrium superconducting system. And so a kinetic scheme to study those types of systems was developed by Larkin and Chubukov. And ultimately what you get from that kinetic scheme is two evolution equations for an even in particle whole branch distribution and an odd in particle whole branch distribution. These are coupled and pretty convoluted. And so kind of the first direction of our work was to parse these down to highlight how the evolution of the density of states really kind of contributes to this kinetics. And so you can imagine in an SNS junction, in the normal region, you have a mini gap that's evolving in time as your phase difference across your junction is growing. And so your mini gap is growing, and so your spectrum is flowing up and down, and the occupation of all the levels is flowing along with that spectrum, creating a non-equilibrium distribution, which has to be inelastically relaxed. And so if you look at the current voltage characteristic, in high voltages, you'll have your normal state conductance with the elastic relaxation time controlling it. But at low voltages, you actually get a non-monotonic response where you have a current peak at low voltages controlled by that inelastic relaxation time. And so the other direction of our work was to kind of generalize these Larkin and Chubukov equations for multi-valley systems where you have disconnected Fermi surfaces. And there's an associated additional timescale of the elastic relaxation between valleys. And so we find an additional kind of current peak at low voltage for this from the spectral flow. Okay. And if you're interested, come talk to us. Thank you.
Go.
Hello. Hello everyone. My name is Chubukov. I'm currently working with Dr. Igor Mazin at George Mason University. My project, poster, is about a toy model for two-dimensional spin fluctuation induced in conventional conductivity. So basically, I try to figure out how the spin fluctuation interaction may induce to the formation of copper pair. That leading to the non-conventional gap parameter, which is not necessarily be a constant, but depends on the momentum. My problem is solved in the two-dimensional Fermi surface, and yeah, I'm gonna present it tomorrow. Thank you so much.
How we
Good afternoon, everyone. I'm Jihao Cui. I'm a postdoc at Columbia University. I work with Professor David Rackman and Professor Andy Millers. So I will present some results on the numerical solution of the Agterberg equation in the strontium titanium oxide. So the way we are doing it is like we use a quantum chemistry way to downfold a model for the strontium titanium oxide from the ab initio calculations, and we solve the Agterberg equation with the anisotropic effect. So I will talk about the how to use a sparse frequency grids and also a non-uniform K-grids to converge the results and to check whether the Agterberg theory works for these materials. I will talk more on the poster session. Thank you.
Aaron?
Done correct. So hello everybody, I'm currently a postdoc in Finland. I did my PhD
Use microphone anyway.
Yeah.
I did my so I'm currently a postdoc in Finland. I did my PhD at Stony Brook, New York. I did my PhD on Moiré systems, and the kind of overarching theme of Moiré systems is that you've got some band structure and your goal is to engineer some flat band with the idea that kind of your interacting scale is inherently large compared to the flat band. If you're curious about that side of things, you can about the Moiré side, you can talk to me about a second poster. But the one of the ways this shows up in superconductivity is that, so if you've got a flat band, then how do you tell flat bands apart? Well, all the energies are the same, so you have to ask about the eigenstates of your system, and that's the quantum geometry. But most of our terminology in quantum geometry, like the quantum metric, asks if you have a state and you have a state at a slightly different K point. But of course, in superconductivity, we're connecting K and minus K. So how do we understand very different K points? Well, usually what we do is we use time reversal symmetry to relate them. So that's kind of the foundation of the results on quantum geometry in superconductors is all based on assuming time reversal symmetry. So my poster is about breaking this assumption perturbatively and using a more general notion of quantum geometry that's rooted in its basis in quantum information approaches to understand how to account for the time reversal symmetry breaking effect. 30 seconds. How to account for the time reversal symmetry breaking effects from the quantum geometry itself in the superconducting phase.
Ahmed Elizabeth.
Hello and howdy. That's how we say it from my university. My name is Ahmed Lazavi. I'm a PhD student at Texas A&M University. I work with Dr. Artem Abanov. My poster tomorrow will be about, we'll talk about how we produce new bounds on the transition temperature for the gamma model of superconductivity. The gamma model of superconductivity is basically a generalization of the standard Agterberg model that describes the pairing at the quantum critical point where the interaction is not necessarily mediated by just phonons. The effective interaction, the effective electron-electron interaction goes as 1 over omega to the power gamma, where omega is the transferred Matsubara frequency, and gamma is a parameter that determines the properties of the boson that we have. So this model is very universal because at quantum critical point, there is only one energy parameter in the problem, which is the bare electron boson coupling constant. And the gamma here is a parameter that determines the the properties of the mediating boson. We use a recent formulation of the equilibrium state of the Eliashberg theory and its generalization in the gamma model as a classical spin chain. And using this, we establish a very simple, like surprisingly very simple, just linear algebra calculation to set bounds for the transition temperatures, lower bounds and upper bounds. And we also propose like an approach to sharpen. We also propose an approach to sharpen these bounds, and they give very closed form, ugly but closed. And if you're interested in that, come see me tomorrow in the poster. And yeah, that's it. Thank you.
Andrea. Yeah, that's right.
Hi all, I'm Andrey from Stony Brook, and in my post I want to tell you a little bit about an interplay between a newly discovered form of magnetism called altomagnetism and topological superconductivity. Specifically, how we can use altomagnets to modify a very well-known setup for realizing Majorana fermions in a 1D wire. So for those who don't know, altomagnets you can view as a combination of ferromagnets and antiferromagnets. Like ferromagnets, they have a spin split band structure, but like antiferromagnets, they have zero net magnetization. So that has the advantage that you can use it in setups and have the same effects as a ferromagnet, but not with the issues that come with having a net magnetization. The other interesting thing about altomagnets is that their spin splitting is anisotropic, which means that depending on how you orient your setup, you're going to get different effects. Specifically for my project, if you consider a semiconducting wire with strong spin orbit coupling with proximatized superconductivity and proximatized altomagnetism, simply by rotating the wire, all else kept equal, on top of the altomagnet, you're going to see topological phase transitions. If you want to hear more, I welcome you to come join me at my poster tomorrow. Thank you.
Aaron.
Hi, my name is Aaron Kleger. I'm from Dartmouth College, advised by Dr. Rufus Boyack. It's well known that strong interactions or strong correlations are known to destroy quasi-particles, prohibiting a Fermi liquid-based description. Nevertheless, superconductivity is found to exist in many systems without sharp excitations, that is, long-lived quasi-particles. This is best illustrated in the cuprates, which have incoherent electrons in the normal state. In recent years, there's been a lot of interest in understanding pairing mechanisms, so that's coherent pairing mechanisms for incoherent electrons. And the Yukawa SYK model, a generalization of the usual SYK model, has emerged for describing these systems. Gathered a lot of interest for its success in recovering attributes of the strange metals, which have T-linear resistivity and logarithmically enhanced heat capacity. And so this model displays marginal Fermi liquid behavior at low temperatures. It's like the SYK model, where it has random all-to-all interactions between the fermions, but the difference is it's for the Yukawa-like interaction. So it's of the form G, psi bar psi, phi, and we have indices here, alpha, beta, gamma. And we consider a system where it's an ensemble of theories with different valued coupling constants G. And the key attribute that recovers marginal Fermi liquid-like behavior that people are most interested in is the case where the variance of this coupling is local in real space. And that leads to a factorization of the momentum integrals. So it's not of the usual form where it's convolution. And this leads to marginal Fermi liquid-like behavior. We are computing and studying viscosity. If you're interested, please see my poster outside. I enjoy talking to you. Thank you.
Sergey Krahin.
Hello, everyone. My name is Sergey. I brought a poster about nonlinear electric response in strange metal. So what's the deal with that? Usually, whenever you see like most of the theoretical works on strange metals and non-Fermi liquids in general, it's usually an attempt to construct some sort of microscopic theory that would give you the T-linear behavior and T-log T behavior and heat capacity. But we decided to take a bit different approach. We asked the question, is it possible to find some other universal feature that strange metals should show that is not encoded inside the microscopic theory? Because usually we try to come up with microscopic theory for linear anti-resistivity, but what else can they predict? And we pretty much were able to show that if you're going to have a critical point that will lead to a strange metallic behavior, it should necessarily lead to nonlinear electric conductivity to be 1/T. And in comparison to, and this is going to be TF/T enhancement in comparison to what you would expect in a Fermi liquid. So this, we pretty much find another universal feature of strange metal phase. We provide both general argument similar to one people had back in 1960s with semiconductors, and we also provide some microscopic arguments by computing, by turning SYK into a kinetic equation in a formal manner using Keldysh, and we pretty much get the result and construct the theory to compute everything perturbatively in an electric field.
Hi, I'm Yujen, and presenting nothing related to superconductivity, but thermal transport. So I'm going to talk about quantum oscillations. So as you know, for quantum oscillations, you probably need to apply it in the outer plane magnetic field to the system, and basically we're from Mandel-Lewis, right? Which is just a periodic distribution of your density of states as a function of energy, and then this is in a clean case, which is like bottom because of disorder, and in a highly disordered state, you have basically just like sinusoidal modulation of it, which is the same coordinates. And now the question is this: if you just want to calculate the charge transport, then you basically see the same sinusoidal oscillation of it, which is just the Chubukov discussed oscillation, right? And but if you were to calculate transport, then electron is charged, but it's not the whole right? It also plays a role. And if you give me 3 more minutes, we have two contribution. One is from electron, one is from. And I can argue that the oscillations from these two contributions are out of phase compared to each other. So when you measure experimentally, you actually measure the sum. And now at the temperature, sure, no problem. All the photons are frozen, so these are from electrons. And as we raise the temperature, more of the photons are populated. So one would anticipate that at some critical temperature scale, the oscillation amplitude from part will take the one from the electron part. So if you add up the sum, and then at low temperature, you will see dominated by electrons, and then as you raise the temperature, these two almost at this critical temperature scale, they almost cancel out with each other. And as you further raise the temperature, it becomes out. Yeah. Okay, out of phase. Yeah, that's all I have. Thanks.
So I'm Maria. My advisor is Natalia. I'm from here. So basically, we research on the 2D planar archetype spin liquid tunneling with the vacancies. So with structure like this. The top and the bottom layers are the substrates, the metallic substrates, and the middle layers is the archetype spin liquid with vacancies. So like this. So we can have two kinds of lattice structures, which is A and B. So in this system, we can apply the magnetic field, and then we can see the signature like this in the numerical calculation because the type liquid is solvable. basically we have this structure. And because the existence of the magnetic field, the time reversibility term, so the box temperature will be above the gap. So we can see the low energy modes, which is from the random modes contribution, will be seen in the near zero voltage inelastic current. So that's what we got. Thank you.
Daniel?
Hi, everybody. I'm a postdoc at Columbia University with Andy Millis and Raquel Quiroz. And well, my research lately, and in particular my poster, is motivated by more TMDs, in particular the recent observation of superconductivity in proximity to some correlated states in twisted tungsten laser electronics. In the poster, I can explain you all the details that we understand what is a twist angle evolution, the transport signatures, and so on, and we reproduce experiments for the correlated state. And now, what are the new interesting things about this correlated state is that it's a magnetic state, but it strongly couples to the layer polarization. So it has a strong magnetoelectric coupling. And what we are studying now is what happens in the collective modes due to this coupling. What happens? What is the effect on the superconductivity due to this magnetoelectric coupling? And third, what is the role of topology, because the bands in these systems are topological in all of this? So Andrey has a paper also related on this, but we'll try to see something more. Thanks.
Risto?
Probably good enough. So I'm Risto Ojärvi. I'm from University of Jyväskylä, and I don't have a poster, but I want to present this recent paper, which is well related to this workshop, this school. It's about there's this common scenario where a bosonic mode mediates an interaction between electrons, and usually the interesting case is where the bosonic mode is critical, and then the interaction is enhanced. This is the case of spin fluctuations, for example. What we did here is we studied loop currents in a cuprate system, and we showed that actually for these modes, the interaction is not enhanced near the critical point, although the bosonic correlator diverges. It doesn't lead to enhanced pairing because of the vanishing matrix element. And this is quite general result. It's based on symmetry analysis. So
30 seconds.
I don't have a poster, but please come discuss with me if you are interested. Thank you.
João Pedro Costa.
Hi, I'm João Pedro, and I'm currently working with Ames Lab with Rebecca Flint in block engineer strong correlated phases. So one issue we had is swing correlated phases are hard to find in nature. One example is in that phase diagram. We have like a phase diagram of a excellent Kitaev model in which the phase correlate we are interested, like Kitaev spin liquids, is very hard to find in that figure, but it's in the polos, one of the two. So we come with this technique for K-engineer, which we use periodic perturbation in our system to change the effective dynamics over time. And we use this based on Fouquet theory, which I will explain details in the presentation. And we also discuss a little about the choices of light we can use. Some of them might break symmetries of our system, some don't. I will talk there a bit. Sorry. And some of the results I may talk about, we use like perturbation theory in certain kind of materials, which can be explained by a minimal model of this extended Kitaev model. And with perturbation theory, we use these fluctuations provided by the electromagnetic radiation to change our effective couplings of the systems. You know, we can find regions and we can possibly find this spin liquid correlated states. So yeah, so we're going to talk more about how different choices of light can change this profile of the fluke engineering and the poster presentation.
That's fun.
Hi, I'm a graduate student at Texas A&M University. I work in cryogenic detectors, utilizing the superconducting transition as a detection mechanism. And tomorrow I'll be presenting one of my project, which is a particle detection utilizing magnetic superconducting transition. So it is a type of a transition S sensor. These transition S sensors are cryogenic detectors that utilize the superconducting transition as a detection mechanism. So they are usually biased near their superconducting transition, but below superconducting transition temperature, the critical temperature, and any additional energy required is given by external particle or external energy, and they go to resistive phase or normal phase, and there will be a voltage drop when they become resistive. So that can be measured using some external electronics. So this type of mechanism of detection has some disadvantages because it goes to resistive phase. There will be a ohmic dissipation, and also there is possibility of Johnson noises. So to get rid of these issues, we are working on slightly different kind of detection mechanism, which instead of resistance measurement uses inductance measurement. So it has some advantages, like we can multiplex the devices, and also these noises can be reduced. So I'll be presenting a proof of concept of the device, that the device I'm working actually works. So I welcome you to my poster session tomorrow.
Yeah.
So, hello everyone, my name is Sofia Pentus. I'm from Aalto University, from Professor Päivi Termas group. And so let me introduce my posters, superconductivity and high density waves on nearest neighbor interactions in frustrated lattice geometries. So in principle, if you're interested in quantum geometry, flat band system, multiband systems, high density waves, so linear response theory, or like I already say, superconductivity calculations. Anyway, you're very welcome to my posters, and I would be very happy to talk about all of these, or one of these, and all of the rest is my posters. Thank you.
Marcy?
So, hi everyone, my name is Merce and I'm a postdoc with Daniel, and my poster will be about altermagnetism, which is a new class of magnetic order different from ferromagnetism or antiferromagnetism, as was introduced nicely by a previous presenter. So we focus on the role of spin-orbit coupling, since spin-orbit coupling in altermagnets can induce anomalous Hall effect and weak ferromagnetism. And since they share the same symmetry, we expect that both of them should be large. However, DFT always finds large anomalous Hall effect, but the size of the ferromagnetic moment induced seems to depend on the specific material. So to understand this discrepancy, in the first part of the poster, I will present realistic time-binding models for altermagnetism, And I will use these models to derive an expression for the Berry curvature and also analyze the enormous scale effect, and also to study the free energy and the interplay between the magnetization and the altermagnetic order. And we also show that our results are general and can be understood by a quasi-symmetry argument enabled by spin-orbit coupling. So the idea is that if we have spin-orbit coupling only along one direction, then we still have rotational invariance along this direction. So we can use these symmetries to constrain the size of the ferromagnetic moment and show for which point groups it is expected, the magnetization is expected to be large or small. So thank you.
Good stuff, no worries.
Yeah, so hi everyone. Nice to see you all. So I'm Gustav Romare. I come from the University of Wisconsin-Madison, where I've been working with early astroliths on the superconductivity, to the superconductivity near Van Hook points. So at weak coupling, it is known that Van Hook points should have a kind of drastic increasing the critical temperature. However, at intermediate coupling, the picture is still unclear. So this motivated us to apply hardcore, like numerically exact determinant quantum Monte Carlo methods to kind of resolve this issue. And we find preliminary results that indicate that the Van Hook proximity to the Van Hook have a very small effect on the critical temperature. So while tuning over the Van Hook and plotting temperature or critical temperature, we find a very broad peak. And we also present some preliminary perturbation approaches to try and understand these results analytically. So yeah, if this sounds interesting to some of you, you're all free to talk to me at my poster. Thank you.
June boson.
Hi, my name is Junho, and I'm currently a postdoc at National High Magnetic Field Lab. For my poster, I will mainly talk about my recent work done with Yiting Xu and Una Kim. And this work is motivated by recent series of experiments on untwisted multi-layer graphene, and especially Bernoulli stick bilayer graphene. So what the experiment sees is that there is no superconductivity in Bernoulli bilayer graphene just in itself, but they discover superconductivity in low density and high displacement field regime if spin degeneracy is broken by in-plane field, or making a heterostructure with TMD layers so that coupling breaks spin degeneracy. So inspired by this, we analyzed instability of the Bernoulli bilayer graphene system using the group method, and we believe that when spin degeneracy is intact, instead of a superconductivity, current state of matter or current density wave, where there's an incommensurate modulation of flux actually dominates over superconductivity, and when spin degeneracy is lifted, the P wave superconductivity dominates again. And if you want to if you're interested, come to my poster session. Thank you.
Hi, my name is Ke. I'm from University of Chicago. I'm postdoc from University of Chicago. My poster will be about pair density wave superconductivity. PDW is very exotic. It's spontaneous break the ion and translational symmetry. Its large excitations are gapless with a finite Fermi surface. Tomorrow I will present a microscopic study of superfluid density, which I believe should be essential to the stability and experimental detection and 2D melting theory of the PW. Yeah, thank you.
Yui Wang Radcliffe.
The last one.
I have a later version.
Oh, I see. Still last one.
Because my first name starts with Y, so if there's no one starts with Z, I'm the last one. So the title of my talk is Variation on Diagrammatic Montello built on dynamical mean field theory, and I'm a grad student work with Professor Christian Hardy at Rutgers University. So yeah. We'll read back to the last one. So yes. So imagine you have an action about your project, like the Hubbard model. I'm just taking a Hubbard model as an example, and maybe you would like to do perturbation theory. But the well-known thing is perturbation theory doesn't work well for such a Hubbard model, especially when you would like to start with so-called time-binding project. But we have one flexibility to exert the self-energy. It could be local, non-local, static, dynamic, and take it away as the third term. So there you have one more interactive term, but the entire perturbation is arranged in a different way. So empirically, this is an idea which can work on different kind of systems. And for example, fly cube and fly force field and Hubbard model, that can pass enduring models for conductivity. And empirically, we better insert some self-energy which is from some kind of approximation, like it could be as simple as constant or mean field, BPS, Nikolay, screening field, DMFT, non-crossing approximation according to what you want. And it can be used to solve for better critical temperature, better self-energy, and
30 seconds.
Different critical behaviors. What we did is we applied this idea using some self-energy related to dynamical field theory. And this perturbation itself serves as a cheap non-local extension as DMFT, and which gives much better description for 3D Hubbard model. And thank you. If you're interested, please come to my poster session.
Young, you.
Yeah, so my name is Yang. So I come from University of Michigan. So my poster is about numerical study of Hubbard model using the so-called dynamic cluster formation, which is a cluster extension of dynamic mean field theory. So basically, as introduced by Andrey, that when we check the pairing instability, we are really looking at the vertex function in the particle channel, which is this some kind of this ladder diagram, which is those irreducible vertex function connected by the Green's function lines. And what we find is that there are particular size of diagram very important for the pairing in the Hubbard model, which is in this cloud shape region. They represent the pairing process mitigated by the spin fluctuation. And we find a particular interesting thing in our result is that this spin fermion coupling vertex have a strong momentum and frequency dependence. For example, we find it has a power law relation with the imaginary part of self-energy. And you know, in the pseudo-gap regime, there is a nodal and antinodal dichotomy in the self-energy. So we also observe this spin fermion coupling also have this nodal antinodal dichotomy. For example, here the red line is the along the antinodal direction, and this blue line is along the nodal direction. And okay, so we further explore the role of spin fermion coupling in the pairing. So the conclusion is that we find it boosts the pairing for the underdope regime and dual suppression for the overdope regime. And we find the pairing boost between incoherent fermions by static spin fluctuation is very important. So if you are familiar with the related literature, you will find all the results listed here have very little support from previous study. So if you are interested in this very novel result, please check out my poster tomorrow. Thank you.
That's all. That's it? Yeah, for tomorrow, right? Not for the third.
Yes. Okay, wonderful. Thanks very much, guys. Was very good. So we're almost done for today. So you put your names and
We didn't get it. Yeah, we're not getting the.
Yes.
Yeah.
No, we have not. Oh, no. Okay, so I need to bring it to you back. Okay, good.
So then the rest is always done. So the name will be typed, so there will be information on the conference website about 3 groups. So and you have problems, at least from 2. But and from me again, calculating what we discussed today, and then the problem will come tomorrow. My only request is this, and we'll do part with you. My only request is this, since just organize yourself. And in particular, it would be good if at the end of the day on Friday, there will be one person presenting the work from the group. It will be just you there. So who you choose? If you want to do it half and half, say, basically you will have, each group will have about half an hour. If you go 15 minutes, fine, but just we're not involved. You organize it by yourself. Okay? Very good. We'll bring this to you. For the rest, see you tomorrow, and there's plenty of places to eat around. And if you want to go walk a little bit further, there's even more places. There is a dinky town with a number of places. Well, okay, local food tells you. Okay, guys, see you tomorrow.
The first one I could look at probably gonna take yes. The second one. I can give you
Yeah, just do it.
Thought about it before. Yeah. I was gonna say.
Yeah, graduated last time. Yeah, I have a meeting tomorrow morning. Yes. So yeah. So you can check. Oh yeah. Two and 3 of those.
Yeah, so you have this paper. Yeah, we smart and use factor equation for like.
Oh, it's just do the self exercise.
Not sure. Okay. You know, if it was to go on, but that's important. Yeah, probably. RPA. No, it's not RPA. I am. It's not with a thing.
Yeah, I love it.
Where check comes to see how long have you been in?
No, yeah, so we didn't do it. No,
Just see what.